people are most energetic now. I think especially for yesterday, I can feel
One, welcome to day 2 of RSS 2025. Please take a seat. We're going to get ready, to get started in a short minute here. Before passing it to the session chairs for the first session, I have, just some quick announcement. So yesterday somebody asked for water fountains in the building. Actually, there are no water fountains in the building, but we made sure to put water stations right outside. So if you're thirsty, you want to drink, you can go outside close to the coffee station. For the entire day, there will be water stations as well. That's announcement number 1. Announcement number 2, we found a laptop. So if you lost a laptop, just come to me or come to the volunteers and claim it, I guess. And last, but important thing, we realized that we ran out of food yesterday during dinner, so we're going to have more food tonight. So don't be worried about tonight's Robo night. We'll have plenty of food for it. Okay. With that, I will pass it to the session chair, and we're going to get started with the perception session.
Hey everyone, good morning. Welcome to the perception session. I'm co-chairing the session. My name is Nikolai Atanasov. I'm at UC San Diego, and my co-chair is...
Hey, good to see you. I'm Ayeon Kim from Seoul National University. We will be chairing this session.
So we'll get started promptly. I'm excited to introduce our first paper. The first paper is called Roman. It's Open Set Object Map Alignment for Robust View-Invariant Global Localization. And the presenter is going to be Mason Peterson.
Okay. Hi, everyone. I'm excited to be presenting our work today, Roman, a method for view-invariant global localization. And to set the stage for the rest of this talk, I want you to picture this scene where there are 2 robots, and they're approaching each other from opposite directions, and they're coming up over this hill. And as they do that, if they want to collaborate and share some information, they need to be able to establish some common global coordinate frame so that they can express things like planned trajectories or different things that they've seen in the environment. And the way that this is typically done is that these robots will share with each other visual or different features that they've observed in the environment. So these things are typically things like visual features or objects, and they will then share these with each other and match these. But both of these methods for performing global localization have a few different failure points. So for visual feature matching, they struggle with this really hard problem of matching features across very different views. And object matching tends to not be generalizable because you might not have the objects that you were trained to detect in this specific environment. So Roman is a method that's both view invariant and generalizable. So we map objects that are open set, and that allows us to then perform view invariant global localization by matching these objects by representing a lot of information in this and sometimes ambiguous matching scenarios, and be able to get global localization successfully in very different viewpoints. So Roman stands for Robust Object Map Alignment Anywhere. And you can see here that on the right, you see these 2 robots now. They're crossing each other, and the green lines show matches between different objects. And we're going to zoom out here, and what you'll see is that Roman is very generalizable. We can do this in many different scenarios. So approaching each other from opposite directions in outdoor environments and indoor environments. In the top left, you'll see an air-ground example, and in the bottom, you'll see even across different seasons. And so this is all enabled by this matching these objects, so this thing that's preserved even from different directions, the geometry of these objects. So the first step here is we need to create these open set object maps. And the way that we do this is we take images and we use FastSam to segment these images, and then we track the segments across frames. And you'll see in the bottom right that there are, we're creating this object map as the robots traverse the environment. The challenge then is we send a sparse version of this map across different robots, or maybe you're matching this with a prior session, And then we want to be able to align these small submaps with each other, and that will give us global localization. And the way that we can do this is by matching objects. So finding sets of objects that have high pairwise consistency. And when we do that, we're then able to align these well. And the way that what I mean by this pairwise consistency, if we have this, we represent this with this affinity matrix M, where each element in the affinity matrix represents the consistency of one association with another association, UI and UJ. And we formulate this optimization problem that then allows us to find a set of inlier associations that are all very consistent with each other, like these green lines, and get these good matches in ambiguous scenarios. And so the key idea that we do is that we represent a rich amount of information in each of these elements by taking this gravity or fusion of these different scores. So first is this gravity-guided distance consistency score. So the idea here is that the distance between these two windows should be the same in one map as in the other map. And if you were to take these and line them up on top of each other, that gravity direction should be consistent throughout. And then we also have this object-to-object similarity score that acts on just a single association. That says that two objects should have similar shape and size, and also they should be similar semantics. So you should match. And to show some quick key results, we show that in these instances of performing global localization in opposite directions in this campus environment, we are able to vastly improve the state of the art and do this very quickly. Something like superglue struggles to find any, to perform successfully at all. And we're also able to use this in a multi-robot SLAM system where typical visual feature-based methods aren't able to get any loop closures going opposite directions while we are. And with that, I'm happy to take any questions.
Okay, we have time for a couple questions.
I think there's...
Thanks. Extreme viewpoint change over here.
Got you.
Extreme viewpoint change is really challenging, and well done on this research. Do you notice any compromises in the performance when you're not experiencing severe viewpoint change? So on data sets on Rails, does anything go wrong?
Yeah, I think, so we definitely still see better performance going in same directions, because I think, so things like occlusions and that sort of thing can still make opposite directions more challenging. I think in general, one of the things that you maybe lose a little bit with this object representation is it's a little bit less fine-grained. So the coarser representation means that your accuracy might be the precision of the localization might be a little bit worse than something that's using these very fine-grained visual features.
Okay, Gaurav at the front.
So I was wondering, could you say a few words about how this goes beyond sort of typical data association in SLAM? How does it go beyond just ransack?
Well, yeah, so I guess one of the key differences between this and ransack is that, it's not a random or sampling-based method, that it's solving this global data association problem by, representing this optimization problem that has a wide basin of convergence where we're able to show that we're able to handle outliers that are much, outlier regimes that are much higher than ransack. That if you have only a few inliers, then ransack really struggles to find the good correspondences. So this is shown just to outperform ransack.
Okay, let's thank Mason again.
Okay, we are moving to the second paper. Second paper is Gauss-MI, Gaussian splitting channel mutual information for active 3D reconstruction, and it will be presented by Ixi Kai.
So hi everyone, I'm Ixi. So today I'm gonna present our work, Gaussian channel mutual information for active 3D reconstruction. So for active 3D reconstruction, we actually want the robot to autonomously reconstruct the scene that you are interested in, like this. But the robot needs to select the best next view that it's really interested in, and with maximal efficiency, maximal information they can obtain with fewer power it consumes. So in many current works, they are majorly focused on the geometry completeness without online variation for the visual quality that has already obtained. But there's, of course, some works that already consider visual uncertainty, but there's somehow lack of the computation efficiency that is easy to deploy on an online system. So our goal is trying to develop a high visual quality active 3D reconstruction system. So we firstly design how to select the next best view by a visual quality metric. And following that, we are majorly consider the real-time design, so how to have the real-time view selection methods so that we can do everything online. So yes, so we have a good summary of our challenges that how can we do everything effectively and also efficiently here. Yes, so actually to our method to address everything we propose here, we firstly propose a probability model, which is trying to quantify how much information we have obtained for the Gaussian splitting. And secondly, with the probability model, we're trying to evaluate the expected mutual information gain, so that we know where to go to obtain more information following on. So to be more specific for the probability model, we first of all designed a probability definition to evaluate how much Gaussian is reliable for rendering. And we also have the inverse sensor model that's trying to update the probability in a binary Bayesian filter. So we take the case observation with the image loss as input, and we also consider the cumulative transmittance here, which is commonly considered in the Gaussian splitting. And for high cumulative transmittance, as you see here, so the loss image will high impact on the probability, but with very low, it will not have a high impact on the final probability. And based on the probability model, we developed or designed the Gaussian mutual information here. So it is decomposed for each Gaussian and pixel, and we're organized and also isolated into two parts. And the first term is about the measurement prior, and the second term is about the mutual information reward function. And as you know, we don't know everything about the point in the novel view, the image in novel view. So here we have to assume that the lost image could be 0 in our inverse sensor model. So here's how we simplified everything there. And finally come up with our Gauss MI or Gauss mean definition here. And after we have everything, we have the probability model, we have the Gauss mean metric. So we're trying to integrate them into a system, into a robot system. And we designed a view planner, which is sampling the viewpoints based on the horizontal, vertical velocity, and also the angular velocity in yard. And we select the best next view with the maximal Gauss mean metric, and then we execute the one with the best primitive trajectory towards the viewpoint. And here are some of the early results about qualitative. So yeah, so you can see we have image here. So we start to construct a probability map here. And on the reconstruction, it's growing better. And also we can see there's a rendering of the Gauss mean metric. And we do everything online for the reconstruction and do the evaluation. And you can see that with the progress ongoing, we have a better probability map. And the online reconstruction result is also going to be better. Yes. And following that, I'll also show you this is the online reconstruction result, which is not that good at the beginning because it is limited by the computational resources, but we have a very high probability map mentioning that we have a very good rendering result reliable for that. And this is offline reconstruction or offline refinement. And we also do some real-world applications in a Franda Panca, so the setting is quite similar. We start everything from online reconstruction. And this is actually a tool that the first author, Yuhan, really liked, but she cannot be here because of visa issues. But she really likes it, and hopefully, after I finish my presentation, I hope you can give her the biggest applause and cheers, because this is her really great work that made me here, or made our work here. And yes, this is the online reconstruction result. Yeah, still not that good, and the probability map here, but I think the final coming out, the refinement results is really good, so yeah, that was a cute one, right? Yes, so yeah, that's all about my presentation, and thank you all again, and welcome poster, and big applause for the first author, Yuhan. Thank you.
Thank you. We'll have some questions from floor. On the left, yep, on the left back there, the last row. Yeah.
Where are you?
Can you catch it?
Thank you, this is very interesting. As you're planning these waypoints for the robot to go to, how do you ensure that the waypoint is collision-free and that the robot can get to that waypoint without experiencing a collision? especially if the map is incomplete while you're planning the waypoints?
Actually, for the mapping, we have another occupancy grid map there to ensure everything is collision-free. So yeah, just another low-level planner system to compute and navigate the robot there.
Great, thank you.
Great. Another one from Florida. Okay. I have a question for you. How does your algorithm scales? How the Shannon user information for Gaussian, how does it scale well for a large scale reconstruction?
Yeah, theoretical speaking, can scale up very good because everything is defined theoretical. But the thing is that Gaussian spreading is currently quite limited by the memory consumption. It costs a lot of memory. So yeah, and we need to use the GPU for compute all the things. So still limited by the memory issues. But I believe if there's good development in the memory consumption in the Gaussian spreading method itself, I think we can scale up according to how good it performs with the Gaussian spreading.
Okay, let's thank our speaker again.
Right, the next presentation is LiDAR registration with visual foundation models, and our speaker is Nicholas Biolish.
Okay, so good morning, everyone. My name is Niklas Födisch, and I'm a PhD student at the University of Freiburg. And this morning I'm presenting our work called LiDAR registration with visual foundation models that I did as a visiting PhD student at the University of Zurich. So I'll start with the key idea of our approach. Let's say we have a robot that is equipped with a LiDAR scanner and a surround view RGB camera, a setup that is quite common in many mobile robotic systems. And the goal is now to register this robot to a 3D map. The core idea of our approach is that we utilize DynoV2 image features as point descriptors. And if the same descriptors were also created during the mapping phase, we can then search for point correspondences to perform scan-to-map registration. Before we continue, let's first review some important properties of DynoV2. So DynoV2 has been shown to generalize effectively across a wide range of domains and camera models, and its generated image features can be interpreted as soft semantic labels. These capabilities have led to a broad array of applications, including pixel correspondence matching. And so in this work, we utilize this property to match 3D points instead. So as I mentioned before, we construct point descriptors by first generating pixel-wise features of surround view images and then project these to the LiDAR point cloud using intrinsic and extrinsic calibration parameters. For registration, we compute the cosine similarity between each point of the LiDAR scan and all map points. Due to downsampling and an efficient search algorithm, this is actually quite fast. And then for each point, we keep the connection to the most similar map points if it's above the threshold. And then we use these point-to-point correspondences and feed them to Ransacked to achieve a coarse global registration, which we refine with ICP afterwards. Therefore, the main contribution of our paper is demonstrating that DynoV2 image features can be used as point descriptors for scan-to-map registration without requiring in-domain retraining. In particular, we make 3 claims in our paper. First, that coupling these descriptors with traditional registration methods facilitates robust 3D localization. Second, although simple, our method substantially outperforms more complex baselines. And finally, our method is robust to tempo changes in the environment. We evaluate our approach with 2 long-term datasets, namely the NCLT dataset, which contains data from the range of 1.3 years, and the radar extension of the Oxford Robot Car dataset, which contains recordings from 1.5 weeks. In this talk, though, I will only present results in NCLT now. So on this slide, we evaluate the translation and rotation errors of scan-to-map registration. For this, we assume that we were already able to identify a relevant part of the map of approximately 300 by 300 meters, for instance, via rough place recognition. And then for the exact 3D registration, we do not assume any initial guess, though. So on this plot, we compare our method, shown on the very right, with previous descriptors, including both handcrafted and learning-based examples. For registration here, we utilize RANSAC, and for the learning-based descriptors, we utilize publicly available network weights. And the key takeaway message is that our approach substantially outperforms prior descriptors without using any in-domain training. Then on the next slide, we evaluate the robustness of the DynoV2-based descriptors with respect to temporal changes in the environment. For this, we simulate heavy changes by manually removing trees from the map, and then compare our approach with the two best performing baselines. And here the key insight is that the more trees are being removed, the lower the registration recall of the baselines, whereas our approach is rarely being affected. So to conclude, in this work, we presented an approach to couple traditional registration methods with visual foundation models. And the key advantages of our method are its robustness to temporal changes for map registration and the fact that it does not require in-domain retraining. So for further results, please consult the paper or come to our poster. And if you're interested in the code, make sure to check out the project website. And now, thank you for your attention. I'm happy to take a question. Thank you.
Any questions?
So when you have DynoV2 features from multiple views, how do you aggregate these features to 3D? Is it by some average pooling?
Yeah, I average the features, basically. There was almost no overlap in these data sets between the different cameras, but if there is, just average the features.
Here at the front.
Did you find any problems that these DynoV2 features has like information about geometry? So for example, the viewpoint or the distance towards certain objects? Or did you not find any problems with this when you accumulate into this matching?
No, I didn't see any problems with that. Actually, like the features are pretty stable also if you move towards the object or if you change the viewpoint.
Okay, I think let's thank our speaker again.
Thank you.
Okay, we'll move to our fourth paper, which is building Rome with convex optimization. The presenter will be here with us is Hao-Yu Han.
Hi, everyone. My name is Hao-Yu. Today, I'm going to present my paper, Building Rome with Convex Optimization. For the problem setup, we consider a 3D environment represented as a point cloud and multiple cameras observing the environment as 2D images. The boundary adjustment problem, which is a key computational procedure in structure for motion and SLAM, seeks to simultaneously reconstruct the camera poses and the 3D landmarks from the 2D key point. This problem is formulated by constructing a so-called wheel graph and solving a mathematical optimization on it. Each 3D landmark is a point in R3, and each camera pose is an element in the 3D spatial Euclidean group. The boundary adjustment is then formulated as a nonlinear least squares problem that seeks the optimal poses and landmarks to minimize the reprojection error. This formulation is widely used in COMAP, series, and other popular solvers. From an optimization perspective, this problem is particularly challenging due to two reasons. First, the rational function caused by the 3D to 2D projection, and second, large scale caused by potentially tens of thousands of landmarks and camera poses. Our first contribution is to address the first challenge by lifting the 2D key point to 3D using foundational depth prediction models like depth anything. Then we propose a new scaled boundary adjustment problem that introduces a per image scaling factor to correct the noisy depth prediction. And we minimize the 3D distance error instead of the 2D reprojection. This is a polynomial optimization problem, but still non-convex due to the SG3 constraint and the quadratic objective. Our second contribution is to show that this remaining non-convexity is benign and can be addressed by a TAD semi-definite relaxation. We've done it in 3 steps. First, we solve out the free variables in closed form, and then we develop a quadratically constrained quadratic program by introducing the set of scaled rotations. And at last, we design a short semi-definite relaxation in the spirit of a growing number of convex relaxations, such as SE-sync. We found that this formulation is empirically tight, that it produces a certifiable global optimal. But the existing solvers, such as Mosaic, cannot solve large-scale problems with more than 2,000 images. Therefore, our third and most significant contribution is to develop XM, a globally convergent, initialization-free, and scalable SDP solver that leverages the low likeness of the SDP solution and the bill of material factorization. This is enhanced by a GPU-accelerated Riemann staircase algorithm directly implemented in C++ and CUDA. This staircase converges at rank 3 or 4, making it possible to solve large-scale problems far beyond Mosaic. Here we show the result of bound adjustment in the large dataset, and I want to highlight that on the red column, the largest dataset has more than 10,000 images. We solve it within hours. The classical approach needs a good initialization, and the CPU version is slow. Our algorithm is fast and accurate. We can solve 93 frames only in 70 milliseconds. And we show the result of replica dataset. We have 4 datasets, each with 2,000 images. And the classical approach, COMAP, is robust but very slow. The new approach last year, GLOMAP, is faster but still takes hours. Our algorithm can reconstruct 2,000 images only in 10 seconds. And here we show the realization. On the right is the largest dataset. And we also show the realization of a replica dataset. And we show that the downstream neural rendering task is perfect on this MIP-NERF dataset. Since open sourcing XM, we are excited to see it successfully applied to many real-world problems, some even larger than the largest dataset in our paper. For example, we show the camera poses of a private dataset with more than 20,000 images, and we solve it in 1 hour. Try XM on your own data and let us know how it goes. We'd love to hear your feedback. Thanks for your attention.
Okay. Questions from floor? Okay, if somebody's waiting for, I have a question for you. So you have nice improvement in accuracy, also speed. And then which module do you think contribute to accuracy and the speed? Like, is it the depths from the foundation model or the relaxation? Do you have any idea which module contribute to which performance more?
Yeah, I think first we propose a new formulation that uses a foundation model to estimate depth. So this helps to improve the problem's structure. So it becomes less non-convex, and we can relax it using simultaneous relaxation. So that we are this is an initialization-free formulation that we don't need a good initial guess. And we also develop some CUDA solvers that can fastly solve this. Thank you.
Oh, okay. On the right, the blue shirt in the middle. Yes. Yeah.
Great. Thank you for the talk. So I feel like these convex STP relaxation-based approaches work really well because we have this benign data in the real world. Do you kind of know how much error in your measurements your method can actually handle before the relaxation starts getting loose and we can't do this global optimization?
I think in practice, like almost all the data sets we test, they are quite robust. The relaxation is always tight. I think the only failure case is that if your depth estimation is really noisy, then it somehow will break the relaxation. Thank you.
Okay, so let's thank our speaker again.
Next paper is demonstrating Mozart, opening articulated objects in the real world, and the presenter is Arjun Gupta.
How do we build mobile relation systems which can operate on previously unseen objects in previously unseen environments? This is a challenging task because it requires strong generalization, particularly for mobile manipulators, which require precise navigation, robust perception, and fine-grained manipulation. We seek to answer this question using opening articulated structures as a mobile ablation testbed. We first describe our system and then focus on the lessons we learned from our large-scale in-the-wild study. Specifically, our focus is on the end-to-end performance on this task without any privileged information in novel and real environments. In other words, the robot starts at a location with the object in view and has to approach the object and successfully open it. We adopt a modular system for this approach. Our perception module detects the articulated objects and predicts their articulation parameters purely using onboard sensors. For this, we train a masked RSS2025 model on our prior dataset. Next, our motion planning module uses the predicted parameters using Sadigh to generate a whole body motion plan. And finally, we find it useful to adapt and execute the generated motion plan at test time using proprioceptive feedback, as shown here. Here's an overview of the full pipeline. The first step is perception. Here's an image which shows the output of our perception model. Next, the robot navigates to a user-selected articulated object. Then we run Sadigh to obtain a motion plan, and the pre-grasp pose is achieved. Finally, we run our adaptation mechanism before the full motion plan is deployed. In this project, we ask 3 research questions. Firstly, how does the system compare to large-scale end-to-end learning? Next, how easy is it to extend the system to other types of objects? And finally, how does the system perform across a large-scale in-the-wild evaluation, and where does it fail? First, we compare our modular system to robot utility models, an end-to-end imitation learning policy trained on large-scale data. RUM is trained on a dataset of 1,200 expert demonstrations for opening cabinets and over 500 demonstrations for opening drawers across 40 environments. We find that the modular system substantially outperforms RUM on a paired evaluation across 3 completely unseen buildings. This comparison suggests that modular approaches may generalize better than end-to-end learning approaches, even when imitation learning policies are trained on 1,000+ demonstrations. We also demonstrate that our proposed system can be easily extended to other articulation types, such as ovens, unlike end-to-end learning systems, which would require yet another round of large-scale data collection. Here, we show the results of our in-the-wild empirical evaluation. We evaluate our system on 31 unseen articulated objects across 13 unseen environments from 10 unseen buildings, and find that we are able to open 61% of articulated objects zero-shot in the real world. We conduct an analysis of our system's failure modes. Here's a pie chart classifying different kinds of failures we observe. The main failure mode we encounter is error in perception. Perception failures include failure to detect the cabinet, misdetecting handles, or misclassifying handle orientation. We also encounter execution failures, where the gripper fails to obtain a firm grasp of the handle, as well as navigation failures, where base rotation is particularly inaccurate on carpeted floors. One key takeaway here is that perception is the biggest bottleneck, informing what future research should focus on. There are 3 key takeaways from our study. First, our results caution practitioners that scaling imitation learning datasets to even 1,000+ demonstrations does not necessarily lead to broad generalization. Next, we find that modular systems can be easily extended without requiring extensive new data collection. And finally, we find that perception is the main bottleneck to task success, highlighting the need for future work to focus on more robust perception. Overall, these lessons provide a pragmatic roadmap for researchers and practitioners aiming to build generalizable mobile ablation systems. Code and more videos are available on the project webpage, and thank you all very much for your attention.
Thank you for a great presentation. We have time for some questions. Here at the front.
Thanks a lot for the presentation. So, given that perception is a bigger bottleneck here, how would you start closing the loop, and at which level would you suggest to close the loop for execution as well? So in this modular approach, would you start, because the advantage of end-to-end normally is that you can close this loop at the whole level, throughout the whole scale. But now in this modular approach, how would you start doing these things?
Yeah, so I think So I guess one example of where perception is a big bottleneck in this particular case is like if you have a very small knob that you want to grasp, then A, detecting that knob from some distance is challenging, and then B, if you just open loop, try to grasp that knob, that can be challenging. And so one way to close the loop here, and I think we have some follow-up work actually which does exactly this, is you can close the loop with some kind of closed loop control to actually improve the grasping, where if you can repeatedly detect the small knob that you're trying to grasp, you can grasp it better. So in this particular case, we actually ended up using like visual servoing with these off-the-shelf detectors, and that was one way to close the loop, which would, in some sense, shift the focus from just simply perception to actually what we actually want to do, which is grasp the small knob. If that answers your question.
Thank you.
I think we'll move on in the interest of time, so let's thank Arjun again for the talks.
Okay, our next paper is titled Physics, Object Reconstruction under Occlusion by Fusing Vision and Contact-Rich Physics. We have two presenters for this. It will be presented by Vibit Pianchini and Minghan Zhu.
Hi everyone, I'm Bibit.
And I'm Minghan.
And we're excited to present to you Physics. Dynamics models are a crucial component of some of the most powerful tools in robotics today, including model predictive control and sim-to-real reinforcement learning. Our goal is to rapidly build an accurate dynamics model of a novel object through just a very short video of our robot interacting with it. Vision-based approaches, however, can be limited by occlusion, though the observed motion itself can imply that contact occurred, helping to fill in some gaps. We combine vision and physics to yield our method Physics, which more accurately reconstructs geometry under occlusion. We start with bundle SDF, which estimates object poses over time and the visible geometry. This geometry captures unobstructed details, but poorly explains the observed motion, as shown in this prediction video. Next, our prior work, Physics Learning Library, infers contact events, which can help estimate other dynamics parameters, including what we call visible geometry, or the geometry that best explains the observed motion. We inject these physics insights back into the shape regression, yielding a geometry that both captures visible details and accurately explains the observed motion. We put all of these dynamics parameters into an easily reusable and interpretable URDF of the object. The result is Physics both inherits the dense details of vision-based approaches and the bulk dynamic properties of physics-based approaches. Physics does this with no pre-training, no privileged pose access, and no tactile sensing, estimating everything from just a short video and robot proprioception.
Our approach unifies two sources of geometric insights. The visual observation of geometry is dense, but can be affected by occlusion. Meanwhile, given the known pose of the robot in the known environment, we can get additional supervision from physics, which is sparse, but the estimated contact force can be hypothesized anywhere regardless of visual occlusions. So we combine the two sources to train a sign distance function to represent the object geometry. One of our core contributions is using context to supervise SDF, which is previously only regressed from vision data. Given the hypothesized contact point and normal direction, we can supervise the SDF at the contact point and anywhere along the contact normal, including slightly inside the contact point to encourage zero crossing of the SDF. To broaden the influence of sparse contact point, we can lower bound the SDF at any point based on their distance to the supporting hyperplane defined by the contact point and normal direction. By incorporating the insight from contact-rich dynamics, Physics builds object models with more accurate geometry and dynamics from very brief observation of data. Here, you can see that the data used to train each object model is on average only 10 seconds long. And the physics dynamics prediction approaches the accuracy of simulating using a ground truth geometry. Quantitatively, physics outperforms vision-only reconstruction methods across the board in all of our experiments. And it also outperforms learning-based shape completion methods, showing that the physics insight within the data itself can be more useful than the general prior shape information learned from pre-training. Our model also results in more accurate dynamics predictions. Thanks, everyone, for listening, and we're happy to take questions.
Yeah, we'll have some questions from floor. The front one? Yeah.
Thanks, very interesting work. I suppose a big part of the computer vision community is approaching such problems as perhaps shape completion using neural networks. Have you thought of how potentially you could combine such predictions together with the physics-based reasoning that you're performing?
It's definitely compatible with our approach. So our approach just tries to extract as much information as we can from just the input video, so vision plus the physics. But if there were a third source of information, such as relying on some pre-trained shape priors, then that would obviously also help our approach.
Yeah, we are looking into that, actually, at this moment, yeah.
Okay. Yep, right in the front row, yeah.
Is there an assumption that there is only one object in the occluded space, or can there be multiple in contact?
For now, we only deal with one object, though moving into multiple objects is definitely an area of interest.
Okay, cool. I think because of the time, we will have to proceed with the next speaker. Let's thank the speakers again.
The next paper is Implicit Neural Representation Learning for Elastic Deformable Object Manipulation. And the presentation will be given by Min-Seok Song.
Hi, this is Min-Seok Song, and I'm pleased to present our research project from KAIST. We aim to solve the problem of manipulating deformable objects, particularly elastic band. In the real world, it's a very common industrial material. However, it is challenging due to several problems: self-occlusion, unlimited degree of freedom, stretchableness, and visual similarity between totally different states. So how to represent the state robustly is the open question. Image embedding method is suffer from visual ambiguity, and point cloud embedding method is more robust for visual ambiguity, but it is not designed for elastic deformation. And so we choose implicit representation. Unlike the previous method, we more aim to learn task-relevant feature for robust policy learning. So we propose a new method, which we term INR DOM. INR DOM is consists with two learning stages: pre-training stage and fine-tuning stage. In the pre-training stage, our encoder learn geometry feature by surface reconstruction with SDF function. In the fine-tuning stage, we refine our latent space by jointly update encoder and policy to learn task-relevant features. We pass partial point cloud to encoder-decoder sequence to predict siren weights. Here, siren is kind of implicit neural network for sign distance function. We compute sign distance and gradient as sample point to compute sign distance SDF loss for surface reconstruction. Unlike the point cloud reconstruction, we can sample unlimited number of points on the continuous surface and stretchable surface. It leads to better learning capability for stretchable surface for elastic band. So in the fine-tuning stage, we jointly update encoder and policy to learn task-relevant features during reinforcement learning. Additionally, we also conduct temporal context-based learning to capture the correlation between similar deformation states. For this, we find a positive key from the episode which having minimum dynamic time warping from the Corey episode, and we also sample negative keys from random episode. As a result, we can cluster latents for similar deformation and separate them otherwise. Left figure show that our encoder effectively cluster the deformed state. You can see that our encoder map different twists to distinct region while mapping untwisted of band to in between. And our method achieved the highest cumulative reward than other baselines. We test our method in three different environments: installation, sealing, and disentanglement. Our method achieved the high success rate in the simulation, and we try to transfer our method into the real world. Based on sample-efficient robotics running method, we adopt our point cloud encoder and context learning method to solve the real-world task. We also conduct some comparison between RG-based method and our method to confirm that our method is robust to the occlusion and visual ambiguity. You can see that our method successfully distinguished the two different directions, but this RG-based method failed due to visual ambiguity at intersecting points. In conclusion, I have introduced INR-DOM, which is the implicit visual representation learning method for deformable object manipulation. Thank you for your attention.
Great presentation. Any questions from the audience? I can ask a question while people are thinking. So I was curious if your model can do some prediction, meaning if I apply a certain force to the shape, can you predict how that would change? Is it just based on an instance, or is there a way to predict change?
Yes, in this research, we didn't predict the future state. We only, in the pre-training stage, our method already reconstruct the band shape. Then, yes, in the reinforcement running process, it does not predict the future state. Yes.
Thank you. Any other questions? Okay, if there are no more questions, let's thank the speaker again.
Okay, we'll move on to the next paper, which is particle grid neural dynamics for learning deformable object model from RGBD videos. Yep, floor is yours.
Hi, everyone. We present particle grid neural dynamics for learning deformable object models from RGBD videos. This work is a close collaboration between Columbia and UIUC. Simulation is crucial for robotic manipulation. However, simulating soft and deformable materials remains a significant challenge. This is mainly due to the high degrees of freedom in deformable objects and the partial observability commonly encountered in the real world. In this paper, we propose a learning-based framework that models deformable objects directly from real-world videos, enabling realistic simulation and rendering that are grounded in observed physical behavior. At the core of this task is learning a dynamics model that predicts the next object state from the current state and the robot action. when applied iteratively, this model can serve as a simulator for planning, policy training, and evaluation. The state-of-the-art in learning-based deformable object modeling is graph-based neurodynamics, which models objects as sparse particle graphs with the robot represented as additional nodes. A graph neural network then performs message passing over this structure to predict motion. However, this approach has key limitations. It relies on expert-designed graphs, struggles with long-range dependencies due to limited message passing steps, and performs poorly under partial observations. To address these issues, we introduce our model, particle grid neurodynamics. Instead of sparse particles and handcrafted graphs, our model represents object states using dense particles and predict the future state of particles, including their positions and velocities. The model works in 3 key stages. First, a point-based encoder processes the dense particle input and predicts a neural velocity field on a grid. Then, robot actions and collision boundaries are incorporated directly into the grid, enabling physically grounded interaction. Finally, the edited velocities are transferred back to the particles, predicting their next step motion. With just a few minutes of real interaction data per object, our model generates accurate future state predictions. It generalizes across diverse object types, including cloth, paper bags, and plush toys. For example, unlike state-of-the-art baseline, it correctly predicts the deformation of a partly observable paper bags and avoids geometry artifacts like broken graph in the plush toy. Our approach also handles rope, box, and bread, showing a better capability in modeling global motion and complex deformations like folding and tearing. We further combine particle grid neurodynamics with 3D Gaussian splatting to enable action condition video prediction. This enhances both motion prediction accuracy and visual realism. Compared to the state-of-the-art baseline, our approach produces sharper, more consistent renderings, better aligned with the ground truth videos. This approach scales to high-density reconstructions from phone-scanned videos, enabling realistic simulations of robot-object interactions. It opens up new possibilities for data augmentation, policy training, and real-world evaluation. Finally, we demonstrate that PGND integrates well with model predictive control. Using 3D chamfer distance between the predicted and target point clouds as the objective, our model enables precise planning for diverse tasks, including rope manipulation, box closing, cloth lifting, and plush toy relocation, consistently achieving strong alignment with the desired target states. Thank you. Let's chat more at our poster session.
We'll have some questions. Yep, right in the front, the woman. Yep. Oh, yeah.
Okay, thank you. So your question is basically about like when we cannot observe the interior of an object, do we model them with particles as well, or like do we? So in our model, our model is actually kind of doing an implicit encoding of the particle set using a point-net encoder. So even without the interior points, it is able to extract information about the shape and the position of the object, and it can be used to predict the positions of either the points on the surface, or potentially if you can inject points on the inside, it can also predict the velocities of the points on the inside. So does that answer your question? Thank you.
Okay. Unfortunately, we have to catch up some time, so we have to thank our presenter here, and we'll move on to the next one. Thank you.
Next paper is VHOP, Visual Haptic 6D Object Pose Tracking. And the presenter is Hongyu Lee.
Hi, everyone. My name is Hongyu Lee. I'm a PhD student at Brown University. I'm excited to present our work, VHOP. Object pose estimation is critical for state-based manipulation policies. For example, prior dexterous manipulation policies based on 6D object poses demonstrate high learning efficiency and robustness. Here's a quick recap of the 6D pose estimation problem. The input is an image, and the output are 3D translation and rotation vector, which together form a 6D pose. A closely related problem is 6D pose tracking, which aims to predict the delta pose between frames, given the previous pose and the current observation. Foundation pose, the current state-of-the-art visual pose tracker, achieves near-perfect performance in many scenarios, for example, in this bimanual handover demo. However, the gripper shown here is small, resulting in less occlusion, and the motion is smooth and consistent, which also makes the tracking problem easier. We deployed foundation pose on our bimanual platform. We found that when the dexterous hand attempts to grasp the object, large occlusions are naturally introduced, causing foundation pose to lose tracking entirely, which also applies to in-hand manipulation tasks. To address this issue, the aforementioned works use a camera cage to achieve stable tracking from multiple viewpoints. However, such a multi-view setup is not feasible for mobile manipulation applications such as a home robot. We are inspired by human perceptual system in which both vision and haptic sensing are used to perceive objects. Haptic perception includes both tactile and proprioceptive input. We adopt the pre-trained weights from foundation pose, which follows a render and compare paradigm. The red box here shows the rendered image using the previous pose, while the blue box represents the current observation used for comparison. To integrate vision and haptic modalities, we found that representation is critical for generalization. While vision is inherently embodiment agnostic, haptic, depending on the chosen representation, can significantly affect cross-embodiment performance. For example, prior works use 2D image or 1D vector represent tactile signals. However, these representations are tied to specific layout, which limit cross-embodiment learning. We propose representing the haptic modality using point clouds. Green points here indicate current object model in the camera frame, transformed using the previous pose. Blue points represent the sampled points from the URDF, and red points indicate activated tactile sensors on the gripper. We obtain the tactile point cloud by binarizing sensor values using a preset threshold. This haptic point cloud representation represents the current observation for comparison and also follows a render and compare paradigm. Here is another view of the visualization of the tactile point cloud on Barrett hand. As a result, both vision and haptic modalities are encoded into delta features that represent the pose differences between the current observation and the previous pose. To support visual haptic cross-embodiment learning, we generated a dataset using NVIDIA ISAC-CM featuring 8 grippers and 13 objects. We conducted various experiments on our dataset. We achieved improved performance in terms of ADD and ADDS metrics compared to foundation pose and Vita, our visual tactile baseline. We also compared our method to neurofields on their dataset. Our results shows that we outperformed them in ADDS with 10 times faster inference speed and without requiring a ground truth segmentation mask. Here are some qualitative results of our tracking sequences on YCB objects in the real world. Our results show that combining vision and haptic modalities lead to more stable and robust tracking during manipulation tasks. We also leveraged the estimated pose in motion plans for various manipulation tasks. We show that with accurate real-time pose tracking results, we can avoid human disturbance and achieve generalization to various positions without learning from any demonstrations. Thank you very much for listening to the talk.
Any questions? Yes, there's one here at the front.
Thank you for the nice presentation. I wonder, is there an assumption in this work about the contact point between your end effector and the object is constant? If it's a case, like what happens for the in-hand manipulation, something like that? Thank you.
Yeah, so the question is if there is an assumption on there's the contact points between the hand and objects. So first of all, we are like a tracking method. So basically, we are tracking the delta pose between frames. And when we generate the data set, we kind of randomize the contact between the gripper and the objects. So there is no specific contact pattern because it's generalized and the data distribution is quite widespread across all kinds of contact between the gripper and object. So we can achieve generalization for different contact pattern. And in the paper, we also show like different experiments that, for example, we do a bimanual handover where one hand grasps the object and hand over to another hand. And so the contact pattern is completely different. Yeah, thank you.
Okay, let's thank the speaker again.
Okay, our next presentation, the authors couldn't make it, so we will have a recorded presentation. The title is Auto-Tune, Joint Weight Tuning and Estimation. Because this is recorded, we're not going to have a Q&A session.
Hi, my name is Kasper Hususi, and this is a joint for Iman shapes. There are plenty of important estimation problems in robotics and computer vision. These problems, under standard assumptions, reduce to nonlinear least squares. To be able to solve the problem, we need to know sigma, the measurement noise covariance matrix. This matrix puts weights on measurements, so the optimizer trusts the measurements that are supposed to be more precise more than others. But where do we get sigma from? You can get it from offline calibration. If you're doing that yourself, you need to collect the data set with ground truth, which is not always easy. The data sheet also provides information about the raw measurements, not the pre-processed measurements that we use in our modern pipelines. Finally, if you tune the measurement covariance yourself today, it may not be valid for tomorrow's use because the true sigma may change over time and with different operating conditions. The alternative is what I call vibe tuning. Here, basically, you use an arbitrary value, often the identity matrix, and hope for the best. This is clearly not ideal, but is this a big deal? It is a big deal because if you are wrong about your sigma, the optimizer will trust measurements that it's not supposed to trust, or vice versa, and that leads to a poor estimation accuracy. You will also be under or overconfident in your state estimates. And if you're using the state covariance matrix in your controller or planner, the robot may end up making poor decisions. These are why this problem has been identified as one of the major open challenges in SLAM in this recent review paper. In this work, we propose a method for jointly estimating the states and sigma simultaneously from online or offline collected measurements, and also prior information we may have about sigma. You should think of our algorithm as an auto-tuner that you can add to existing systems to tune sigma for us as it's doing the state estimation. Our approach is based on joint ML or MAP estimation. The gray boxes is what we currently have in standard solvers. What we are adding are shown in red. First of all, sigma now becomes a decision variable that we optimize together with X. And the other red box shows the prior over sigma that you can exploit if you have such priors. In reality, we can have multiple sigmas for different types of measurements or different sensors in sensor fusion scenarios. The joint problem is unfortunately non-convex, but in the paper, we show that the problem of estimating sigma for a fixed value of X is a convex optimization problem. In the paper, we show that this problem has a unique closed form optimal solutions under some conditions, and the solution can be computed really fast in time that grows linearly with the number of measurements. In the paper, we proposed this block coordinate descent algorithm for solving the joint problem. Again, line 6 is the standard iteration of existing solvers for the nonlinear least squares problem. What we have added is shown in red. In these red boxes, we are using the closed form solution that I mentioned in the previous slide for updating sigma. In a post-graph optimization problem with more than 5,000 measurements, the overhead added by these red boxes was about 1 millisecond, which is negligible. We have analyzed the convergence properties of this algorithm in the paper, and we have shown how you can make it robust to outliers using M estimation techniques. We have already added this to G2O, and we are currently adding this to Series and GTSAM. And we're currently testing the algorithm on real-time visual and LiDAR systems such as OrbSLAM3. If you're interested, please reach out. Yulun will be at the poster session to answer your questions, and you can always reach out to me if you have any questions. I'm also looking for a PhD student here at the University of Queensland in Brisbane, Australia. If you know a student, please ask them to contact me. Thank you very much. I hope you enjoy the conference.
Okay, we'll directly move on to the next talk. The next paper is Map Space Belief Prediction for Manipulation Enhanced Mapping. And I think our speaker is João Marcos. Yes.
Hi, everyone. I'm happy to talk to you about our paper on leveraging belief prediction to enable the exploration of interactive scenes efficiently. Is it playing? Okay, so many of the tasks that you execute in your daily life actually require you to do some minimal amount of exploration if you want to actually do them. For instance, imagine you ask your robot to bring you a can of tomato soup from the shelf, which apparently doesn't have any. But if you look a little carefully, you can identify there's at least 2 cans that are hidden by boxes and require manipulation to be revealed. At the same time, there's a lot of other elements in the scene that can be seen just by carefully looking around. So depending on what you ask your robot to do, it has to decide between strategically manipulating the environment to reveal hidden objects, or potentially just looking around and very quickly finding what you need. The problem is when you look at literature, most of the approaches that did exploration would either consider robots that can only manipulate the environment, can only look around, or would heuristically switch between manipulating the environment and looking around, resulting in very inefficient exploration of interactive scenes. Our core insight is that we can leverage, we could model this very complex action switching behavior by leveraging the formalism of partially observable Markov decision processes in map space. However, to solve POMDPs in such an expansive and hard to sample state space, we actually have to leverage confidence calibrated neural networks to enable us to solve this POMDPs by allowing us to reason beyond line of sight whenever we get a new observation, and also to reason about the consequences of actions after an execution. So we solve this by online policy search, by breaking this into 2 different branches. One branch is purely observational, where we use well-known knowledge from information gain literature to find the sequence of most informative, the 2 most informative viewpoints that we could take and score this branch based on this information gain, expected information gain. The other branch is a manipulation branch, which samples different manipulation actions and uses neural networks to predict the consequences of those actions in the maps, and then, once again, using the information gain literature, finds the expected information gain of the most informative view on that specific map. We then execute the action of the most informative branch in a receding horizon fashion. If you choose to do an observation action, we take the robot to the observation point, take that data, and feed that partial observation alongside the previous belief into an observation NABU that predicts the belief at the next time step, helping you reason beyond the line of sight of what you've observed. So, on the other hand, if you decide to manipulate the environment, the robot executes that manipulation and then reuses the belief that it predicted as a consequence of that action being executed in its belief at type T. Here you see an example of a qualitative example of our system running, and you can see its belief being updated in the bottom right. As you can see, the system smartly chooses between different observation actions and manipulation actions, updating its belief according to whatever action it took. As you can see, even though it eventually occludes items that it had previously seen, because of its stateful representation, it does not forget that they exist. and it effectively reveals new items in the environment without causing any drops. We also provide a series of quantitative experiments and simulation that show that we vastly outperform the previous state of the art in interactive scene exploration, in purple here, by finding many more objects in a very cluttered scene. We also show that our action selection strategy vastly outperforms other action selection strategies, even those that can also leverage the neural networks for predicting beyond line of sight and action consequences. Finally, we show that our method generalizes reasonably well zero-shot in hardware experiments, even though we perform very few augmentations during training of our NABU networks. So in summary, we propose a novel approach for solving partially observable Markov decision processes in map space by leveraging confidence-calibrated neural networks to accelerate belief propagation during planning. And this enables a robot to more effectively explore and map interactive scenes. So here you have a link to our paper, you have a link to our code that was released on GitHub. I'm more than happy to talk about any of you during our poster session, and I'm also very happy to take any of your questions right now. So thank you so much for your attention.
Any questions from the audience?
There's one right there.
Oh, yeah, up there. Yes, on the first balcony.
Great talk. I was just curious,
Thank you.
Can you tell us a little bit about the constraints of the system that you're thinking about that requires you to switch off between manipulation and observation? I guess visual observation or something like that. Is there a reason why you can't just always be observing, if you know what I mean?
Yeah. Basically, robots shake, and that's very bad for depth cameras. So if you try to incorporate depth images and you're doing like iterative mapping, you end up with a very bad result in general. But also, it makes planning a little bit more complicated and time inefficient. So basically, it's a twofold problem. One of them is computational efficiency, so we can plan this very quickly. The other one is the quality of the images you get when your robot's moving around, especially if it's not a very high-quality robot. Thanks. You're welcome.
Okay, I think we can thank the speaker and move on.
Thank you very much.
Thank you.
Okay, we'll move on to the next paper, which is PINGS, Gaussian splatting meets distance field with a point-based implicit neural map.
Let me return.
Okay. The floor is yours.
Hello, everyone. I'm Yue Pan. Today, I'd like to present PINGS, a point-based implicit neural map representation that can unify the Gaussian splatting radiance field and also the sign distance field. So nowadays, robots have two kinds of dense scene representations, the distance field and also the radiance field. So distance field can support basic robot navigations, but for high-level applications that require some dense photometric information, the radiance field such as 3D Gaussian splatting is a better choice. And they can support teleoperation, active reconstruction, simulation, and so on. So in our previous work, PINSLAM, we try to use the neural points to model the distance field for LiDAR SLAM. And from that distance field, we can then realize post-estimation of the robot and also the surface mesh reconstruction. So in this work, we additionally integrate a Gaussian splatting-based radiance field into the neural point map so that it can support all kinds of downstream tasks with a unified scene representation. And take a look at this 2D toy example. So in PINSLAM, we use neural points with optimizable shapecode to model the SDF. And now, to additionally model the radiance field, we spawn k Gaussian primitives from each neural point by decoding the shapecode and color code. And we optimize those spawned Gaussians by minimizing the difference between the rendered and observed training images. And when the training image is sparse, sometimes the optimization will converge to a kind of local minimal, while the rendering is photorealistic, but not geometrically inaccurate. So to address this, we use the distance field to kind of rectify those Gaussian splattings. And we use the Gaussian circles instead of the 3D ellipsoids to have better surface representation. And then intuitively, we align those Gaussian circles with the zero ISO surface of the SDF and also the surface normals with the direction of SDF gradient to get a kind of geometrically accurate radiance field. And when the LiDAR data is kind of sparse, but visual data are rich, we can also rectify the distance field with the radiance field. So to summarize, we optimize the shape and color code stored in the neural point map, supervised by the 3D losses from the range data, the 2D losses from rendering, and also a consistency loss between both fields. So we devise a LiDAR visual slant system using such kind of map representation. And here you can see on this Ars Relief dataset, our system take the LiDAR point cloud and also RGB image as input and can jointly build a radiance field that can support photorealistic rendering and also the distance field that can support the surface mesh reconstruction and state estimation. So we also build a large-scale pins map using the robot car in Bonn. So here we show the rendering from this pins map. So here you can see the panoramic rendering and also the neural point map. On top, you can see the RGB rendering, and on the bottom, you can see the surface normal rendering. And on the left, now you can see the surface mesh, which is reconstructed from the distance field modeled by the neural points. So from the experiments, it's validated that our pins can achieve a better radiance field with better, higher RGB and geometric rendering results. It can also achieve better distance field, leading to better surface reconstruction quality, better localization accuracy when used for a distance field-based SLAM system. And also, our pins is kind of elastic to map deformations caused by loop closure. So you can see our rendering is globally consistent with all those duplicated artifacts, such as a tree in the middle of the road. Our pins is also more compact compared with previous radiance field and distance field representations. So we released the source code of pins on GitHub. You're welcome to try it out, and thank you very much for your attention. I'm glad to take questions.
Thank you very much. Is there any questions from floor? Yeah, over there, yes.
Thank you for the interesting talk. I have a quick question about for the number of Gaussians that you spawn for each neural point, how do you determine the K, or is that a kind of a adaptive choice?
Thank you very much for the question. So it's actually an empirical choose number. So we choose 8, but we also try for 16. The results is kind of similar. So we finally use 8 in our experiments.
Any other question? If not, oh yeah, sorry, yeah.
Super quick one, maybe I missed it. Did you comment on runtime? Is it fast enough? Maybe I missed it, sorry.
The runtime is actually not fast enough. So in previous work in SLAM, it can run at a kind of sensor frame rate, but by also adding this Gaussian splitting radiance field, the runtime is about 3 or 4 seconds per frame. So currently, it's not fast enough. Thanks.
Right. Okay. Right, thank you very much. Let's thank our speaker again.
All right, moving on to the next paper. Next paper is Ramen, real-time asynchronous multi-agent neuro-implicit mapping. And I think our presenter is Hong Rei.
Yes. Hi, everyone. My name is Hong Rei. I'm a PhD student from UIUC, and I'm presenting our work, Ramen. So the motivation for our work is for autonomous robotic exploration, and it's very relevant to applications such as search and rescue or planetary exploration. So the question is, what is multi-agent neural implicit mapping? Let's say we have 2 agents, agent 1 and agent 2. Both of them have their local camera and capture a local data set and use that data set to train a neural implicit map. For the multi-agent mapping, they also share the parameters of their map with their neighbors and try to achieve a consensus with their neighbor in the sense that both neural implicit map will eventually converge to the same map that represents the entire seams. So the existing method commonly use CADMM algorithm to solve this problem. We have, say, an agent I and j, and we just drive them towards a consensus target Zij. And this Zij is just a simple average of the two parameters. And then we can do primal and do update to build a map and to enforce the consensus. So the question is, does this method actually work in real world with all the constraint and communication issue? So to evaluate that, we do hardware experiments. We first have a single agent doing the centralized mapping, and then this is the reconstructing mesh. We use this as our ground truth. And then we do the multi-agent mapping with the state-of-the-art method, Dino. And because of all the hardware issue, we only have one communication every 30 seconds. And there's lots of latency and dropout. And this is the random mesh. As you can see, completely diverge and then fail. So the challenge, how do we deal with this kind of communication issue? So the main intuition of our method is a weighted consensus. Let's say we have agent I, and then most of its parameter would correspond to a region that has been well explored that with low uncertainty. But maybe some of its parameter will correspond to a region that hasn't been explored by the robot yet. And let's say we have a neighboring agent J, and because of the communication issue, we haven't heard from it for a while. So we only have a really outdated copy of its neural map. And then most of its parameter will correspond to a region that hasn't been explored yet, so very high uncertainty. But maybe some of the parameters still have useful information that we care about. If we're just doing CADMM, there are consensus targets, a simple average of the two, that would degrade the good information in both of them. So the question is, can we do some kind of weighted consensus that we favor the parameters that with lower uncertainty that have higher quality information? So to do that, we represent our seam as a feature grid. To query a point in the seams, we find the neighboring vertices, we do the interpolation, we pass those values to a decoder. And our first intuition is that the uncertainty of a seam decreases with the frequency of observation. The second intuition is that the update to a vertex happens when the robot visits its corresponding location. So more often the vertex gets updated, the more often the robot visits the location, the more certain we should be about the parameter of that vertex. So using this simple heuristic, we use the frequency-based uncertainty, where we simply use the number of gradient update each parameter gets as its uncertainty. And we normalize that to get our weight for the optimization. And here's a visualization of our uncertainty. The purple is certain, the blue is uncertain. So it divides the scene into a certain part and then an uncertain part. And you can see that actually corresponds pretty well to the reconstructing mesh. And once we have this weight, we can do weighted CADMM. So instead of just using a simple average as our target, now our consensus target becomes a weighted target. And then we perform the weighted primal and do update. So we favor the parameters with lower uncertainty, and we mitigate the bad influence from those parameters because of the communication issue. And here are our hardware experiment results. As you can see, both robots, they map the entire seams using both their observation and through this weighted consensus optimization. And here's our final reconstructing mesh and achieve comparable performance to the ground truth. And also quantitatively, our method is much better than the baseline Dino. So some key takeaway for Raman. Communication disruption is very challenging, and then you can use weighted consensus to solve that challenge. A very simple frequency-based uncertainty is good enough to give you good performance improvement. So if you want to hear more about, have more Raman, please come to our poster site, and thank you very much.
Okay, questions? Yes, one here at the front.
So instead of enforcing theta I equal to theta j, what if you put that as a penalty with soft constraints? Would that give you improvements over the baseline, CADMM?
What do you mean by a soft constraint?
So you penalize 1/2 theta I minus theta j squared in the objective function, and then
yes, that's the
original.
That's the original CADMM.
Okay.
Drive them towards like it's the average of the two parameters. Yes.
Okay.
questions? Yes, there in the middle.
Thank you for the talk. Very interesting work. I was wondering, is like the frequency of the updates enough, or do you add any additional information about viewpoint entropy, for example? So or keyframing mechanism, because if your robot stays still and just like updates the map, does it actually like reduces the uncertainty?
Okay, so you mentioned about the keyframe. At the foundation of our methods, we are using it from CoastLab. And Coastline does have like a whole keyframe that store all the historical frames, and using some kind of important sampling method to do like what frames of pixel we sample from that to do the update. So hope that answers your question. Yes.
We have time for one more very quick question. Yes, here at the front.
Hi, thanks for the talk. Really nice work. I have a question about the weight space. So there's a lot of symmetry in the weight space, and there's also sometimes weights that could give the same reconstruction but are maybe a little bit different. Can you speak to like other alternatives of how you would reach consensus instead of just averaging the two?
Yes. So you mentioned the weight space, like the way we use to weight to like where you drive the consensus towards, right? So what we're using here is very simple. It's like a gradient base. And then the good thing about that is that it basically takes you no extra computation load. So we can run this thing in real time on a really low end laptop GPU, like 2 frames per second. And there are lots of methods from the NERF literature that use in different ways to quantify the weights. And those may give you better performance, but those takes lots of time to compute. So that's kind of the
maybe to clarify, when I say weights, I mean like the weights of the...
Oh, the parameters?
Yes, yes.
Okay.
Parameters of the network.
Okay. What's the question again?
So because, for example, in an MLP, you can kind of permute some of the neurons, right? And then you would get an equivalent output.
Maybe we can
we can talk in the poster side, yes.
So we can keep the session on time. Thank you.
Okay, we have our final paper, robot panoptics, the all-seeing robot with whole body dexterity, and the presenter, this will be presented by Xiaoming So. The floor is yours.
Hi everyone, I'm Xiaomeng, and I'm here today to show you a new creature in our lab, Robopanoptis. It has, so the idea behind Robopanoptis is simple. More motors give you more degrees of freedom, more cameras give you more information. So why not build a lot of boats onto one robot? Let's try it. We will start with this building block, with 1 servo motor and 2 tiny cameras. We can chain many of them together, stick a hook on the end, and we get Robopanoptis. It has 9 degrees of freedom for snake-like flexibility. And it has 21 cameras sprinkled from head to tail. So what new capabilities do these 2 design choices enable? Let's first start with the 9 degrees of freedom. With that much flexibility, it is a natural sweeper. Here it sweeps all cube with 1 body wave. We call this whole body dexterity. And now that's something that a classic 6-off arm just cannot match. So compared to this, Robopanoptis hardware has a lot of potential. But how can we control it to realize all of this potential? If I stick with the common way to teleoperate an arm using a space mouse, I'm back to poking the cube with the end effector only, 1 by 1. So instead, we built a leader-follower teleoperation setup. As I use both of my hands to move the leader robot, the follower robot mimics every twist and bend. And this makes the cube sweeping like 10 times faster. Next, let's look at what Robopanoptis 21 cameras that enable this unboxing task. The goal here is to enter a box through its small side hole and then poke the lid open. So there are many occlusions in this task. So where should we put the camera? Well, a top-down view would get the workspace, but miss where the hole is. A head-only camera would see what's happening inside the box, but miss where the box is. But with Robopanoptis, you don't have to choose where to look. With cameras all on its body, it can see the surroundings, And even it can peek inside the box to find the opening edge. And we call this whole body vision. So now we can train a visual motor policy to infer whole body actions from whole body vision. The pre-trained image features and proprioception are passed to a diffusion transformer policy to infer robot actions. We call this the vanilla policy architecture. So now we want the robot to stow shoes. First open the drawer, poke its head into the shoes, and then finally close the drawer. We train a vanilla policy on this task. The robot generally moves toward the right direction, but often misses by just a few centimeters, achieving only 28% success rate. In other words, it lacks 3D spatial awareness. So we concatenate camera pose of each camera as positional encoding to the image features. And with this additional camera pose information, which can be computed for kinematics, the success rate bumps to 83%. And now there is one last remaining problem. That is reliability. So with so many cameras, when they suddenly drop frames during test time, the robot misses the box opening much more often. So to make the perception system more robust, during training, we randomly mask out camera inputs so that the robot learns to blink and keep going. And this bumps the success rate from 56% to 94%. And this forms the RoboPanoptis policy architecture. Putting it all together, these design choices unlock novel capabilities like whole body dexterity and whole body vision. After I built RoboPanoptis, I asked, why have previous manipulators stuck to 6 off and 1 cameras? Well, previously, more degree of freedom meant more complex control and program, and more sensors meant unreliable control. But now in the era of robot learning, we can use human demonstration for intuitive teaching and use blink training for robust perception. These data-driven methods allow us to explore unconventional hardware design to enable novel capabilities. In other words, we hope that robot learning can allow us to embrace robots of all shapes and sizes. Thank you.
Thank you very much. As we pass the time a little bit, let's have one question from floor, and let's have more questions during our coffee break. Any questions? Yeah.
How much is this new robot?
Oh, it's actually very cheap. So we use like off-the-shelf motors, like the dynamic soul motor. Each motor is like $90, and the cameras are also extremely cheap as well. It's like only $6 for each USB camera. So like the robot in total is like 1K, 2K-ish. Yeah.
Very nice. Thank you.
Thank you.
A quick question. I think we can have another one. Yeah, in the front row. Yeah.
Great. Have you thought about putting it on the ground, doing some locomotion, making it a snake robot as well?
Yeah, that's definitely the hope. So right now, maybe the limitation is like the cameras they're connected to a desktop. That's the current limitation of the system. But like in the future, we can probably use some like small size like camera sensor boards to enable it to like communicate through like Wi-Fi or Bluetooth to make the robot mobile. And like I think that's also one of the point of like putting so many cameras on the robot rather than having like external cameras. Thank you.
Okay, thank you very much. And I was thinking, let's thank our speaker. So let me conclude this session. And quick announcement is we will have coffee break right now until 11 a.m. So the next session starts at 11. So please enjoy the coffee and come back by 11.
Hello, everyone. Please take your seats. It's a great pleasure to introduce our first early career spotlight talk. Our speaker is Dorsa Sadigh. She's an associate professor in computer science and a senior fellow at the Human-Centered AI Institute at Hartford University. She has already achieved quite a bit of impact in our community, despite being an early career faculty member. Her research lies at the intersection of robot learning and human-robot interaction, And she received her doctorate degree in electrical engineering and computer sciences from UC Berkeley in 2017, where she also received her bachelor's degree a little bit earlier, right, 2012. She has received a lot of recognitions, including Sloan Fellowship, the NSF Career and Pecase Award, as well as the ONR Young Investigator Award. Okay, so as you're getting ready to listen to the talk, we're going to hear more about from dirt to data, and we're going to learn a little bit more about gardening today.
Okay.
Dorsa?
All right. Thank you so much for having me. Thanks, Kostas, for the wonderful introduction. Really excited to be here. This is an early career talk. I very much don't feel like an early career person anymore. In fact, I'm in the midst of midlife crisising. But regardless, I would like to talk a little bit about some of the work that we have been doing over the past 7-8 years, and just generally my journey towards adulthood. So that's the goal of this talk. So in 2017, I joined Stanford. And at the time when I joined Stanford, we also moved to Palo Alto and we bought a house. And that was crazy because it was the first time that we had a house and we didn't know what to do with it. And this house had a backyard, and it had this wonderful backyard that was empty. And every single time I would look at this backyard, it would stress me out. It was empty, and I was like, I don't know how to do landscaping or gardening or anything. And what do I do with this? Like, I can't just leave it as it is. And at Stanford, I got a conference room that I turned into a lab. I inherited Daphne Kohler's office. That was exciting. But the common thing between this house and Stanford, my career at Stanford, was it was a clean slate. Like, I kind of was starting from a clean slate. There were so many opportunities. I could do so many wonderful things. And I was kind of unsure what to do or how to approach it. So going back to the gardening example, right? One vision would be to have a lot of wonderful flowers, tulip flowers in our garden. Another vision is maybe to have this Zen space where you can chill during summers. At some point, we were thinking about lots of fruits and vegetables. Maybe we can have lots of fruits and vegetables out of this wonderful garden, or really a space to kind of see our kid grow up in. And similarly, in robotics, when I started in 2017, there were a lot of wonderful problems that I was excited about. So dexterity was for sure one of them. How do we think about building robots that could go beyond pick and place and do dexterous tasks, like picking up food, picking up spaghetti, and transferring that to a person's mouth? We were looking at generalization. This was a time where we were seeing a rise in robot learning. And one of the key problems that it was supposed to help with solving was generalization. So if I change the background, if I add distractors, could I get a generalist policy that could actually work in these scenarios? I was pretty excited about interaction and reactivity. So one of the projects we were looking at was having a robot that can play a game of air hockey with another robot, or maybe with a human. And we started looking at a lot of problems in the space of human-robot interaction. So how do we think about close physical interactions between humans and robots? How do we think about picking up food and transferring that to a person's mouth in a way that is safe and comfortable? And also, how do we think about steerability? What if the robot, what if the human jumps in here and wants to kind of interrupt the robot or talk to the robot? How do we think about these types of problems? So all of these were really, really exciting. And at the same time, roughly a few years later, we started seeing this rise of large language models in the space of natural language processing, to the level that it started addressing so many NLP problems that was extremely exciting for the NLP folks. But also for us, being in the space of robotics, we started wondering the same question. So what would it look like to replicate the success of large language models for robotics? What would be a recipe for building a robotics foundation model? So around this time, we started thinking about this idea as part of this foundation models paper, where we're looking at this idea of having many different data sources. Maybe you have human videos, maybe you have robot data, simulation data, maybe you have language data. And you use all of this data and you pre-train some sort of representation so you could actually fine-tune it for many different downstream tasks. And we started thinking about this vision, what would this solve all those wonderful problems that I laid out in robotics? So as one of our first steps, we started looking at pre-training. It seemed like the difficult part is to figure out this recipe of pre-training. What is that representation? What does it mean to learn a representation that captures all of these different wonderful data that's going in? And around this work, like we started looking at visual representations that are grounded. So this is work that Sid Karamchedi was leading in my lab. He's joining Georgia Tech, actually starting in 2026. And what Sid was looking at was really the layers of this onion. So you could start with learning grounded visual representations as part of this Voltron project. This was RSS2025, where you're using language reasoning, you're using language grounding and language captioning as part of the loss function of learning a visual representation. So the goal is to train this visual representation on lots of human data, and that visual representation could be useful for grounded reasoning in robotics. And building on top of this visual representation, you could go ahead and build a vision language model. So Sid looked at prismatic VLM and actually a number of different projects. So this is a work by Alan Wren, where we used prismatic VLM to actually answer embodied reasoning questions, embodied QAs. Like you go around the house and maybe you're asking, is the lamp next to the sofa turned on? And then you could use conformal prediction and uncertainty estimations on top of a VLM that we developed in the lab. And we could actually like answer these questions and navigate in this space. But the key idea of prismatic VLM that Sid was developing was really thinking about the different components that goes into training these large models. Like what matters when you're training a VLM? Like does the way you're passing in your images matter? Does it matter that you have a frozen language backbone? How are you thinking about your training and scaling laws and things of those forms? And then taking prismatic VLM checkpoint, you could go and fine-tune that even further and then actually train it on action data and get the model to output actions. And this brings me to the OpenVLA work, which is a collaboration with folks at Stanford, at TRI, at Berkeley. This was work that Moojin Kim, Carl Persch, Sid, they were all leading together. And the idea was getting this model to go ahead and output actions. Now I have a vision language action model that is pre-trained and could be my generalist policy for doing many different types of tasks. So turns out the same idea is also present in gardening. I learned about grafting. And the idea of grafting is you have this wonderful rootstock that actually works. It's very resilient. It works with all sorts of pests. It is kind of this nice, wonderful foundation model that you have. And if you really care about having fruitful trees and wonderful flowers, it's really hard to train that from scratch. So you have this rootstock and you have this scion thing that you put on top of it, and boom, all of a sudden, you have all the different types of trees that you want. You get your generalization. And we ended up getting our generalization. We ended up having kumquat trees and passion fruit and pomegranate and plums. And all of these were possible because we had really good rootstocks, because we had really good foundation models. And we actually ended up doing this grafting idea ourselves on a plum tree. So this is a 3-headed plum tree that I'm very proud of, where you can kind of see you have different color flowers here. And we had 3 different types of plums out of the same flower because, again, we have a really good base model that gives us so many different generalizations of plums that we could enjoy during summers. All right, so what is the promise of this idea of robotics foundation model? What is it supposed to give us, right? I think one of the big promises here is that it is a path towards generalization, okay? It is a way of getting generalist robot policies. And I think at this point, you got to pause and ask, well, what is generalization, right? The example that I showed was, oh, you'll throw in different distractors and the policy still works. And that just feels like one example of generalization. That doesn't really capture all types of generalizations that we care about. So for the next 5 minutes, I want to spend a little bit of time kind of getting us on the same page on how to think about generalization. And this is really a taxonomy that we have thought about. It doesn't capture everything. It's probably not the right taxonomy. But at least it gets us on the same page. When we say I have a generalist policy, then we could kind of talk about the details of what that means. So if I were to categorize generalization, I would categorize it into the category of semantic generalization. So if you look at the RT2 model, one of the first vision language action models that we have seen out there from Google DeepMind, this model was able to move a Coke can to a picture of Taylor Swift. And that was really exciting at the time, right? If you think about it, okay, it has a lot of data for moving Coke cans, it's good at that, but it knows who Taylor Swift is, right? And the fact that it knows, I think is impressive. I think we should acknowledge that it is impressive, because now it can tap into internet scale data. Now it can do common sense reasoning. And that is semantic generalization. That doesn't tell me about solving a specific downstream robotics motion, but it does tell me something about reasoning, common sense reasoning, grounded reasoning. In addition to that, we have things like visual and physical generalization. So that is the type of thing where you change the background color, you add distractors, you expect your robot policy to still work in those scenarios. And that's the type of thing that we often solve with, let's say, domain randomization. Or if you pass in simulation data and co-train with simulation data, that is a type of generalization that you could actually get quite a bit of because you could vary these different factors, these visual factors, maybe the physics. And then we've seen a lot of signs of life around co-training with simulation data in terms of achieving this type of generalization. And the last type of generalization, which I would argue is a little overlooked, but it is important, is behavior generalization. So what is behavior generalization? So going back to the RT1, RT2 example, they had a lot of move the Coke can from one place to another place. And it turns out that if you change the table height a little bit, like things don't work anymore, even though the task is the same, right? Like it knows it is moving the Coke can, it's seen a lot of it. Like the change in table height all of a sudden messes up this policy. Why? Because it was trained on data that was of the same table height. So here we're not really getting this motion generalization, this behavior generalization. And more broadly, right, like we might think about a setting where, let's say I'm opening a faucet, and that motion of opening a faucet should be relevant for opening a doorknob. They're different tasks, they look different, their names, their task definitions are different, but the motion, that skill, end up like being important for the other task. And then that's what I refer to as behavior or motion generalization. Like there is some notion of like some sort of skill that ideally I would want to be able to transfer from some task that I've collected data on another task. And I'd argue we don't see so much of this today. So I wanted to kind of like bring up this work, StarGen. So this is a recent work that Jensen and folks at Google DeepMind, Dhruv, Ashwin, Sadigh have been leading. And what we are looking at in this work is that taxonomy. So this is not solving anyone's problem. This is just basically allowing us to get on the same page to talk about generalization. This is not a benchmark. I know roboticists are very allergic to benchmarks. This is not a benchmark. But this is basically taking those three different axes that I mentioned, semantic, visual, and behavior, and kind of like intersections of the two. Of all of them, and think about how we currently measure generalization and how do these different measurements like fall into each one of these categories. So if you go to stargentaxonomy.github.io, what you could do is you also have like this framework where you can throw in an image of the setup that you have. Maybe you have like this bridge, like kitchen setup, and your task information, and you could actually query the model to generate a new kind of like setup for you to test a specific type of generalization. And what we decided to do as part of this paper was to kind of like measure like these policies, these VLAs that are so wonderful, like are they actually generalists? Right? Like how well are they doing on all of these different axes of generalization that I talked about? So here I have this radial plot where ID means in distribution, and everything else around it are these different axes of generalization that we are varying. And here we are looking at open source models and open source data sets. So we're not proposing any new model or any new data set. Open source data sets are the bridge data set and the OpenX embodiment data set. Open source models that we're using at the time is the OpenVLA model, the Pi0 reimplementation, and also MiniVLA, which is a 1 billion parameter version of OpenVLA with vector quantized tokenization. So a little bit of better tokenization than OpenVLA. And here, like what you can see is that, well, in distribution, we are doing pretty well in this bridge setup. This is the bridge results. But then, like, if you look at like viewpoint, like it's 0, right? Like you change the viewpoint of the bridge setup, and it's actually really hard to show any type of generalization there. And of course, this is a function of the data, right? Like this is and model. It's really like kind of like a two-headed thing. It's a function of data and model going together, and we're not getting that type of generalization with OpenVLA. And similarly, like if you look at MiniVLA, it's maybe doing a little bit better, potentially due to the better like tokenizer, but it's not that much better. And similarly, like looking at the Pi0 implementation, we're seeing again like some benefits across some axes, but still there's quite a bit of room for improvement. So there's a ton to unpack here. It's in the paper. I'm not going to be able to unpack everything, and we have like all these other applications around data set size, various types of tokenizers. But again, the point of this work was to get us around the same definitions of measuring generalization so we don't just go around and say, well, we have generalist policies. All right. So, okay. So but what should we do in terms of a path towards generalization? Right? Like I'm still like claiming this robotics foundation model direction maybe has some promise for that. But what is the recipe for getting there, right? Like what are our options in terms of actually taking a step towards better generalist policies? And specifically, one thing that I am personally excited about is behavior generalization, right? Because sure, like we get into like internet data, like we now know who Taylor Swift is, but I think the more important thing for us as roboticists is, do we get behavior generalization? Or do we need to like collect a continuum of like data because the world is continuous and this is just not going to scale up? My personal belief is we have seen some signs of compositional generalization, so the story of collecting data might just work out. But in practice, I think there's a spectrum here. There's a spectrum, and on one end of the spectrum is to collect as much data as you can and cross your fingers. It feels a little unscientific, but might be the answer. Maybe we'll all be surprised, and maybe that is the answer. And then there's the other end of the, and then actually like going back to my fruit examples, like I think there's an analogy here with like a path towards fruitful trees, right? Like one end of the spectrum, you can have lots of flowers and bees and cross your fingers and hope for the bees to just get their job done. And if you really care about having many different types of fruits, the bees will do the job and you'll have lots of fruits. And that's actually what we hoped for in our garden. So we had this pomegranate tree. We were very excited about it. We really love pomegranate. And we had lots of bees, and we thought, okay, like these bees will get the job done, and all of these wonderful flowers will turn out to be pomegranates. Fall comes, we end up with 2 pomegranates. We were very happy about it, but it was 2, and it was kind of sad. So what we did the next year was we were like, okay, this idea of scaling like flowers and bees and crossing your finger doesn't really work out. You need to do some cleverness. And what is the cleverness? Well, the cleverness, it turns out in gardening, is to use a paintbrush and go and pollinate all your flowers to make sure they turn out to be fruits. And we did that. We did that with pomegranate. We did that with passion fruit. So these are our passion fruit flowers. We used the paintbrush. Using the paintbrush approach, we ended up with lots of passion fruits. I think I ended up giving like some passion fruit jams to Jeanette at some point, and all the neighbors and our chair. And so if you want passion fruits over the summer, we have a lot of passion fruits. And the way that we are getting that is by cleverness, right? The cleverness is to tie the net between all your flowers, right? Like make deeper connections between your flowers. And you could do the same cleverness in VLAs, right? So why is it that they're not generalizing? Why is it that we are lacking behavior generalization? I'd argue one reason is that the tie between your actions and your vision language backbone is minimal. And you could actually make an effort to make them much more connected. If you know what is that skill, opening doorknob or opening like a faucet, what is that skill, and you have a representation of that skill, then you could potentially like connect those 2 tasks, even in language and even in the visual representation, and realize that their actions are actually similar. So one implementation of this cleverness is to use some sort of mid-level representation, right? Like maybe it is your bounding boxes, maybe it is your key points, maybe it is your traces, right? So some sort of representation here that is useful for grounding and actually helps us connect our actions with the vision language backbone. So I want to briefly mention some of the works that we have been doing in the space of tying vision, language, and actions. And I want to kind of like briefly mention 2 works here. RTH is one of the first works that we explored here. So this is RT hierarchy. This is the work that Sunil was leading with folks at Google DeepMind. And then afterwards, I want to kind of like talk about the expansion of that to the idea of mid-level experts. This is a work that Jonathan is presenting here at this RSS. So what do I mean by tying vision language with actions? So if you think about it, the actions that we are taking, like the fact that I'm turning a doorknob, that turning behavior, like there's a language that refers to that. And the key idea that we had here is, can we use language, but not high-level language, low-level language to actually connect our actions with the rest of this vision language backbone? So if you think about language in robotics, how do we use language in robotics? Oftentimes, language is used to represent a task. So for example, I have pick up Coke can and pick up the chip bag. So if I look at these 2 pickup tasks and I recognize, well, both of them are pickups, then I could kind of like, again, like align them a little bit more and try to learn from pick up the chip bag for picking up the Coke can, okay? But in practice, we have a lot of diverse task instructions. In practice, if I look at 2 other tasks, like pick up the Coke can and knock the water bottle over, like their names look different from each other. They seem to be semantically pretty different from each other. But it turns out even in this scenario, they share very similar behaviors. Even in the scenario where the task names are quite different from each other, there's this idea of moving the arm left. And there's also this idea of closing the gripper, like that shows up across like both of these tasks. So the key idea that we had here was to use language motions. What I mean by language motion is a language that refers to that low-level motion to actually capture these more fine-grained actions that the robot is doing around the task instruction and actually like build better ties between our cross-embodiment multitask data sets. So this brings us to RTH. So the idea is that we start with kind of like the task of close the pistachio bar, let's say, and we ask the model, we ask the same VLA, like what motion should the task do to, should the robot do to achieve the task? And you get the motion and you condition on that motion and get the model to actually output actions. So you have a language motion query, you have an action query, and the same model is actually going to be able to act as both of them. And you start seeing like benefits of this. So this is, again, simplified setting. This doesn't have a ton of data. This was built on top of RT2. So RT2 is my flat model. And then I have RTH, which is querying for both language, motion, and action. And I see quite a bit of difference between the two when we have like diverse multitask data. We start benefiting from all the data that we have collected and building these ties a little more. You could take this idea further and make it a little bit more generalizable. It's not just language motions. It is all mid-level representations that we could really benefit. And this brings me to Jonathan's work at this RSS, where we are looking at various types of representations like object-centric and motion-centric and pose-aware and depth-aware representations that we could get our hands on, and really using these representations to demonstrate a bit of generalization for complex tasks. So the task we are looking at here is, let's say, tying like shoelaces. And if I capture things like the traces or the bounding boxes, it turns out like all these different information is quite useful. And I can have a self-attention layer that attends to these mid-level representations that I'm getting here. And that allows me to get quite a bit of generalization on this type of task. All right, so that was the idea of cleverness, right? Like you could use some level of cleverness, some level of algorithmic ideas here to actually get more benefits and get this generalization. But I was chatting with actually Tatsuya Hashimoto, who's one of our NLP faculty, recently about this. And he was like, well, in NLP, we always thought you need cleverness. And we were proven wrong. You actually don't need so much cleverness. And I think there is this question of, do we need cleverness? And I personally like struggle with that question often. Like, do we need all of this cleverness? And going back to my gardening example, right? Like I argued you need cleverness, but then, I don't know, over time, we got older and not maybe as passionate about it. And we ended up with a bunch of lavender flowers all of a sudden in our front yard. And these lavender flowers bring so many bees now. And like we don't do the paintbrush thing anymore, but we still have passion fruit. So it turns out that if you scale up, if you truly scale up like your flowers and bees, you still get the generalization too. So there is a benefit to scaling up. So I don't want to undermine like this benefit of scaling up and collecting data and leveraging data. I do think this is important, as much as unsatisfying it feels like from an academic perspective. I don't know if everyone even agrees with that, but it is an important piece that we need to pay attention to. Like data matters, and like we should think about the quality of data, we should think about how we are collecting it, guiding that collection, active learning. And then we're doing a bunch of work in that space that I'm not going to be able to talk about in this short time, but I want to just briefly mention one fun project that we have explored in this idea of scaling up robotics data. And this brings me to RoboCrowd. This was a work that was just presented at ICRA a couple weeks ago. And the idea is, if you want to scale up your data, well, one approach is to hire people to come and give you data. So Google DeepMind has a whole process of all of these different Aloha cells where you have teleoperators who come in, sometimes they're professional gamers, who come in and collect data for you, right? Like collect robotics data that we could actually leverage. And one could argue that doesn't really scale up, so we need to have a path for scaling up robotics data that is maybe more achievable long term. So the idea that we had here was, could we distribute robot data collection via crowdsourcing? And could we explore incentive design here to actually crowdsource this type of data? So in RoboCrowd, we had basically one Aloha set up in a coffee shop at Stanford. We left it over there for, I think, a 2-week period, and anyone with a Stanford badge could come in and collect, give us data. And we started exploring incentive questions here. So what are the incentives for people giving us data? Well, it turns out material rewards matters. This was kind of obvious. We were giving out candy, and the type of candy matters. So the point here was, if the candy is better, people will give you better data and more data. The second point that was maybe a little bit surprising to me was intrinsic motivation. So we had a setup where we had the candy just sitting there versus a setup where you had to take the candy out of a Ziploc bag And it turns out that people like to do the harder thing. So we ended up getting more and better data on the harder thing of like opening the Ziploc bag and getting a candy out of it. So that was interesting and a little bit surprising to me. And then at the end, like social comparison also matters. If you create an app around it and have a leaderboard, people compete and give you better and more data. So it was kind of like interesting to explore all these different incentive questions. It turns out you could collect data and you could co-train on that data on non-candy tasks too. And that data is useful. So that's just in general something that we're very interested in, like how could we gamify data collection in a way that is fun and interesting so we could collect data in a more effective way and scale up data collection a little bit more effectively. Okay? So this was kind of like my story of like how we are thinking about a path towards generalization. Let me go back on this slide. So I kind of like talked about the spectrum, 2 ways of looking at the spectrum. But I want to briefly mention some other things that we weren't expecting on this path towards generalization, right? Like that was the thing that we were hoping for. But then we have ended up having really fun, interesting interactions with robots with these types of like VLAs that I wasn't personally expecting. So Gemini Robotics recently like put out a release on like their recent models, their recent like VLAs. This is a long video. I'm not going to play all of it, but this is basically, and I don't even want to, like, I'm not showing the audio here either, but this is an interaction that I had. This is kind of like an uncut video of me interacting with this robot during like a half-an-hour meeting like time that I had. So I go to Google on Thursdays, so I spend 1 day a week at Google DeepMind, and I literally had like half an hour between meetings, and I dragged Dhruv, and I was like, Dhruv, can I play with the robot? And this was kind of like a real, genuine interaction that I had with this robot. The full video is somewhere like on Twitter or somewhere online. But the point here was not that, oh my God, the robot is such a wonderful generalist, but it was a little bit of that, actually, because like the objects that you see here are my son's toys. So there were objects that the robot had never seen before. I like brought them like to the office in the morning. But the point was I had such a rich interaction with this robot, right? Like I could actually talk to it. It could like recognize what I'm drawing, what I'm making, what origami thing I'm making. It would make a mistake and it would like correct itself. I could interrupt it in real time. And it almost like felt like, oh, this is the first time that we could really do like HRI research and we're not assuming too much about robotics. Like robotics is like finally at a stage where I could think about rich interactions between humans and robots. And that aspect of it was really exciting. And similarly, our garden has given us so much in ways that we weren't expecting when I first was looking at that empty backyard. Like we have spent so much like wonderful time and rich interactions. We have had so many rich interactions in this garden that, again, like I was not expecting going into this. So I think that is really exciting, that aspect that you hope for something, but then there's so much more here to do. All right, so with that, that's kind of like a summary of what I want to talk about. I do want to do credits for a second. Going back to gardening, I don't really garden, guys. So I remember during the pandemic, there was a Zoom call once, and people were talking about their hobbies, and someone asked me, well, what is your hobby? And I freaked out, and I was like, gardening. But that's really my partner's hobby, and he was so mad that I stole his hobby. So I decided to steal his hobby again and talk about gardening in this talk, but all the credit really like goes to him for the wonderful garden that we have. And honestly, like all the credit for all the work that I talked about goes to all the wonderful students and collaborators that I've worked with. So thank you to Iliad Lab, thank you collaborators at Google DeepMind, at TRI, at Berkeley. Yeah, and with that, I'll just end here, and I can take any questions if there's any.
Great, thank you, Dorsa. We have time for 1 or 2 questions before we get to our next session. We have a question here on the right.
Eric.
Hi.
Oh, wait, where am I?
Just over here.
Okay.
Thanks very much for the talk. Yeah, the RoboCrowd stuff was impressive. It was cool that you managed to scale that sort of thing. I'm wondering, is it still going? If not, what's to stop you from scaling that up and just winning robotics? As in, what are the reasons that maybe it doesn't work? Or you can just say it will work.
Yeah, no, that's a very good question. Yeah, so scaling that up properly, it's still going. Scaling that up properly is interesting. So I think there are two ways to go about it. One way that we are exploring is literally making a game out of it. So like working with gamers who can actually teleoperate the robot. The challenge is there is oftentimes you need to send them like some sort of like teleoperation system, maybe a Jello system. So we're working with Frodobots to actually like make that happen and work with real gamers for that. But then you need to get like remote teleop working for that. So if I'm really like tapping into the gamers community, then that means that like I need to have remote teleop working, which is often really difficult. Depth perception is kind of challenging. So making a fun game out of like data collection, I think is an interesting project. Again, we are exploring that. There's the other aspect of like putting one of these systems like maybe in a mall or in an arcade. I think that's also like very much possible. That means that, well, we need to have people and robots for making that happen. In this work, like that 2-week period, I think poor Severe was like watching the robot like on call like for a 2-week period. So that ends up a little bit unscalable in a kind of like lab academic setting. But definitely like I think an interesting idea to explore.
All right, thank you.
Okay, and perhaps a second and last question here.
Hi, thanks for an inspiring talk. It's really great to see you mention mid-level representations feeding into robotics. So having worked in computer vision for many years, one of my questions is, computer vision has almost solved, what can be called instant segmentation, panoptic segmentation, 3D representations, and so on. So why not adopt them as whole hog to move robotics forward?
I think that's a good question. I think, yeah, so in practice, I do think we should use more of these mid-level representations. I think sometimes like for example, let's look at like depth, right? So like, do I need like depth information? Like when I look at like these types of VLAs, like finding good scenarios that also like showcase that sometimes is often also challenging. So I think it comes, short answer is we should be doing that. And because we don't have good ways of measuring generalization, it's a bit of a benchmarking. It's really difficult to tell, did it move the needle? So I think it goes back to the first part of the talk that I was talking about. We need to have some ways of measuring generalization so we can demonstrate using these mid-level representations is actually moving a needle.
Great. Please stay on your seats for the next session, which is on planning, and let's thank Dorsa one last time.
Okay, everyone. I'd like to welcome you all to session 5 on planning. I'm your session chair, Chris Hauser from the University of Illinois.
And I'm Negar Mer from the University of California, Berkeley.
So our first paper is going to be presented by Bowen Lee.
Hello, everyone. My name is Bowen Lee, and I'm very glad to be here to introduce our work, Bi-level Learning for Bi-level Planning. If you feel interested, please scan our QR code to visit our project website. Let's start by considering this task. The robot hopes to transport an object that is placed high on table to a container by using a platform. To achieve this task, we can collect long-horizon demonstration datasets consisting of low-level states such as continuous poses, images, or point clouds, with high-level actions such as move to, pick, gaze, place, grasp, etc. With this long-horizon demonstration dataset, we hope to train a model that can achieve high-level generalization, where the new tasks can have new objects, new goals that requires longer action sequences to achieve. For example, in this never-seen-before test scenario, both the container and the object are placed high. How can the robot still put the object into the container? If we are doing naive imitation, the robot will learn to first pick and place the platform and grasp the object. However, at this point, the container is still not reachable. What's worse, the robot also cannot move the platforms around to reach the container because its hand is not empty. If we have a high-level predicate, hand empty, which is the precondition of action pick and delete effect of action grasp, the robot would automatically know that it needs to first rearrange the two platforms before grasping the object. Therefore, we can expect zero-shot generalized behavior like this. the robot automatically finds out that it needs to first rearrange the two platforms into corresponding locations, walk onto it to grasp the object, and finally transport the object into the container. However, given the low-level transition pairs we see during demonstration, how can we automatically create the high-level representation or the predicates? In this work, we introduced a novel bi-level learning system, the inventor, which can automatically invent neural network state abstractions or the predicates from the low-level demonstration dataset. And the invented predicates enable the learning of a bi-level planner, including planning operators and samplers. We evaluated our work on 6 diverse robot planning domains with various state abstractions, such as IC2 poses, 3D locations, IC3 poses, and high-dimensional point clouds. With the invented neural predicates, our system can successfully solve the unseen tasks, where the task can have new objects, and states and goals require longer action sequences. However, most other pure behavior cloning methods fail to generalize. Specifically, the key innovation of our system is the bi-level learning framework, where the neural learning of predicate functions and the symbolic learning of predicate effects alternate. Given the low-level transition pairs of different high-level actions, our system starts by proposing the high-level effect of a predicate. This high-level effect can serve as the labels on the transition data we see during training. They can enable the learning of a neural classifier served as the high-level presentation. After neural learning, we collect the neural learning loss, which can serve as a guidance for the next iteration of symbolic effect proposed. So such iterative bi-level learning finally construct a rich neural predicate pool where the neural functions have minimum loss with respect to the transition data we see during training and the high-level effect. We collect predicates with different types as input to form a large candidate pool, and we conduct a down selection on this pool where the final set minimizes planning time and maximizes planning success. With the final set of predicates, we finally learn the planning operators and samplers. The findings from our work underscore the promise of planning and learning with abstractions as a path towards generalization. Thank you.
We have time for questions. On the ground floor on the right.
Hi, thanks for the talk. So I have a question about how this can be leveraged to, or say, can this be leveraged to solve some temporal logic tasks?
Yeah, this is a very, very good question. So actually what we use here is called PDDL. It doesn't quite consider the time horizon of constraints. So we are working actively on integrating time constraints into PDDL. So we are trying LTL and also signal temporal logic for this planning task also. Yeah.
Maybe one more quick question. Also on the right. Ground floor on the right.
Could you repeat again? Sorry.
If the environment changes, if the environment is dynamic, how will the task change? Will it work for even dynamic environments?
Yeah, I think during training we have variance on the states. So I think the change of the location of the platforms doesn't quite affect the high-level task and low-level sampler. And by the way, our invented predicates can also guide the low-level sampling.
Let's thank the speaker one more time.
Thank you.
So next we have a biconvex method for minimum time motion planning through sequences of convex sets by Tobia Marcucci.
Thank you for the introduction, and good morning, everyone. My name is Tobia Marcucci, and today I will present a new biconvex method for minimum time motion planning through sequences of convex sets that we have developed at Amazon Robotics. At Amazon, we are pushing the boundaries of warehouse automation, and one of the core problems in this area is minimum time motion planning. Consider, for example, the robot shown on the right, Sparrow, whose goal is to sort products into bins as quickly as possible. The algorithms that move this robot must be extremely reliable, they must be very fast, and they must also push the hardware to the limit by generating high-quality trajectories. In this work, we have focused on a limited but practically important class of problems, and we have developed a motion planning algorithm that actually meets these three criteria. This is the problem statement. We seek a trajectory Q of minimum time duration, capital T, that traverses a given sequence of convex sets, Q1 through Qi. The initial and final points of the trajectory are specified, and the initial and final velocity of the trajectory must be 0. And we also have convex velocity and acceleration constraints that the velocity must satisfy at every time. Our algorithm is based on a key observation. The minimum time problem I just described is naturally reformulated as a non-convex program, but it actually becomes convex and therefore easy to solve if we fix either the transition points or the transition velocities. The transition points are shown on the left, and they are the points that we select for our trajectory to move from one convex set to the next, while the transition velocities are shown on the right, and they are the trajectory derivative evaluated at the transition points. So this key observation motivates the following algorithm. We start by designing a polygonal trajectory that traverses our safe sets and has a short time duration. Then we fix the transition points of this polygonal curve, and we obtain a convex program that we can quickly solve to reduce the cost, so the duration of our trajectory. Then we fix the transition velocities of this improved trajectory, and we get a second convex program that we can solve again in order to reduce the trajectory cost. This process, this alternation is repeated until convergence. We solve a new convex program with fixed transition points, and then we solve another convex program with fixed transition velocities. When the cost decrease of an iteration is small enough, we exit our algorithm and we return the trajectory we converge to. So these are the strengths and the limitations of our approach. On the one hand, our approach is fully reliable. In fact, it's a complete planning algorithm. It's also anytime and parameter-free. It is pretty fast. It takes tens of milliseconds to solve large-scale planning problems in Python. And it also pushes the hardware to the limit by finding trajectories, minimum time trajectories that are typically globally optimal. On the other hand, it's not always easy to describe the free space of a robot using safe convex sets, although Pete in the next presentation will present a very good method for doing this step. And also, we cannot handle yet constraints on the trajectory jerk or higher derivative constraints. We compared thoroughly our method against state-of-the-art solvers for non-convex optimization. Here you see the runtimes of our method in red, versus the runtimes of SNOPT in green and IPOPT in blue. From the top left to the bottom right, we consider problems with increasing number of safe sets, space dimension, facets of the convex sets, and trajectory degree. And across the board, our method is more reliable than the state-of-the-art solvers, and is also significantly faster, about an order of magnitude faster. We compared also our approach with industry standard planners like waypoint-based motion planners. In this case, we have two Sparrow robots that need to collaborate in order to unload a bin full of packages in minimum time. Over 50 of these problems, our method allows to transfer 50% more packages per unit of time with the same algorithmic reliability of the baseline. Thank you very much. Happy to take any questions.
Okay, time for questions in the front row.
Thanks for a great talk.
Thank you.
If my understanding is correct, I think your algorithm actually has a two-component-wise convex optimization. Mm-hmm. So I wonder where do you guarantee the global optimality? Because I think if you, because they are just doing coordinate-wise.
No, yeah, it's a good question. As I mentioned, typically, empirically, we verify that often we converge to the global optimum, but these problems do have local minima and there is no actual guarantee that we are able to escape from one. The truth is that we need an algorithm that is fully reliable, is guaranteed to converge, and sometimes you do not converge to the global minimum. It's kind of rare. You need to kind of cook up examples in a smart way to find those cases, though.
Thank you.
Thank you.
Okay, we have time for another quick question on the right.
For the great talk. The question I had is more on constructing of the convex set. So if the scene is dynamic and like changes quite frequently, would you have to reconstruct the sets? And if yes, the millisecond time that you were talking about, did that involve the set construction time too? And what I want to understand is, if no, then how would this scale with like more dynamic?
I think we can take this offline in the interest of essentially having the session run on time.
Yeah, the next speaker will have a presentation exactly on this step, and yeah, you'll see it the next speaker.
Let's thank Kubia one more time. Our next speaker is Peter Werner, presenting superfast configuration space convex set computation on GPUs for online motion planning. I couldn't have planned it any better.
Okay, hi everyone, I'm Pete, and I'm here today to talk about our work on motion planning. Motion planning is a fundamental problem in robotics, and in recent years, there's been a push to combine the best of the two most established approaches into decomposition-based motion planners. The idea is to combine the reliability of sampling-based motion planning and the expressiveness of nonlinear trajectory optimization. Decomposition-based motion planners work by first approximating the free space through a union of convex sets, and then planning a trajectory through the union of these sets. This allows us to replace nasty non-convex collision avoidance constraints with simple convex constraints. The catch, though, is if we want to use these planners, we actually have to compute these sets, which is challenging. We want the sets to cover interesting trajectories so our planner can find them. We want a small number of sets to make the planner efficient. And finally, we want these sets to live in configuration space to make the approach general. And yeah, somewhat unsurprisingly, set construction has been a bottleneck in adopting these planners. And this is mainly due to the complexity of configuration space. It's not obvious how to place these convex sets to cover interesting trajectories or guarantee their connectivity. And also constructing the individual sets has so far not been real-time feasible and has only been done for static environments. In this paper, we show that we can alleviate some of these challenges by demonstrating that the set computation can be dramatically accelerated, done reliably, and is now indeed real-time feasible. And yeah, our key contribution is an algorithm that takes in a collision-free line segment in configuration space and inflates it into a probabilistically collision-free polytope in configuration space. And this algorithm only relies on collision checking and is massively parallelizable, which we leverage to implement it in CUDA and run it entirely on the GPU. And now that we can compute these sets rapidly, we face the next challenge, which is actually placing the sets. And here we can use a pragmatic solution from the past, which was to inflate a piecewise linear path found with sampling-based search, which then inherently guarantees feasibility. And we can now apply this approach in configuration space with our new algorithm. And so now we can put the puzzle pieces together into an entire motion planning pipeline that allows us to use these decomposition-based motion planners in configuration space. We propose to pre-compute a dynamic roadmap offline, which we can then rapidly query online to get piecewise linear paths, which we inflate and then use in the planner. And now, because these sets are only probabilistically collision-free, we also propose an online correction scheme if the trajectory ends up in collision. We evaluated our approach on a simulation benchmark and on hardware, and we found that while compared to a trajectory optimization baseline, we produced slightly higher costs, we're 17 times faster on average and dramatically more reliable. And most importantly, the set construction was no longer an obvious bottleneck. I now have some videos from our hardware experiments to share. You're going to see a robot setup with 3 cameras that are capturing a voxel map of the environment. And then every time I hit the button is when the planner runs. And we're using SCS planning, which was just presented to optimize minimum time trajectories for the robot in 7 dimensions. And to get a peek under the hood of what's going on, we can also visualize some 2-dimensional configuration space slices to get an idea of what these sets actually look like. Cool. With that, I'd like to conclude my talk and thank my collaborators. We've made the code open source. There are Python examples, and also the full videos are there, so make sure to check that out. Thank you.
Did that answer your question, sir? All right. Any other questions? Over there, ground floor in the middle.
Thanks. How well do these methods scale with the number of degrees of freedom of the robot?
So far, we've run it on 7 DOF problems pretty comfortably, where the set computation takes like, I think per set, it depends on how many voxels you have, but like around 1/10 of a second. And yeah, it's still subject to future work to see if we can do this for like a bimanual system with like 14 degrees of freedom. But I think if you just have like a single arm robot manipulator, you're golden. It should work. Yeah.
Question over here, ground floor.
So the one thing there is that you still have an offline roadmap phase. How much is that meaningful if you do have a dynamic environment? For example, you're moving boxes.
Yeah. So the dynamic roadmap we use to get initial piecewise linear path that's collision-free. If you recall, the algorithm requires an initial collision-free piecewise linear path. So I know there's like a lot of new work on generating these paths really quickly with VAMP, for example. So maybe you can just replace this module with VAMP, for instance. I think there's many solutions here. This is just a possible solution.
Let's thank Peter once again.
Okay, next we have global contact-rich planning with the sparsity-rich semi-definite relaxations by Heng Yang.
Hello, everyone. I'm Hen. Today, I'll present our paper, Global Contact-Rich Planning with Sparsity-Rich Semi-Definite Relaxations. This is joint work with 2 amazing students, Xu Chen and Guo Rui. Contact-rich planning plays an essential role in robotics. We formulate contact-rich planning as polynomial operation. Here, x is a state, u is a control, lambda is a contact variable representing either binary contact modes or continuous contact forces. Fk is discrete time dynamics, Ck is a general path constraint, Lk is the loss function. Contact-rich planning is hard to solve. The growth of possible contact sequences is exponential in the planning horizon. Additionally, the problem involves nonlinear dynamics and non-convex geometric constraints. In this paper, we asked the question, is there a way to solve contact-rich planning to near global optimality efficiently? A promising candidate is the so-called moment and sums of squares hierarchy, a general recipe to tightly relax a polynomial optimization problem, POP, to a convex semi-definite program, SCP. 2 challenges appear when applying the moment SOS hierarchy to contact-rich planning. If you use first-order relaxation, it is far from tight. If you use second-order dense relaxation, then the size of the SCP quickly grows intractable for practical examples. The key contribution of our paper is to show that contact-rich planning is also sparsity-rich. We introduced 2 general sparsity patterns, correlative sparsity pattern, CSP, and term sparsity pattern, TSP. Together, they exploit both variable level and term level sparsity patterns in the POP. For example, the construction of a correlative sparsity pattern involves 3 steps. First, we construct CSP graph. Its nodes indicate polynomial variables, and each edge indicates 2 variables are either in the same constraint or in the same term of the objective. Second, we perform caudal extension. We implement 2 efficient heuristics for caudal extension, the minimum degree heuristic and the minimum edge filling heuristic. In the third step, we find the maximal cliques in the caudal graph and regroup the variables. For example, in this picture, V1, V2, V3 form a clique. With correlative sparsity, instead of a large, dense SCP, now what we have is a sparse SCP with many but small positive semi-infinite blocks, as shown in this picture. For term sparsity, we have a similar three-step recipe. We just need to change from manipulating variables to manipulating monomials. With term sparsity, we can further decompose the PSD block inside each variable clique. So putting everything together, we introduce Spot, a lightweight and high-performance sparse polynomialization toolbox written in C++ with both MATLAB and Python interfaces. Given a POP defined by the user, we construct its sparsity graphs and find the maximal cliques. This step is fully automatic. To further exploit robotics-specific sparsity patterns, such as the Markovian sparsity and kinematic chain sparsity, Spot also allows the user to manually pass their own sparsity patterns. We test Spot on 5 contact-rich planning tasks. For the conversion time, we compare Spot with TSOS, Julia sparse POP package. Spot achieves over 10 times speed up for large-scale problems. For the SCP solving time, we test all examples with different sparsity options. By exploiting sparsity more aggressively, we reduce the solving time, but we sacrifice tightness of relaxation. So there's a trade-off. Here's the animation of our numerical results. All contact-rich trajectories are solved to near global optimality. We implemented Spot in the real-world push-T task using model predictive control. Here we solve each planning step to global optimality in near real time, about 2 to 3 seconds. The experiment had a 100% success rate, even in the presence of severe model mismatches. Finally, we want to emphasize that Spot, as a general-purpose sparse POP package, can solve problems beyond contact-rich planning. Here we demonstrate how to use Spot to solve the outlier robust WABA problem from computer vision using Python. After importing all the modules and data, we define polynomial variables, constraints, and the objective. Calling Spot can be done in less than 10 lines. After solving the SCP, we can extract solutions in the end. In addition to Spot, we recently released cuADMM, a general-purpose CUDA-accelerated ADMM solver that is particularly suitable for solving these sparse SCPs. Try Spot and cuADMM and let us know how it works. We have many exciting things to come about cuADMM. If you're interested, catch me at the poster session. Thank you very much.
All right, we have time for questions. Ground floor on the right.
Thank you for your talk. So it is the case that the call graphs allow you to solve for the max click problem efficiently, but there's a larger class of graphs which are the perfect graphs. The caudal graphs are a strict subset of those. So I wonder if the claim here is that the sparsity that you see in contact always naturally matches the caudal case when you have caudalized, or whether you've looked at the sort of broader class of perfect graphs.
So that's a great question. So I think so the reason for performing caudal extension is to make sure that when we find the maximal cliques, we can solve it in linear time. However, sparsity here is sort of like manipulating the layers of a neural network. So it can be quite heuristic. So for example, even if you don't do caudal graph, even if you don't do caudal extension, you can still find maximal cliques using some parallel maximum clique solvers. In such cases, it's not guaranteed that this sparsity is better than the other sparsity. So there's a lot of room to exploit about how to exploit these sparsities, even from users' domain expertise. So that's why we sort of allow the user to define these things on their own.
Thank you.
All right, let's thank the speaker again.
The next paper is on the surprising robustness of sequential convex optimization for contact implicit motion planning, and the speaker is Haoyu Han.
Hi, everyone. My name is Haoyu. Today, I'm going to present our paper on the surprising robustness of sequential convex optimization for contact implicit motion planning. Contact-rich planning is crucial when the robot frequently makes contact with the physical environment. Hybrid MPC, a most popular planning paradigm, combines predefined contact sequence with online model predictive control. We are offering real-time performance. Hybrid MPC often fail in the presence of unexpected contact and cannot discover novel contact modes. Contact implicit planning is an alternative paradigm that jointly optimizes the contact sequence. It embeds the contact sequence into a complementarity constraint. As you can see in this cube folding example, the contact force is non-zero only when the cube is in contact with the ground. This problem is called mathematical programming with complementarity constraints. Although being a continuous optimization problem, MPCC is notoriously hard to solve because of the failure of common constraint qualifications. Popular nonlinear programming solvers like IPOBT and SNOP can become brittle in the absence of CQs. The key issue is that they seek for a primal dual pair that satisfies the KT system. Well, this only makes sense when CQs holds. This simple example shows that the local geometry of the feasible set failed to align with its algebraic description if CQ fails. And our main contribution is to introduce CRISP, a high-performance numerical solver that can robustly solve the contact implicit motion planning. The key idea is quite straightforward. Instead of seeking for primal dual pairs, how about we just compute a primal solution? We develop CRISP with 3 key features. The first is we approximate the cost function using a quadratic model, and we linearize the constraints. This has 2 benefits. So first, the hashing is often a constant, so it's more stable. And second, the subproblem is a convex problem, so it is easy to solve. And we further bring the constraints to the cost function as a L1 penalty, and we add the trust region to ensure convergence. In addition to proposing an algorithm, our paper contributes a new theory shedding insights on the convergence behavior of CRISP. We build the relationship between original MPCC and the Murray function, particularly assuming convexity of the cost function. Under technical conditions, CRISP guarantee converges to a first-order critical point of the Murray function. If, in addition, the point is locally optimal for the Murray function and is feasible to the original MPCC, then it is a local minimizer of the MPCC. We benchmark CRISP in multiple models. They are all contact models that need to switch the contact sequence, and we test them always in naive initial guess that either a constant or interpolation trajectory between the initial and the target. Here we show the result table. So first, CRISP achieved a 100% successful rate in all models, and where other solvers can be brittle. Second, CRISP reached the target with tiny error, and third, CRISP is fast that it can solve hard problems within seconds. We also show the box plot that you can see CRISP has the lowest objective value and the tracking error, where all the cases constraint violation is below 10 power to minus 6. And here we show the realization. This is a card pole with soft wall, and we want to swing up the pendulum. I want to highlight that the left below one, the algorithm uses contact to swing up the pendulum. And also this another example involves friction. There are 2 blocks stacking together, and the highlighted one pushed back and forth to make it to the target position. And this waiter problem, which we want to pull out the plate using an orange cube. And we show the robustness of our method in a real-world experiment, push-D task. We want to push a T-shaped block to the target position. We recently have integrated CRISP into Pinocchio and successfully generated a running motion of a half theta. Try CRISP on your own robot now. Thank you very much.
We have time for a question. Well, if there are no questions, I'll ask one question. So it seems like you turned everything into a kind of standard nonlinear program and then converted it into your first order, your primal problem. But it didn't seem like there was anything specific about contact in that formulation. Is there something about the conditions of contact and complementarity that you're exploiting in order to make this work?
Okay, so I think our motivation from the absence of CQs. So because of the absence of CQs, that this primal dual method, they may fail. So we seek to find a primal solution. But the solver itself can deal with any like a general nonlinear programming solvers. It does not stick to the like MPCC problem.
Okay, thank you. Well, let's thank the speaker one more time.
So for the next talk, we are going to see the recording of a talk because unfortunately the authors couldn't be here in person, and as such we will not have any Q&A afterwards. So next talk is going to be effective sampling for robot motion planning through the lens of lattices.
Can we get the audio up? Okay, due to the technical difficulties, we'll skip this presentation and move on to the next talk, which is efficient hierarchical any-angle path planning on multi-resolution grids, presented by Victor Regwart.
Hi, welcome to my presentation. I'm Victor Regwart, and today I'll be introducing WaveStar, which is an efficient global planner that uses multi-resolution. I completed this work as part of my PhD at ETH Zurich, and have since started working at the Robotics and AI Institute. The motivation to work on global planning is that it's applicable to a wide range of robotics problems, since we often need robots to move between different points of interest that might be far apart. In this presentation specifically, we'll be looking at Euclidean shortest path finding from a point A to a point B, where we don't want collisions with the obstacles in the environment as represented by 3D map. A wide range of solutions exist to global path planning, which can be broken down in 3 different families of approaches. The first of which are optimization-based, which find very high-quality, smooth solutions, but are inherently local. So they need a good initial guess in order to converge. Such an initial guess is often found, for example, by sampling-based planners, which are very efficient and scale well, but do not provide any guarantees if they're only given a finite amount of time to find a solution. In contrast, search-based methods come with many nice guarantees, including finite time completeness and optimality, and also explicitly detect when no solution exists in the search space. But they scale very poorly, as their computational cost is at best linear in a number of explored cells. In volumetric mapping research, we've seen that very large environments can efficiently be represented using a small number of multi-resolution cells. And therefore, in this work, we had the question of whether we can also use multi-resolution to efficiently and accurately perform search-based planning. So one way to do this would be to run a standard search-based planner, such as A*, over the center points of this multi-resolution grid. But this unfortunately finds very long and jagged paths that are very different from true Euclidean shortest paths. Euclidean shortest paths have the property that they must be taut, which means that they only consist of straight line segments and inflection points which are always on the borders of obstacles. So going back to this idea of taut paths, we propose a special initialization procedure that pads all of the obstacles with high-resolution cells and therefore explicitly guarantees that all potentially optimal inflection points will be considered. We then run an any-angle path planning approach, which is very similar to A*, but in addition to connecting each cell to its neighbors, it also tries to connect to the neighbor's predecessors. This allows it to diagonally cut across the grid and find paths that are much closer to true Euclidean shortest paths. In addition to these two steps in the paper, we also introduce a dynamic resolution refinement procedure to further improve the accuracy of the solutions. Looking at some qualitative evaluations, we compare our methods to a range of both sampling-based and search-based methods, including RT-Connect, RT-star, A-star, and theta-star, which is a fixed resolution any-angle planner, and then Octree theta-star, which generalizes that to multi-resolution. And finally, we show our method here in green, but it's very difficult to see because the solutions are almost identical to those of theta-star. Looking at this more quantitatively, we here compare the path lengths of the solutions of all the different planners relative to theta-star, and we see that theta-star finds, in general, extremely good paths. If we increase the time budget for the sampling-based approaches, you can see that they get closer to theta-star, but they don't quite get there. In contrast, our method finds paths that are almost indistinguishable of theta-star solutions. Now looking at the runtime of all the different planners, we again compare it to the runtimes of theta-star, and here we see that our method outperforms all of the search-based methods and performs well even if you compare it to a sampling-based method. So in conclusion, we presented WaveStar, which is a very accurate and efficient search-based planner, which maintains all of the nice properties and guarantees of A-star, including finite time completeness and optimality, and the ability to detect whether a solution even exists in finite time. All of the work presented here is available as open source, and I really much look forward to your questions. Thank you so much for listening.
Questions? One in the front down here.
Thank you very much. Very cool work. I'm curious if there's any connections to jump point search. Can you skip adding nodes in the tree in a similar way?
So unfortunately, I'm not familiar with jump point search, but we generally don't skip any connections because it's a dense method. So we'll really find a solution through the entire volume, and that's why the speed up is so big from the multi-resolution. I would love to discuss it more at the poster.
Yeah, we can discuss offline. Thank you.
Okay, great. Thank you.
We have time for one more question, also down here in the front.
Thanks for the talk. I think the optimality, does it depends on how you partition the space? Or?
So that's a really good question. So the optimality bounds that we find are that it will not be worse than the solutions of A-star by some margin. However, the solutions that we find in general are about 13% shorter than those of A-star because we have these diagonal connections across the grid. The partitioning we have in the space is like an octree. So it's not flexible in our implementation, but this could be changed, of course.
Okay, thank you.
Thanks.
All right, let's thank the speaker one more time.
All right, next we have differentiable GPU parallelized task and motion planning by William Shen.
I'm William, a PhD student at MIT, and I'll be presenting our joint work with NVIDIA on differentiable GPU parallelized task and motion planning. So let's consider this problem where we want to pack all the free objects onto the box. So we want to go from raw perception to a complete long horizon plan, including graphs, placements, and trajectories in just a few seconds. And for learning-based approaches, this is very difficult because of the long horizon dependencies and complex constraints. So we model this as task and motion planning, or TAMP, which requires reasoning over high-level discrete actions like pick and place, and low-level continuous parameters like graphs, placements, and trajectories. So sampling-based methods rely on trial and error and really struggle to scale due to the single-threaded nature, while optimization-based methods are sensitive to initialization and local minima. Our goal is to solve these highly constrained, non-convex, difficult TAMP problems in just seconds. And we introduce QTAMP, which is our approach for differentiable GPU parallelized TAMP. We're going to combine the global exploration properties of sampling with the local refinement behavior of optimization at scale. We use parallel compositional sampling to populate candidate particles near the solution manifold, and then we're going to use differentiable optimization to explore thousands of these candidate solutions simultaneously. So let's have a look at how QTAMP works on this highly constrained packing problem. So the first thing we're going to do is have a search over plan skeletons, which are sequences of discrete actions like pick, place, and move. So each skeleton defines continuous parameters like grass placements and configurations. And we're going to sample initializations for these, what we call particles. So you can see at time step 0, these particles are unsatisfying because of collision and kinematic constraints. And each plan skeleton also defines constraints and plan costs, which define cost functions, which we can evaluate over all the particles in parallel, and then use gradient-based optimization to update them. OK, so how can we initialize the particles in the first place? So each plan skeleton defines what we call a constraint network, where the variables are connected to the constraints. And what we want to do is initialize them so they are a good start for the optimizer. So we're going to, similar to sampling-based TAMP, use samplers that solve subgraphs of the constraint network. So here's an example of a graph sampler that samples graphs for a red object. We can take these samples and then feed them to a conditional sampler that uses inverse kinematics to find robot configurations. And by composing these generations for all these different samplers, what we get is full initializations for all the continuous parameters. And because we're using sampling, QTAMP remains probabilistically complete. OK, so we've initialized these particles, but one crucial thing now is they may not satisfy all the hard constraints in our TAMP problem. So these are things like grass, kinematic, collisions. In addition, we might want to also optimize for soft costs, such as trajectory length. So we treat this as a continuous constraint satisfaction problem, which we solve with unconstrained optimization. And what we're going to do is we're going to minimize a weighted sum between the hard constraint costs and the soft action costs. And to really scale up, we're going to parallelize this and optimize a batch of particles all at the same time on the GPU. And through the nature of scale, we're going to have a higher chance of finding a feasible solution in the first place. So if we have a look at optimization for this packing problem, you can see just within a few seconds, we can find a solution. So now let's have a look at the simpler problem of packing two non-convex objects. So QTAMP, which combines optimization with sampling, significantly outperforms the baselines which use optimization or sampling alone. So QTAMP here, as we increase the batch size, we also improve the solution time. Let's revisit this packing problem with 5 objects again, which is very highly constrained. And what we saw was that sampling alone fails completely, whereas QTAMP and a variant of QTAMP, where we automatically tune the cost weights, become increasingly robust as we increase the batch size. And another nice property of using GPUs is if we scale up to 1024 particles, there's no increase in the wall clock time. So that's a pretty nice property to have as well. OK, so to summarize, QTAMP scales task and motion planning via GPU parallelized sampling optimization. We use our structured particle initialization to improve robustness and convergence speed. And all in all, this produces high-quality TAMP plans and solves difficult TAMP problems in just seconds. Great, thank you.
OK, so we have time for a question from the audience.
Yeah, thank you for your great talk. And my question, basically, I have 2 questions. The first is, what is the description format? Is it compatible to like PDDL stream? And the second question is that does this method require like prior knowledge of the models of the objects? Thank you.
Right, so on the first question of what kind of model we use, so I think it's very similar to PDDL. We have a task planning search, where it's essentially some sort of breadth-first search, and we generate essentially task plans. So it's similar to PDDL stream in that regard. And in terms of a second question on object models, yes, we do need object models. So we take the object model, we then convert it to a collision representation, and use that for collision checking as well.
Okay, thank you.
We have time for a quick question. OK, so just one quick question for you. Can you comment on the frequency with which you can run this algorithm, whether it's a real-time algorithm?
So I think we're not really focusing on the real-time aspect. I think it would be interesting to be able to, say, generate an initial solution and online keep replanning. But I think at this stage, for these very difficult problems, it takes on the order of like maybe up to 5 seconds in the real world to plan. But I think it's an exciting direction to see how we can incorporate the replanning aspect.
Thank you. Let's thank the speaker again.
Our Our next talk is Flow Matching Ergodic Coverage, and the presenter will be Max Muchin-Sun.
Hi, my name is Max, and I'm here to present our work, Flow Matching Ergodic Coverage. So coverage-based motion planning has played an important role in many robotics problems, including autonomous exploration, manipulation, and embodied learning. In this work, we formulate coverage-based motion planning as a statistical inference problem that's also known as ergodic coverage. Our goal is to synthesize the spatial distribution of the robot's trajectory with respect to a target distribution. In other words, we view coverage as a sampling process with the robot's trajectory being the samples. To solve this problem, we combine flow-based inference with model-based optimal control. Flow-based inference is a technique widely used in generative models for sample generation. Here's how it works. Given a set of samples from an initial distribution, such as a Gaussian, flow-based inference will construct a time-dependent vector field to continuously transform the samples toward the target distribution. This flow vector field can be constructed analytically, such as through formulations such as optimal transport, and it can also be learned as a neural network through flow matching, which is a supervised learning method that align the learned vector field with the analytical vector field as a reference. So if we view the robot's trajectory as a set of samples, can we directly transform it by following the reference vector field? Unfortunately, the answer is no. The robot trajectory is constrained by its dynamics, and we have to incorporate such constraints into the flow vector field to avoid dynamically infeasible results. To overcome this issue, in this work, we construct the flow vector field in the control space of the robot. This ensures dynamically feasible results. And we can optimize the control space flow to match with the analytical reference flow in a state space. As a key contribution of our paper, we show that this control space flow matching problem is simply the same as an LQR problem, which means it can be solved in closed form using the Riccardi equation. As you can see here, the optimized flow can closely match the reference flow while still preserving the robot's dynamics. We name our method LQ flow matching, and our method enables online real-time flow matching on nonlinear systems with minimum computational overhead. It can also be massively accelerated on GPUs for large-scale and long-horizon coverage problems. Furthermore, our methods can benefit from advanced formulations of the reference flows from generative models. In particular, in this work, we show that we can use the Stein variational gradient flow for covering of learning-based target distributions, and we can use the optimal transport-based Sinkhorn divergence flow to improve coverage of point clouds, as you can see here. Lastly, we demonstrate our methods on a Franka robot through a series of drawing and erasing experiments, including an online vision-based erasing task, as you can see here. The robot here repeatedly takes an overhead photo of the whiteboard as a target distribution and plans a long horizon coverage trajectory for erasing the drawings. New drawings are being added during the erasing process, and the robot is able to react in real time to successfully complete the task. And I will let the video finish. And I missed one spot there. It will eventually get there. Here we go. You can find the paper code and more videos on our project website. Please come visit my poster, and I'm happy to answer your questions and also hear about postdoc opportunities if you're hiring. Thank you.
All right, very good. Questions? Okay, well, in the interest of time, maybe we can try just moving on to the next one. Thank you very much again. Let's thank the speaker one more time. And we are going to try to play that video once again, and we'll cross our fingers and hope we have audio. If, yeah, let's see how it goes.
Thank you.
And we lost this video too.
Hello everyone, my name is Kirill Solovey, and I'm happy to present the work I did together with my student Itai Panasov, titled Effective Sampling for Robot Motion Planning Through the Lens of Lattices. So in this work, we take a closer look at the most basic ingredient in all of our sampling-based planners, namely the samples themselves. And our broad goal is to improve the performance and strengthen the theoretical guarantees of sampling-based planners by developing better sampling methods. Nowadays, most of the approaches rely on either uniform random sampling, which is very easy to implement, but has very poor asymptotic guarantees. Some people are using deterministic samples, such as grid samples or Halton sequences, but those, although they do have slightly better theoretical understanding and guarantees, they still don't perform as well when you compare it to uniform random sampling. So in this work, we get inspired by the vast body of literature on lattices. And we take a closer look at lattices and exploit the structure of lattices, which are essentially regularly structured assembles of points in space to develop from them good sampling distributions. There are a lot of theoretical properties known about lattices, and we are specifically interested in lattices that have good coverage properties. That is, they provide coverage of space with a few number of points. So in our work, we develop a theoretical framework that allows us to convert lattices into good sample sets that endow the underlying motion planners with strong deterministic optimality guarantees. And the resulting sample sets can be used in many sampling-based planners, such as PRM star, FMT star, beat star, so on and so forth, and including in sample-based planners that you are yourself developing and using. So what are the practical implications of our approach? We show that using the best sample sets that we develop from lattices, we can significantly improve the performance of existing sampling-based planners. And we demonstrate this claim on a variety of scenarios, including 6 degrees of freedom manipulator, as well as multi-robot systems. And we show that using our best lattice-based sample sets, we can speed up the performance of the underlying algorithm by as much as 10 times to even 100 times compared to previous deterministic or randomized sampling methods. Okay, so to summarize, our work provides deep theoretical insights into the performance and structure of sampling-based planners, while also significantly improving their practical performance and allowing to solve more challenging high-dimensional problems than before. We provide all of our implementation, including the construction of the lattices and the algorithms that we use in a GitHub repository, where you can find an OMPL-based and a VAMP-based implementation. Other than that, we're currently working on a few exciting future directions, which include an anytime adaptive sampling adaptation of our current sampling distributions, extensions to non-Euclidean systems, and kedodynamic planning. So that said, I thank you for your attention, and I look forward to interact with you during the poster session. Thanks.
I don't know how successful that interaction will be, but the poster session is now until 2 o'clock. We also have lunch, and all of the posters from the morning sessions will be present in the back here. Thank you.
Hi everyone, welcome to the session 6, Manipulation 1. We are going to get started. I'm Roberto Martin from UT Austin.
And I'm the session co-chair, Yunzhu Li from Columbia.
We are going to get started with our first paper, Reactive Diffusion Policy, Slow, Fast, Visual Tactile Policy, Learning for Contact-Rich Manipulation, with presenter Han Xu.
Today, I will introduce Reactive Diffusion Policy, an imitative learning framework for contact-rich manipulation. For humans, vision and touch are crucial for complex tasks. So how to enable robots to utilize vision and touch? For the hardware, we need RGB cameras and tactile or force sensors. Next, let's step into the learning algorithm. So let's think about how do we do this task. We don't predict precise commands, but we can do this contact-rich task with high precision and flexibility. So what is the key to this mystery? So let's imagine that we are trying to grab a mug. First, we will plan a cross action, for example, approaching the mug and closing the fingers. Once we make contact, we will have a fast correction phase. We fine-tune our finger positions based on tactile feedbacks. So how do we let robots to master this? On the one side, we have visual imitative learning, like diffusion policy. They rely on action chunking to reduce accumulated errors and improve consistency. So they usually have a slow updating frequency. On the other side, we have force controllers. They can correct actions at a very high frequency, but they usually need accurate dynamics model or need manual parameter tuning. So can we combine the advantages in one unified framework? We propose RDP, use the slow policy as a neural planner and the fast policy as a learnable controller. Here is the key idea of RDP. The slow policy predicts complex latent actions by diffusion for modeling complexity. And the fast policy learns quick reaction based on tactile or force feedback for reactivity. During training, we use an asymmetric tokenizer as the fast policy. It encodes actions into latent space and decodes actions based on recent tactile feedbacks. The slow policy will use the latent action chunk for diffusion training. During inference, the slow policy will predict coarse latent actions, and the fast policy will decode actions based on recent feedback at high frequency in a closed-loop way. So we still need to collect visual tactile data with reactive behavior. So we design a teleoperation system called TACT-AR with tactile or force feedback. It can provide real-time tactile feedback in AR visualization for different sensors. Here are two example tasks. We can see that visual feedback can help the user to control the contact forces more precisely. TACT-AR can provide real-time tactile or force feedback, and it can be easily deployed with different sensors and robots, and it has very low cost. Now we have data. Let's see what reactivity of our RDP can bring us. In this task, the human tries to move down the cucumber during contact, but RDP can still track the surface during perturbation. Next, let's try a harder task with curved surface and rotation variations. The human is trying to rotate the vase, but we can see RDP can still handle this task. In this lifting task, RDP can perform precise force control and lift the paper cup without squeezing it. Note that we remove the cup verge to increase task difficulty. So RDP can perform tasks that require precision, precise force control, and robustness to perturbations. It also has large performance improvement over baselines and is applicable to different sensors. We also perform a user study on text AI and find that it can improve data quality and policy performance. Our code are fully open source now. Please see our website for more details. So that's it for RDP. We hope our work can make very tactile manipulation with context-rich tasks more practical and accessible. Thank you.
Let's go into some questions. Okay, I don't see any hand. Right, ground floor, left.
Hi, thank you for the great talk. Very cool work. I have a question about the ideal granularity of open-loop, closed-loop operations. So in your work, it looks like the the low-level policy is made closed-loop and reactive, whereas the high-level chunk-based policy is still open-loop. So how important do you think it is for the high-level policy also become more reactive? And do you have any thoughts on how to potentially achieve this?
Let me repeat that question. So you're asking that how do the high-level policy be more closed loop?
Yep, yeah,
okay.
More reactive.
So in our RDP, we mainly use the fast policy for the closed loop control part. But if you want the high-level policy more closed loop, maybe you can introduce some kind of impeding techniques. For example, you can make the action chunks, the transition more smoother. Yeah. So maybe in that way we can have better closed loop control for the high-level policy. Yeah.
That's all the time we have for the questions. Let's thank Han again for his great presentation.
Okay, thank you.
Next, we will have Lu Jie. Her presentation will be about physics-driven data generations for context-rich manipulation via trajectory optimization.
Hi, everyone. I'm Lu Jie. I'm excited to present our work on data generation for context-rich manipulation. Robot foundation models have shown great promise in dexterous manipulation. However, collecting diverse and high-quality data set remains a major challenge for robotics, especially for context-rich tasks. In this project, we introduce a low-cost data generation pipeline that uses trajectory optimization to augment a small number of human demonstrations to a distribution of tasks. Human demonstrations offer valuable global information for solving long-horizon multi-contact tasks, but can be costly and difficult to collect. Trajectory optimization has demonstrated success in generating locally optimal trajectories for context-rich tasks, but they often rely on global guidance in the form of good initial guesses. In this project, we leverage the strengths of both approaches to generate a large, high-quality, context-rich datasets that generalizes across varying embodiments, physical parameters, and initial states. Starting from a small number of human demonstrations collected in a virtual reality simulation environment, the pipeline refines these demonstrations using optimization-based kinematic retargeting and trajectory optimization to adapt them across various robot embodiments and physical parameters. This process yields a diverse, physically consistent dataset that enables cross-embodiment data transfer and training robust policies that achieve high success rate in sim-to-real hardware deployment on bimanual EWA arms. Our automated data collection pipeline consists of a human demonstration interface in virtual reality, which allows for fast and cost-effective demonstration collection compared to traditional teleoperation systems. It takes approximately 7 minutes to collect 24 long-horizon demos for each system. After collecting human demonstrations in VR, we kinematically retarget these trajectories to the specific robot embodiment in simulation. The kinematically feasible robot trajectories are generally not dynamically feasible due to the embodiment gap and differences in physical parameters. We use trajectory optimization to locally refine them to obey dynamical constraints. Thanks to access to the dynamics, we can locally perturb the physical parameters as well as robot and object states around a nominal demonstration. allowing us to solve the trajectory optimization program on a distribution of tasks using a single nominal demonstration. Here, the left column visualizes the human demonstration in VR. The middle column shows the kinematic replay, which often fails the task, and the right column demonstrates the dynamical feasible trajectories after trajectory optimization. Notice that both the EWA and Panda arms can leverage the same human demonstration to achieve the manipulation task. While kinematic retargeting of demonstrations might suffice to generate data for simpler manipulation tasks such as pick and place, trajectory optimization is crucial for generating dynamic feasibility for contact-rich tasks. Trajectory optimization is also crucial for generating diverse trajectories. It efficiently augments a small set of demonstrations to a wide distribution of trajectories with locally perturbed physical parameters and initial conditions. We validate our approach by training behavior cloning policies on the generated dataset. The baseline policy trained on 24 original human demonstrations easily encounters out-of-distribution states and fails the task. In contrast, the policy trained on 500 generated trajectories is much more robust. Even after initial misses, it persistently attempts to re-establish contact with the object and ultimately completes the task successfully. We further deploy the train policy directly on hardware using fixed-base bimanual KUKA EWA arms without any real-world fine-tuning. The arms performed a sequence of coordinated rolling, pitching, and yawing actions to reorient the box to the goalpost. This is a long-horizon, whole-body manipulation task that is especially challenging. It requires the robots to frequently make and break contact with the object and demands precise control. Small positional errors can result in missed contacts, which will in turn lead to task failure. So the policy must be both robust and accurate. That concludes my talk, and I'm happy to take any questions.
Now have time for questions. The ground floor. In the middle.
Thanks for the great talk. It seems that simulation is an essential part of your pipeline. And I wonder, how can we apply your method to large-scale real-world data collection?
That's a great question. So right now, we rely on the high-fidelity contact model of Drake. But I think in the long run, we might be able to do real-to-sim to build like a realistic simulation of the world, and then do sim to real to transfer into the real world. So yes, my pipeline is essentially relies on a high-fidelity simulator. But later, we might be able to learn a word model so that we can do planning on a latent state.
Thank you.
We have time for another quick questions. The ground floor on the right. The right. Sorry, your left.
Hi, that was a great talk. I noticed on your website that you haven't released the code yet. Are you planning to release it soon?
We're working towards it. Stay tuned.
Okay. And so do you think it's easily transferable to other simulators, or do you think it would take a lot of changes to make that happen?
Yes, of course. It's directly applicable to any simulators. So right now, I'm actually working on developing the Majorco pipeline for manipulation, locomotion, and local manipulation as a general pipeline. So keep updated. We'll keep you updated.
Okay. All right. Thank you.
Let's thank again our speaker. And let's welcome Jae-Jun Lee, who's going to present Vitascope, visual tactile implicit representation for in-hand pose and extrinsic contact estimation.
Hi everyone, I'm Jae-Jun. Today I'll present Vitascope, visual tactile implicit representation for in-hand pose and extrinsic contact estimation. So we're interested in this problem of estimating the extrinsic contact between the grasped object and the environment. However, relying on a single sensory modality has a number of challenges. For example, vision suffers from occlusions and tactile feedback is local, which means that you need some global context such as in-hand object pose and 3D geometry to give more information. So the question is, how do we leverage the complementary nature of visual tactile feedback to infer extrinsic contacts? More specifically, how do we learn an object representation to enable a joint reasoning of 3D geometry, in-and pose, and extrinsic contacts from vision and touch. Here's an overview of Vitascope, visual tactile simultaneous contact and object pose estimation. Given an extrinsic contact event, we take multisensory feedback, such as partial point cloud from vision and touch, and tactile shear feedback from the tactile sensors. Then, Vitascope runs inference in 2 stages. We first estimate the in-and object pose, then we estimate the extrinsic contact. We call this contact-aware visual tactile 3D object representation, and it's trained entirely in simulation. On the left side, we show a sample environment of the simulation environment with the tactile feedback, and on the right, we show the tactile real-world environment. And I'll briefly introduce the model architecture. Vitascope has 3 implicit field modules: object, tactile, and contact. The object module represents the 3D geometry as a signed distance field, and we test on 6 different geometries with increasing tooltip complexity. Next, we represent the tactile shear feedback as a tactile vector field contextualized by the in-and object pose, latent, and a contact configuration latent code. And we assume that the tactile shear feedback is a great way to characterize extrinsic contact configuration. Lastly, we have the contact field, which predicts the contact probability for a given 3D query point, such that we can register 3D extrinsic contact patch onto the 3D geometry. So how do we train Vitascope? We scale up visual tactile data in simulation. So we use Taxol framework from NVIDIA, where we sample extrinsic contacts, and then we collect the visual tactile feedback from it. And for the inference pipeline, it's split into 2 stages. We use the object module to do pose estimation. And because the object module is trained to take query points from the object canonical pose from the normalized geometry, we factor this out into the object pose and the query points from the real-world visual tactile partial point cloud observations. Then we run the inference via optimization, where we minimize the surface distance loss to infer the in-and object pose. Next, given this in-and object pose latent, we infer the extrinsic contact configuration latent by minimizing the mean squared error shear vector loss from the tactile shear feedback. And then lastly, we run the full inference using the contact field contextualized by the in-and object pose latent and the contact latent to predict the extrinsic contact patch. And here we visualize the 0 shots immaterial transfer results. In blue, we show the ground truth, and in red, we show the prediction. And we can see that our method can successfully transfer to the real world. For more details, please visit our poster at number 6, and thank you for your attention.
We have time for questions. Do you see here on the floor? First row on the floor.
Thank you for the talk. You mentioned there is a separate SDF module and a contact probability module. I wonder how they differ and whether you can unify them to have a single way of estimating shape and predicting contact.
So they serve a different purpose. The object module learns the 3D geometry, which is a common thing in this field. And the contact field is, we use that to predict the contact patch. So I don't think it's easy to combine them together, because they're learning an implicit function, so each module has a different purpose. Cool.
Any other questions? I'm going to have a quick question here. Is convexity of the shapes a prerequisite for your model? Are you able also to infer when there is not enough information to know if it's concave?
Oh, that's a very good question. We're currently limited to the convex shapes, so that would be a great direction to take. Yes.
All right. Let's thank our speaker.
Thank you.
Yeah, let's thank the speaker again. Next, we'll have Joe Hume. He will be presenting a low-cost and lightweight 6-off bimanual arm for dynamic and context-rich manipulation. Please.
Hi, I'm Jaeyoung Kim from Kai's Huge Lab, and I'll present today a low-cost and lightweight 6 degrees of freedom bimanual arm for dynamic and context-rich manipulation. We want our robot to throw boxes and hammer nails and perform other dynamic and context-rich tasks. But most research robots are not made for that. They're too careful, too stiff, and too expensive to crash. They're often moved very slowly or shut down unexpectedly and difficult to repair after impacts. And I think the most biggest reason is in hardware. So they use high ratio harmonic gear, which is very stiff, and they use torque sensors, and it is very vulnerable to impacts and very expensive. And also, every actuator is attached to every joint, so it makes inertia very high. So that's why we made Armada, an open source, affordable robot for manipulation and dynamic actions. It costs around $3,000 for each arm, and everything is open source, including CAD models, URDF, learning codes, simulation, and assemblies in this link. To solve the stiffness issue, we use QDD actuator, which uses low gear ratio planetary gears. So it has more backlash, but has higher compliance, and so it absorbs external impacts. Since its friction is low, so we could use torque control via current sensing and omitting the use of vulnerable torque sensors. And to reduce the moving mass, we attach 4 heavy actuators to the body. So the torque for elbow joint is transmitted from the body by using 4-bar parallelogram linkage system. So by adding 2 small actuators for the wrist, we have 6 degrees of freedom per arm. So we want to make our arm light, cheap, and easy to repair. So most parts are made of 3D printed PLAs, but PLA is known for not enough rigidity, so we use aluminum material for high-stress areas like this part, black parts, so that we can reduce the deformation. And also we implemented simple 1 degrees of freedom gripper with 1 servo and a flexible 3D printed TPU finger. So it is also open source and easy to be assembled. And Armada's end effector can achieve 6.2 meters per second end effector velocity, which is faster than most collaborate robots. And despite its speed, even at its fast speed, its collision force is lower than a human palm strike. So it is fast, but still safe. And it can handle up to 2.5 kilograms, so by following how a human really lifts. But its repeatability is 2.6 millimeters, so it's less precise, and it shows the trade-off relationship between having high compliant joint and precision. To show the capability of dynamic tasks, with this swiftly grasp and throw the object into a basket, and we succeed on every object except the most heaviest one. This is slow motion video. And to show the robustness on frequent contact, so we did hammering, and it can drive nail into wood, similar on how really human does. And we also hit the ping pong balls more than 3.5 meters. Since many guys want to do the learning-based manipulation, we also did RL sim to real task. So our goal is to put the object over a bump into a desired pose. And we also achieved 80% zero-shot success rate in the real world. Also, to utilize the large-scale human motion data set, we did human motion retargeting. So by using single RGB camera, we track the human joint motion and retarget it to our robot and just throw the boxes, like as you can see here. Cool, isn't it? Yeah. So this is it, and thank you for listening. And if you want to talk more, then please visit poster number 8, not 55. Thank you.
Oh, there's a questions on the ground floor.
Yeah. Since you gave up repeatability on the polls side, are there special policies that you need to train that's different from a more precise robot? And if so, how do you tackle that?
I think it would be harsher domain randomization might help, but I think there's not many things we can do. Maybe we can try some like ACT, like how Aloha did. So maybe trying that kind of method might help with dealing with this kind of low precise hardware.
We have time for one more quick question. There's a question on the ground floor on the and in the middle on the left.
Hi, thank you for the talk. I was wondering about the hardware reliability. Namely, you wanted to keep the hardware cost low by using PLA, but you are also attaching motors directly to it. I was wondering on especially extended deployments, do you find that the PLA often melts and does that degrade the precision further? Thank you.
Yeah, actually using PLA is it has a good thing because we can repair very easily, but it also makes the repeatability and precision very bad. So if we can do aluminum machining very easily and cheap, then it would be the best solution. But as far, I think there is not a best solution as far as I know. So.
All right, let's thank our speaker again.
Thank you.
Let's introduce our next speaker, Beilin, who is going to present PPTAG paper picking using omnidirectional tactile feedback in Dexter's robotic hands.
Okay, thank you. Good afternoon, everyone. I'm Pei Lin from Beijing Institute for General AI and Shanghai Tech University. It's a great honor to present our project named PPTAG, which focuses on picking up paper-like object by using tactile in a Dexter's hand. Okay. In this task, for vision-based method, paper-like objects do not have any grasp point and always have diverse appearance. It does not make sense if retraining was needed every time the pattern on the paper changes. So inspired by human, the cortex take vision for decision, and the grasping can be executed by cerebrum using tactile feedback, and without the need of the ongoing vision input. But we find that the existing flat-shaped tactile sensor can only perceive single direction, and the parallel gripper is really easy to exit its workspace. What we need is a Dexter hand with tactile and with a round tactile sensor. But the Dexter hand also faces many key challenges. One is a very non-negligible execution error, and another is the complex finger-wrist coupling dynamics. And another challenge lies on the efficiency to get data. So our system consists of three parts. First, we propose a round-shaped tactile sensor and mount them on the Dexter's hand. And second, we propose a new data generation method without any physical simulation. And third, we propose a robust policy with tactile feedback. We propose a new tactile sensor named RTAG, which is really easy to calibrate thanks to the monochrome design. And it achieves very accurate depth reconstruction. Thanks to the high resolution, we also achieve the sleep detection. The whole design has already been open sourced, and you can use it. And I also bring one here. Maybe you can try in our later session. The grasping strategy is inspired by human. By maintaining consistent finger contact force and avoiding slip, the fingers induce material buckling and create pinchable area. The press force can be presented by the deformation depth of fingertip, Once we sample the trajectory from random terrains, we can adjust the platforms by varying the fingertip to surface distance. And after we get the target trajectory, we can optimize the whole system state by gradient descent. And our aim, the policy is to predict next 5 frames by giving the prefix 5 frames. In each frame, it consists of proprioception, tactile information, and the target force. If the slip occurs during the grasping, the target force will be increased to avoid slip. And thanks to the encode-only transformer and without any input of vision, our whole system is really efficiency and achieve 30 Hertz control frequency. Here's our results. We successfully grasping different material from different terrains. And the policy is also robust in the wild. For example, we randomly place a book on the desk. Yeah. We also compare our method to the open loop and the parallel gripper to show the necessity to use tactile feedback and the dexterous hand. And we also compare a method of force checking by giving the race trajectory of PP tag. All of the comparisons show our PP tag is really robust. One limitation is that our strategy is not fitful for all the materials. For example, a mouse pad. And we also find that it's really important to set an initial target force. But I think the whole framework can be extended to other tasks. For example, rotating an orange or pinch rotate a bulb. Because the data we generated is expandable, we want to annotate them automatically. And maybe in the future, we want to merge all of the tasks together. I think manipulation is not only grasping, it's more diverse than grasping. Yeah, thank you.
Questions for our speaker? Here on the floor, left side.
Thanks for the very inspiring presentation. I wonder, have you ever explored the different tactile sensing technology? Is there any specific reason why you choose this vision-based tactile sensing?
Okay, thank you. Really good question. For this task, we just use the force and the slip. If there's any sensor can help me to get the force and the slip information, I think this is a good one. Because the slip is really, I think, really hard to be detected. For vision-based method, for vision-based sensor, if the slip occurs, you will find a wrinkle in the sensor, and it will be very obvious. So we use this vision-based sensor. Thank you.
Maybe another very quick ones in the middle. Please keep your question short.
If the slip isn't large enough to cause a wrinkle, can you not detect it? Or are you able to detect even very low levels of slip?
It depends on the force, I think. I bring one sensor here. Maybe you can try it later in the post session.
Yeah. Okay. Thank you.
Let's thank the speaker again for the great presentation.
Thank you.
Next, we'll have GeoDex, a unified geometric framework for tactile, dexterous, and extrinsic manipulation under force uncertainty. The presentation will be by Sadigh. Please.
Hi. We present GeoDex, a unified geometric framework for tactile, extrinsic, and dexterous manipulation under force uncertainty. Tactile sensors are playing an ever important role in dexterous manipulation. It allows the robot to manipulate objects without even with vision as input, or achieve precise tool manipulation, such as like twisting a screwdriver. However, tactile sensors are far from perfect. Most of the tactile sensors are pressure only, so they cannot provide 3D force information. And for those that can sense force informations, the force magnitude requires constant calibrations and still have errors. And also the materials that make the surface of tactile sensors are usually not uniform and not perfectly elastic. So hysteresis and errors will present. Previous works only use a small part of the information from the tactile sensor, for example, discretized into contact detection signals or contact direction vectors. So we study how can we utilize the tactile sensors for tasks that requires force controls, for example, grasping fragile object or pivoting object without sliding. So in our approach, we present GeoDex, a unified geometric framework that combining force planning, estimation, and control under force measurement uncertainties. The key insight is that under quasi-static assumptions, different tactile sensors at different fingertips should reach consensus with each other and underlying physics. We can perform both intrinsic and extrinsic dexterous manipulation using the framework. Let's take a geometric interpretation of the manipulation problems. So for all force that achieve contact, they are concatenated into a single force vector. And all force that can balance the object against gravity are lying on the hyperplane in the force space. We call this force equilibrium plane. However, not all force on the force equilibrium planes are feasible contact force. They also need to satisfy friction cone constraints. So for all the constraints, they lie inside the convex set on the force equilibrium plane. To model the measurement, since we're studying pressure-only tactile sensors, we can only measure the force magnitude in normal direction. So all feasible measurement actually spanning a cone with contact normal vectors. We call it measurement cone. To estimate the force, a particular measurement is reflected as a point on the measurement cone. By quasi-static assumptions, all contact force must lie on the force equilibrium plane. So the estimation is to project the measurement to the force equilibrium plane. To achieve force control, we consider there is a desired contact force, and we want to achieve the desired contact force from the current states. Then we compute the delta force between the estimated contact force and the target force, and apply the delta force to the actual contact force. Because the entire thing is quasi-static, so the actual resulted force still lies on the force equilibrium plane. However, errors could happen from either projection error or sensor noise. So not only a point on within the constraint boundary is enough. We need to consider an ellipsoid of safety margin so that even with errors, the force still lies within the constraints. So how can we find the center of the ellipsoid? We can solve a QP to determine the ellipsoid centers within the constraints. For the case of extrinsic manipulations, a single measurement becomes a subspace cone of the measurement cone. And the extrinsic contact provide least force to cancel out extrinsic force and gravity. So for estimation and for planning, we can find a force that lies closely to the origin. We compare our result with directly using raw measurement from the tactile sensors. We show that our method can successfully grasp object using force control-based dexterous grasp, while using raw measurement, the object is being slide away or fail to achieve a stable dexterous grasp. We also show that using our method, we can track the position more accurately in terms of extrinsic manipulation, such as cube flipping or lifting a screwdriver. So currently, we cannot handle the normal directions uncertainty. And also, we assume quasi-static manipulation case. We hope to extend them into our future work. Thank you, and our poster will be at 12, and I'm willing to answer any questions. Yeah.
Now it's time for question. So I can ask a quick question. So this is a very model-based approach on modeling all the contacting modes, etc. So what type of state estimation do you need for it to work in the real environment?
I think right now we are still using mocap to capture the object pose. And for the robot, its proprioception can handle all of the situation. The issue with this kind of sensing is that we assume that the geometry of the fingertips are well-defined and they can infer the contact normals very accurately, but in practice, this may not be the case. The pose estimation may have error. So we need to also handle the normal direction uncertainties in our future work. Yeah.
Do we have any additional questions? Maybe I can ask another one. So during this kind of sim-to-real transfer, where do you see that you have the largest gap, and how did you actually resolve those?
I think the gap is still on the post-estimation side. So in the sim, you have perfect force, but in real life, even from mocap, there are still some errors. Another thing is that the modeling of the hand is not perfect. For example, we use electric-based tactile sensors, so the thickness of the film is not modeled in our URDF. So that will also cause some errors. So we require some manually tune the models to make the sim-to-real gap smaller. Yeah.
Let's thank our speaker again. And let's welcome the speaker of demonstrating the Octopi 1.5 visual tactile language model by Samson Yu et al.
Hello everyone. Today we're presenting a multi-modal visual tactile language model that incorporates touch, sight, as well as language to perform physical property inference. Humans have used a sense of touch to accomplish a wide variety of feats. For example, I can tell if a fruit is ripe by touching it. In recent years, roboticists have been working on giving robots a sense of touch. There are now a wide variety of tactile sensors, along with a number of works in tactile manipulation involving object manipulation as well as tool use. We've also seen recent work where touch has been incorporated into large language models. For example, where tactile feedback supplements text queries. Last year, we presented Octopi, a tactile language model that is able to perform tasks such as identifying ripe versus unripe fruits using the prior knowledge that ripe fruits are softer. As part of our demo, we'll be presenting our latest version of Octopi 1.5, along with a handheld approach to tactile data collection. You will be able to use natural language to direct queries at our LLM using our GUI. Here, the LLM attempts to guess what is on the table purely by touch. And here, it correctly deduces that it is an apple. What you have just seen is our guessing game, but we will also have a sorting game as well as free interaction, where you'll be able to use our tactile manipulation interface to interact with the various objects around us. Let us talk about our two main components. First, Octopi 1.5. Octopi 1.5 builds upon our previous version of Octopi with four main improvements. First, we replaced our VLM from Vicuna 1.5 to Q1.2. This is to improve the inference capabilities of our model, as Q1 has shown high performance in regular benchmark testing. We also add a vision encoder that allows us to contextualize from the given image what are the objects present in the scene. We also improve our tactile encoder by training it on a larger data set. Our physical data set is increased from 74 to 133 items, consisting of objects of various object properties, as well as a number of action types, such as pressing, twisting, and sliding. And lastly, we add a retriever augmented generation module that makes a prediction of the most similar items that you have observed before. We find that this helps when performing inference on completely unseen objects. These changes improve the accuracy of our models. For example, in the guessing game, Octopi 1 has a performance of around 45%. Octopi 1.5 increases this to around 55%, and when RAG is enabled, this jumps to more than 90%. Next, the tactile manipulation interface. During our data collection for PhysiClear, we rely on a hand-collected approach. Using our hands to directly guide the data collection allows for a high amount of flexibility, but this comes at the cost of inconsistent data, even for the same object across different trials. We also explored using a robot to collect the data for us. While this ensures that each object can be grasped with the same amount of force, this is not very flexible as the robot is bulky and also leads to frequent sensor damage, as it is difficult to fine-tune the amount of force needed. We thus consider if there is an approach that can have the benefits of both. Last year, UMI was presented. It is flexible, but it does not have any capabilities for tactile sensing. We thus modified it into a tactile manipulation interface, TMI, by swapping out the two soft fingers for a hard finger mouse that houses our sensors. The left finger contains the gel site that we use for our PhysiClear. It is an RGB-based sensor that deforms on touch when it comes into contact with an object and serves as a high-fidelity method of identifying textures. The right sensor is a Teco 2 piezo-resistive sensor. It is a 6x11 texture-based representation that allows us to numerically quantify the amount of pressure the object is experiencing. AutoPy 0.5 is not trained on this new modality, but this is part of our future plan. Like the UMI, the TMI also allows for flexible data collection while having the benefit of tactile sickness. In short, our contributions include AutoPy 0.5 as well as a tactile manipulation interface. We will be very happy to showcase this at our demo booth, so please do drop by at our poster 36. Our dataset is also available publicly, so for more information, please check out this. Please scan the QR code to check out our project page. Thank you.
We have time for questions. All right. I have one question. Why did you use Clip as a featureizer for your tactile sensing? It has not been trained with this type of images, so I was wondering what was the reason for using that specific structure.
You mean the piezo-resistor sensor? Yeah. So the TMI actually is in an infancy stage, so our main contribution is AutoPy. So we plan on improving improving our model by adding multiple sensors to it. So our first step is through this piezo-resistive TAC02 sensor.
All right. Any other questions? No. Let's thank our. Oh, we have one question here. Yeah. The ground floor.
Yeah, I was just wondering why do you use two different types of tactile sensors on each of the two different fingers?
Yeah, so thank you for your question. So each tactile sensor has its own benefits and its demerits. So for example, the gel size sensor has a frequency that is quite low, it's around 15, while our TAC02 sensor has a frequency of around 200 to 400. So we want to leverage the benefits of both sensors at once.
Cool. Let's thank the speaker again. Next, we'll have Daniel demonstrating reassemble, a multimodal dataset for context-rich robotic assembly and disassembly. Please.
Hi, everyone. My name is Daniel Śliwowski, and I'm excited to present today a work titled Demonstrating Reassemble, a multimodal dataset for contact-rich robotic assembly and disassembly. So many existing datasets focus on contact-rich manipulation, such as cooking, and others focus on contact-rich and long-horizon data, like furniture assembly. However, we notice there is still a gap for contact-rich, long-horizon, and high-precision manipulation tasks, where small motion deviations could lead to task failures. So hence, we propose to reassemble a robotic assembly and disassembly dataset. So let's start with the data collection setup. In Reassemble, we collect common modalities found in other datasets, such as wrist-mounted and external RGB cameras, force measurements at the wrist of the robot, or audio from externally and wrist-mounted microphones. What's new in Reassemble is actually the inclusion of an event camera, which gives us high-frequency information about object and robot movements in the scene. So here you can see an example where a subtle movement of the peg after the robot nudges it is much more clearly visible in the event stream compared to RGB stream. We also observe distinct force torque patterns for different objects and actions in Reassemble, making it a valuable clue for contact-rich manipulation. What's also new in Reassemble is the hierarchical annotations of our tasks. So in case of Reassemble, we have 4 high-level actions, which are composed of 9 low-level skills. And then across the 17 objects in Reassemble, this results in 78 unique object action instances and 121 unique skill object instances. Reassemble contains a wide range of different hierarchical patterns. So for example, here you can see a gear insertion. Where everything goes well, we would have the approaching, aligning, and then pushing motion. But in some cases, the gear can get stuck during the meshing operation, which prompts additional skills in the higher level action. For example, regrasping and then realigning the gear and then pushing again.
And contact-rich and high-precision manipulation is especially prone to failures. And in reassemble, we have around 520 naturally occurring failures annotated from the demonstrations. And then insert being the most difficult task has the most failures. In the top right corner, you can see a correct assembly or insertion of a bolt, where it's pulled after the assembly to ensure that it's fastened. On the other side, you have on the bottom incorrect assembly where there is insufficient rotation during the demonstration, which highlights how small scale or small deviations from the motions can lead to task failures. Naturally, some objects are more difficult than others, and then there are several factors for this. So for example, it's the motion complexity required for some of the objects. Like in case of the bolt and the BNC, during the insertion, we have to push and rotate it at the same time. Another factor that we observe is the object size. So generally, smaller objects tend to fail more often. And here you can see an example where the small square peg one fails more often than its counterparts. So what can we do with reassemble? Reassemble enables learning contact-rich manipulation policies. In this example here, we use dynamical movement primitives to learn insertion, assembly, and disassembly of the gear. Another key task that is enabled by reassemble is anomaly detection and recovery. So thanks to the rich failure annotations here, we are able to train an anomaly detection model and then use it in an execution monitoring pipeline for the picking action. Reassemble also enables Richards intemporal action segmentation, and actually in a recent work, we showed that by incorporating this multimodal information reassemble, we can actually quite significantly improve temporal action segmentation. So from 5% with vision only to 80% with multimodal data. So just to recap, reassemble is a contact-rich, high-precision, long-horizon manipulation dataset with annotations designed for several robotic tasks. You can access the dataset on the project webpage. You can just scan the QR code in the top left corner. And that would be all from my side. Thank you for your attention, and please come to our demo booth.
Now I have time for questions. There's a question on the ground floor in the middle. Oh, Dale, please.
Is there any consideration of trying to take these tasks and bring them into simulation for large-scale evaluations and things like that for people who don't have robots?
Mm-hmm. We have one student working now on preparing a simulation environment for this data set, so hopefully soon we'll be able to also have a simulator for it. Yeah.
Yeah, the next question will be the middle. Do you still have the questions? Yeah, we can go with the...
Thanks for great talk. I wonder how audios are playing an important role in the assembling task.
That's a very great question. So you can imagine that one of the tasks in the reassembly is, for example, inserting an Ethernet plug, where you have this tab that is getting locked after you push it in. And actually, when you're pushing in the plug, you can clearly hear like an audio cue for it being completed. So it could, for example, help in the anomaly detection part, where if you hear the click, you know that you did it successfully. And if you did not hear it, then there might be some problem.
Thank you.
Let's thank Daniel again. And let's welcome our last speaker, Jitin Chen, who is going to present robust pegging hole assembly under uncertainties via compliant and interactive contact-rich manipulation.
It's a great pleasure to present our recent work on robust pegging hole assembly. I'm Jitin Chen from Rice University. Pegging hole assembly is a fundamental task in manipulation. Billions of such insertions occur daily across global manufacturing processes. However, despite of decades of research, real-world robotic systems continue to struggle with this challenge. Here are two videos of humans demonstrating this task. While these seemingly simple tasks are actually quite difficult for robots. So why is it so difficult? Common strategies often formulate the task as a relatively positioning task, seek to optimize the insertion trajectories under certain conditions, either through modeling the environment or formulating the problem as a partially observable Markov decision process. But the question is, can we really rely on this paradigm for robust manipulation? We're just trying to find a suitable motion trajectory and execute it. In the real world, the system will always have to cope with all kinds of unmodeled parameters and inaccurate dynamics. No matter how good the policy is, it is the execution phase that brings the optimized result into reality, as shown in this figure. And there exist inevitable uncertainties. We always introduce small deviations between planned and executed trajectories. And this level of uncertainties might be trivial for other tasks, but it is actually fatal to pegging hole assembly under very tight conditions. To tackle the above challenges, instead of formulating the pegging assembly as a positioning task, we view it as an interaction-driven task. We focus on outcomes of interactions between the peg and the environment, and allow the environment to alter the peg's motion. Our design consists of two major components. First, we identify the environmental constraints through compliant interactions, and then we leverage the environmental constraints to shape the insertion process to achieve robust pegging hole assembly. To realize this system, we examine the role of structured compliant motions under contact constraints. First, when compliant motion is altered by external contact, it also reveals information about the environment which provides that contact. And second, we interpret compliant motion as creating a potential energy field with the target equilibrium posed at its global minimum. By strategically placing that potential energy field around non-penetration contact constraints, we are able to set the actual goal state as the local minimum inside the potential well. Any initial states from the potential well will converge to the actual goal states without relying on any precise executions or any precise trajectories. In brief, our system first plans collision-inclusive interactions with the environment to infer constraints on the target distribution of the target hole. And during the insertion process, the system finds a sequence of intermediate states that connects the initial states to the pegging hole states and configure each one of those intermediate states as the local minimum inside the potential well. And in this way, our system formulates the insertion process as a joint effort of compliant interactions and passive adaptation from the environmental contact constraints. And this is how the robustness comes from. We evaluated our system on real-world pegging hole tasks, including the NIST assembly task board and challenging irregular shaped holes. I think the video stopped.
We're having some technical difficulties with the video. Can we fix the frozen video? Okay, I see there is someone working on it. All right, we're manually moving it.
Okay.
First.
And we evaluated our system on real-world pegging hole tasks, including the NIST assembly task board on the left side, and those challenging irregular shaped holes on the right side with rough materials and tight clearances. And we aim to demonstrate that we can achieve precise insertions without exact defined trajectories.
I believe it's frozen again. Can we move it forward? All right. Okay, I'm sorry about the technical difficulties. You should go to talk to the speaker on their poster. We're going to take one very quick question because we are over time with the session. I'm very sorry. Let's take one. First, a round of applause to our speaker. And let's have a very good question for our speaker. Here in the middle.
So for many industry peg and hold tasks, there's a minor deviation from symmetry to orient the part. Do you know if your local minimum like heuristic works well if there's minor symmetry deviations?
Sure, I think our theory actually works for a lot of convex object shapes, and we do not require any symmetries on the pegs. Okay. If that answers your questions.
Yeah, I was just wondering if the more complex, like concave or not convex objects also.
Oh, and we haven't tested on the on the concave shapes, but actually we have videos of performing the insertion with very random convex shaped pegs. Okay.
Thank you.
Okay.
Yeah, let's thank the speaker again with a strong applause. So this concludes these sessions. Next, we'll be gonna have a very exciting panel on the past, present, and future of robotics. Please stay around.
Alrighty. All right, we might get started with the panel. Great to see you all still here. So we're going to do this in a little bit of a reverse order. So I'm going to first introduce our amazing panelists one by one, and then they're going to come out. And then I'm going to explain a little bit the rationale behind why we're experimenting with a slightly new event this year, and what you can expect to hear from our panelists during this panel. So first off, I'm going to introduce the panel. We have 6 amazing panelists, and we'll welcome them one by one. So first up, we have Chelsea Finn, assistant professor at Stanford and co-founder of company Physical Intelligence. Next up, we have Russ Tedrake, professor at MIT, senior VP of research at the Toyota Research Institute. Next, we have Jeff Hollinger, professor at Oregon State University. Next up, a little closer to home for me, we have Fabio Ramos, a professor at the University of Sydney and a principal research scientist at NVIDIA. Next up, we have Ayoung Kim, an associate professor at Seoul National University. And finally, for our 6th panelist, we have Harold So, an assistant professor at National University of Singapore. So I should probably introduce myself. My name is Michael Milford. I'm director of the QT Centre for Robotics all the way back in Australia, and I have the honour and also surprisingly nerve-wracking privilege of trying to organise and MC this panel, and so I'm very much looking forward to it. So why are we here? Well, a couple of years ago, Luca asked me to do some area chairing, and I said, thank you, but no. And then this year, he asked me to do some more area chairing, and I said, thank you, but no, but let me know how I can help out in any other way. And then Luca came back a 3rd time, and the 3rd time you're asked, you can't say no. And so I signed up to try and organize and MC this panel. So this is not my idea. This is Luca and Amanda's idea that with the coming of age of RSS, its 21st birthday, and also all the exciting things happening in robotics, it would be very suitable to have a panel where we step back a little bit from the amazing technical research that you've been seeing and think about the big picture for a little bit. And to talk about the big picture, and today we're not going to have a 1-hour debate on humanoids and autonomous vehicles, that's not what we're here to do, but you can literally step outside this hall and go take a fully autonomous robotaxi. And for the first time, arguably in history, we can say with a straight face that there is now a non-zero chance that there will be millions of new, useful robots in our homes and our workplaces in the next few years, and potentially billions a few years after that. And I don't think we've really been able to say that at any other point in history. Some people have said it, but I don't think we could have widely said it. And so it's a really good time to reflect back on the research that we've done over the past few decades that has led us to this point. What we are doing now in research, are they the right things? Are we missing some of the bigger picture? and then to think forward in time, to research 10, 20, 30 years into the future in robotics. And so that's what this panel is about. We thought about having a debate, but the debate is a little bit adversarial by nature. So we went with a panel, but in exchange for that, I've encouraged the panelists to present their hot takes, their unpopular opinions, to add a little bit of spice to today. So we'll see what they say. I do not know what they're going to say. I have not been forewarned. In terms of how we're going to run it, we're going to run it in 3 sections. Surprisingly, or not so surprisingly, the past. What have we been doing in the past? What can we learn from past research? What mistakes should we perhaps not repeat? And what things have we forgotten about that we should perhaps be looking at again? We'll look at the present. We're in the present right now. We're hearing from a record crowd at RSS about all the amazing research going on. But there's also a chance to step back and think about, are we doing all the right research in all the right areas? And are we going about it the right way? And then in the most speculative session, because we don't know what's going to happen, we're going to do the future. So what do we expect going into the future 10, 20, or 30 years into the future? All right, so before we get into the past section, I just want to calibrate what past means for the audience, for our panel, so they get a bit of an idea. So what I'm going to do is I'm going to mention just a few pivotal moments in robotics research history or platforms history, and if you were currently engaged in active research in robotics at the time, whether it was as a master's student or perhaps even as an undergraduate, please raise your hand. And I'm going to go reverse in time. So we're going to see what we get from our audience. So first up, we have the popularization of large language models with the release of ChatGPT, which then spurned a whole bunch of follow-on research in robotics. And this was in late 2022. Who was active in their research careers already at that stage? Oh, wow, we've already knocked out a fair chunk of the audience. Wow, that's fantastic. All right, going back a little bit further, in 2015, 2016, when we're really getting into deep RL for manipulation, who was active in their research careers back then? Oh, wow, that's surprising. Okay, we didn't knock so many people out in that little gap. All right, let's go back a little bit further to what was then the most disruptive AI and robotics revolution, which was deep learning, circa 2012. Who was doing research in robotics or similar fields back in 2012? Okay, we're getting some handshakes, sort of fuzzy definitions. Fantastic. All right, we all use this, or a lot of us use this software, ROS. Its origins were in Stanford, but then Willow Garage really took the ball and ran with it in 2007 onwards. Who was active in research in 2007? Okay, we're really thinning out the pack a little bit. All right, 2000. Arguably about the time that SLAM, simultaneous localization and mapping, became a thing in robotics. Who was active in research back in 2000? All right, and very quickly, And very quickly, 1992, Alvin, one of the first sort of autonomous vehicles. Anyone still active in 1992? Gaurav, thank you. Okay, let's just knock Gaurav out. 1986, Brooks, subsumption architectures. Still going then? All right, apologies, my eyesight is not great in the dark, but I think we've knocked everyone out. All right, so we have a bit of an idea of our audience. So let's go on to the past. So the past is behind us. It's really hard. We're not going to get into the semantics, but we've had sort of, I would say, about 40, 45 years of a relatively large, vibrant robotics field. ICRA started in the mid-'80s, and the field has been growing and going from strength to strength since. So for their takes on what we've done in the past, perhaps what we've done well, what we missed, what we've forgotten, what lessons we've learnt and then forgot, I'm going to throw over to our panel for some pre-prepared statements, and I'm going to start with Chelsea.
Great. So I'm going to talk about the year of 2015, so maybe somewhere roughly in the middle. The past, yeah. So at this point, I started working on machine learning and robotics. At that point, if you went to ICRA or RSS, the works that were doing learning for control were a very small minority of works. And in particular, I worked with a number of collaborators, Suri Levin, Peter Abil, Trevor Darrell, others. Trevor will be giving a talk tomorrow, I think, or today. one of the things we're really proud of in our work is we trained a robot to like screw a cap on a bottle with like 5 to 10 minutes of data. And we were really proud that the robot was so data efficient. It was able to learn so quickly to do this sorts of task. And looking back on that, I actually think that one of the things that I've learned is that using such little data means that your system is going to be so brittle under the face of any sort of new situations. It was trained completely from scratch, and its whole world was that 5 minutes of experience. And instead, I think if we look towards today, the systems that are going to generalize broadly to open world conditions are the systems that are trained on broad and diverse data sets. And so instead of trying to actually have this virtue of data efficiency, in fact, the most important thing to be working on is actually not data efficiency, but systems that actually leverage large amounts of data in order to generalize under broad open world conditions.
Thank you, Chelsea. Russ.
Awesome. So I thought I was going to be the future part, but then I guess the poll disillusioned me. Okay, so back when I did my thesis, first of all, it was different to be a roboticist then. You know, I cut my own metal, I wired my own electronics, I wrote my own equations of motion, and I wrote my dynamics engine and my visualizer because it didn't exist. You had to do all of that. And I'm not saying that it's better, but that's very different than the experience that students have today. And it makes you, I think, look at the problem a little differently. And it's interesting to think about what we've gained. We're a lot faster now, but we've also lost something. Ironically, I wasn't thinking it, but I guess I did RL for my thesis back in the day, too. And it's interesting, you know, it was even RL for bipeds. It was too early. But now it seems to be kind of, at least this year, it's kind of the winning approach. So I was reflecting, if I knew then what I knew now, you know, I'm not taking credit for that. I wasn't like Jan LeCun, who was just like laser focused on CNNs for many, many years and gets all the credit. I did many things and came back. But actually, I think the journey was extremely good and important, and is still super important. I think that, you know, it was hard talking about RL back then. You had to convince people it was important. It was hard talking about optimization back then. I remember having a meeting at one of the big conferences at a table with people that I deeply respected, and someone looked at me and said, "Russ, people who talk like you aren't the people that make real robots work." And I was just like crushed, right? And then I think it was really the DRC was the first time people started using quadratic programs to make inverse dynamics respect friction cone constraints. And that was, I think, the first time the optimization world kind of came more mainstream, and people, even that particular person, started using QPs. Actually, when Mark Rabert, who was not that person, gave a talk about MPC, I was like, oh, yes, that is success, because he used to hate on MPC before that. But I think that journey was like super important. I think I look at the problems, I look at what's happening in RL today, like very differently. I mean, not only did I not have the GPUs and stuff back then, but I really think that path took a really important intellectual journey that changes the way I look at that problem. And I hope that we can find incentives for young people today to take similar journeys that are a little bit, you know, off the beaten path and make you look at the problem in a different way.
Thank you, Ross. And we may revisit that theme of what we knew at the time and what we know now as well. Jeff.
Okay, so I'm going to take you back to my first RSS, which was not the first RSS, but it was 2006 in Philadelphia. I spent that summer at UPenn updating my code from player stage 1.6 to player stage 2.0. Anybody? Yeah. And so that RSS, you know, almost every presentation, or lots of the presentations, they had Gaussian processes or Bayesian reasoning in them. And that seemed to be the fad at the time. That was what people were using. That's what people were excited about. And I was excited about that. I did a lot of research in that area, too. And 5 years later or so, people were talking a lot about factor graphs. That was really exciting. Lots of the talks had factor graphs in them. Then maybe 5 years after that, everybody was talking about autoencoders, LSTMs, deep learning hit the scene. That was huge. Tons of the talks had that. So these seem to be the fads. Now, here, maybe it's foundation models, whatever, right? There's lots and lots of talks have similar things. So what I wanted to bring up was this idea that there seem to be these fads. And is that good or is that bad? Well, what seems to happen is there's a fad and lots of papers have them, and now a few papers have them. Because I definitely saw Gaussian processes this week. I definitely saw factor graphs this week. I saw some autoencoders this week. And so what I think we're really good at doing as a community is taking these fads that often come from other communities and distilling them down into the key capabilities and the key tools that we're using for our robots. So I think that's something that we've learned and something we've progressed on.
Awesome. Thank you. Over to you, Fabio.
Yeah. I'll take you back to 2008, 2009, and at that time we thought we had SLAM figured out, right? And my goal at that time, I was finishing my PhD, was how do I take this research in robotics and turn that into, into something useful for industry and have an impact that goes beyond papers. So a big mining company came to us and said, I would like you to automate material movement. And I said, oh, I have SLAM here. What about that? And he's my robot. And that's that white car you see in the screen there. 1 year passed, and they didn't care much about that. Then they came back and said, oh, I would like you to automate drilling so I can fill up the ground with explosives and grind the material and transport. So I have SLAM figured out. I can make this localization work very well for the drill process. 1 year passed. They didn't care much about it. Then they came and they said, well, I would like you to automate the entire mine. And I said, all right. So maybe what you are looking for is not a robot, but what you actually need is a system. It's how you put everything together and turn research into a solution to your problem. So I think my main message was, I think we think too much about a robot. A robot is basically a tool, and we need to think about the solution they're trying to build as a system altogether, particularly when we talk to industry.
Thanks, Fabio. Hey, Young. You can always borrow the mic next to you if you need. I think it's just on.
Oh, it's on.
Yeah, you're on.
Yeah, I got it. So when I was asked by Michael about this topic, I was thinking, well, yeah, what is the past and what is the future? My assumption for the past was 20 years ago, and I was projecting to the front another 20 years. So for me, 2005 was the past for me. And that was time when I started my master, and I started my PhD in 2007 and started working on SLAM. So I was in the transition mode from starting my PhD with Kalman filter and ending my PhD with factor graph. So I was in that range. And what I was thinking as a past, and I looked back and what is the difference, and the first thing came up with my mind was the generalization capability. I think we didn't really care about that much, but in a second thought, I realized when I was working in the past, instead, we really worked hard to make the system robust. We run algorithm. I think everybody are doing the same thing, manipulation or control, or whatever. We run algorithm. It may succeed, may fail, and we wanted to improve the success rate more and more, and we wanted to make it succeed, even if there's some random thing happen and kind of prevent you from succeeding it. So. Something that one learned from the past is how whatever we tried so hard during that last 20 years to secure robustness, maybe could that be helpful and implemented to secure the generalization capability? That's something that I was thinking about the past.
Thank you, Aaron. And just before I throw to Harold, I will mention we were not sure how well the panelists would stick to their very strict timing that I allocated them, but they're doing very well, so we will have time for some audience questions. So if you have any humdinger questions about the past, the present, or the future, we will throw to the audience for a few questions as well. Sorry, Harold, over to you.
You did not count on me exceeding the time they given to me. So I'll go back to 2012, 2010. I think I was working with the iCup. I don't know if anybody here worked on the iCup, this humanoid robot. Working with the Pioneer, Red robots, mobile robots that moved on the ground. So those days, robots were a lot more expensive and less capable than they are now. I think that's a trend I see. We see robots getting better, they're getting cheaper. You can walk around RSS, walk around ICRA, and you see just amazing stuff. And this is great because it's lowered the bar, right, the entry towards robotics. And I think that that's been fantastic. I think we've gotten new people in and bringing the ideas, and that's been great. Okay? I like the fact that I don't have to plunk down millions of dollars to start my research lab. I think that's been fantastic. That's what I've been happy about. Something I've not been so happy about. So I used to work in Gaussian processes as well. I still do a little bit. But I think that the key idea there was really about uncertainty modeling. And I'm a little bit upset that that hasn't been, brought into our new generation of models. We've kind of left it aside for a little while. I can understand why this is the case, because it's hard. But I think it's also super important as you move from predictions to kind of actions. And I think that we should bring that back. So if we were to learn something from that past, I think we shouldn't forget some of these core principles as we move forward. So that's my take.
Awesome. Thank you, Harold. All right, I don't see anyone in the audience ripping their hair out yet with angst over a controversial take, so we can continue to work on that. But in the meantime, do we have any questions? We have an amazing panel at your disposal for any questions, particularly focused on historical past robotics practice and perhaps what we can learn. Any takers? Thank you. In the middle, on the bottom floor, please. Keep your hand up.
Can you hear me?
Yes.
I don't know if it is considered past, but I was there when, back in the Valley in 2013 timeframe, people were saying we are going to solve level 4 autonomy, level 5 autonomy by 2020. And I was there again, I didn't see level 4 or level 5 autonomy. So it's like, I feel like people are setting expectations way high, so humble people cannot find a place to work. So what went wrong in autonomous driving? At the end of the day, it's a robot we ride on. We are roboticists. Well, what can we learn from the failure of companies? Because they burn billions of dollars on some hype, in my opinion.
All right, before I throw over to the panel, I sense the first red flags of a degeneration into a debate around either autonomous vehicles or humanoids, so we're going to try and stay and connected to the research. But any thoughts on expectation management, overpromising as applied to autonomous vehicles or other areas from our panel? Russ?
I'll take a shot. So it's not obvious to me what the right answer is. So I agree there was a lot of expectations set. Maybe some of them have been met, not all of them have been met. But I think the question of what was the right thing is actually extremely nuanced, because it did bring a lot of money into the field. It brought a lot of talent, probably a lot of you, into the field because of that. It accelerated things in certain directions that we're benefiting from now. I think that's happening again, right? I think that the fact that we're talking big, we're lighting up everybody's imagination, is bringing incredible resources and incredible velocity into the field. And we're walking the line again, of course, but it's not clear what's the right solution.
Awesome. Now, just in the interest of making sure we stay on time, the panelists will get a chance for final thoughts, and so any particular burning answers to questions we can come back to at the end. But in the interest of sticking to a relatively even coverage of historical, present, and future practices, what we will do is we will move on to the present, broadly construed, and it's a pretty fuzzy definition of what is the present, but loosely you could just think about all the stuff that you're seeing at RSS, all the amazing research. It's the age of learning. We have large language models, foundation models, we have splats, we have NERFs, and we have a resurgence of interest in commercial companies and startups in areas of robotics. So with that sort of general context, in terms of what we're seeing this week and generally in the research community and what we're doing now, what are the key insights or things that you would like to raise attention to? And we might do this in reverse order this time, and we'll start with Harold.
Oh, okay. So thinking about the present, I thought about this in terms of a thought experiment. So let's play along. Guys, play along, okay? So this is a thought experiment. Imagine if you could reorganize the world's robotic research. Like, you get to tell everyone here what to do, essentially. And you organize the resources, you can put us into teams, you can do whatever you want, okay? Total power trip. The catch is this. once you decide on what to do, you can't interfere anymore. Okay, you got to let the system run. Okay, so you think about that. I don't know the answer. I'm not sure anyone does. But I would like to bring up maybe 2 principles that we might want the system to have. So the first is that good ideas should spread and persist in the system. Okay, and the second is that the system should be self-correcting because good ideas change. Okay, now these are not new ideas. I think science is built on these 2 ideas. All right, the reason I bring this up is because if you look at how research is conducted today, sometimes when I speak to my students, I see problems with these 2 principles. Okay, how do my students come to me and they say, okay, we found out all these papers from Twitter, which is great because we get information fast. That's fantastic. But sometimes it's not the good ideas that spread. It's the ideas that are easily digestible, a bit more sexy, so they spread faster. I think that we need to be cautious about signal to noise. So how we do that, we should think about. The second about self-correction. So I think that, talking about how hardware is getting cheaper, maybe we need to think more about valuation and how we make sure that, how we tell the good ideas from the bad ones, I think is critical. So we're at this phase now, we're in lucky time. I think it's very exciting that we have all these developments along the way. But we really, really need to be more rigorous about testing and rigorous about finding out which ideas are the good ones and which ones are the bad ones. And so I would encourage us all to push towards that direction a little bit more.
Thank you, Harold.
Yeah, following up on that, I really thought a lot about this present part a lot because, like for me, the one that I want to, if I can correct and then make a new design for the Robotics Society, what I want to fix and correct is the evaluation system or evaluation metric or whatever you call. It's somewhat related to what Harold just previously mentioned. The current estimate, for example, the SLAM, what we use as the evaluator, like we all look into the mean value of the error, looking at the trajectory, how if the odometry accuracy is really accurate, we think it is a good. So we can develop and we can grow in the way that we design, how we design the evaluation system, I think. So if we wanted to, but that's kind of controversial to what we wanted to achieve, isn't it? Like accuracy and not making mistake, and versus what we want to achieve is generalization capability and reducing uncertainty. I think if I can do something, I really want to spend some time designing a better and more robust evaluation scheme or metric or system or whatever, so that we can focus more on the generalization capability and robustness, and we can value more on those. I think that's the thing that I want to mention.
Yeah.
Yeah, one thing I noticed from that time, early in the days, 2008, 2010, was the independence of each research component in robotics. So you go to the perception session, and you'll be, just perception. Not many people caring about planning or control. And then you go to control, they wouldn't care much about perception and so on. Now I see much more of an integration happening, right? So people are trying to put together a solution to problems. And robotics is becoming much more accessible. You can buy reusable arms, robot arms, for less than a laptop today, which means that there's more people joining our community. We should welcome them. In addition to that, we have software, open source software, simulators out there. And when these people come to the community, they find lots of software that allows very easily, training on data, right? Gathering their own data, training, doing the full loop, get some evaluation, and so on. But in many cases, they forget about what we've done in the past that goes beyond learning. What about the control, the planning methods that were already there? How do they compare to the new learning approaches, right? So what I see today is, a community that is growing. There's a lot of young folks here, and it's very exciting to see this. but it's also part of our job as a field to inform them that there is more than just what has been happening the last 3-4 years, right? There's the entire research of robotics that's still relevant today and will be relevant in the future.
Thank you, Fabi.
Okay, so how many people watch the show Bluey? Either with your kids or by yourself, that's okay too. My daughter's 8, I love it, great show. So there's a character on the show that the dad puppets. It's called Unicourse. And Unicourse always says, why should I care? Why should I care? So when I'm watching robotics presentations, I've seen hundreds of them, I'm always thinking, why should I care? Because I've seen dozens, if not hundreds, of robots picking up objects. Dozens, if not hundreds, of robots putting pegs in holes. Dozens, if not hundreds, of self-driving cars driving down the road, right? So I think that currently, when I care, and this is becoming more and more the case, I see new capabilities that I haven't seen before. So I'm going to give you an example. I was part of one of the teams in the Subterranean Challenge, the DARPA Sub-T Challenge, where we went into underground environments and we mapped them and we found objects in those environments. And in order to do that, we had to develop entirely new capabilities of dealing with terrain, dealing with difficult perception, degraded communication, all of these things that don't happen in the lab. So I see these demonstrations in the lab, and I think about, well, how would this algorithm work in more denied environments, more challenging field robotic environments? And I think that what's exciting to me is that I'm seeing more papers that are in these incredibly unstructured and uninstrumented type of environments. And towards the end of the Sub-T Challenge, they actually had announcers that they hired to try to make it like the Super Bowl of robotics. And one of those announcers said to the other one, after about the 4th or 5th team did really, really well, because there were a number of teams that did very well in the final challenge. They said to them, well, what do you think? What do you think about the results here? And the announcer said, I think you could go into subterranean environments, map them, and find objects. Now, you can do that. You couldn't do that before. That's a brand new capability. It's not a 1% improvement. It's not a 10% improvement. It's a whole new capability. And that's what I'm excited about robotics right now, is I'm seeing more of that.
Thanks, Jeff.
Okay, that's awesome. So I actually loved what Harold said. I'm going to riff on that a little bit. And it's because when I talk to people out in the lawn or whatever, I think the questions I get these days are not always technical. Sometimes they're just like, how should I think about research? And I do think being a student today is a really interesting, it's both an incredible time, like where things are changing so fast and you can have so much impact, but it's also a very complicated time. I think we've seen, I guess I was old enough to have seen like the transition from robotics published mostly in journals to conferences, and we had to convince our department heads the conferences counted. And we went from conferences to archive, and archive to Twitter, right, and blog posts. And that's a big change, right? And we went from, our funding has changed, right? It used to be that we were mostly government funded in the US, right? And to being a lot of industrial funding, and now we're VC funded. And that has changed, and that has changed right? And that changes the incentives, and it changes, some of the morals that I have don't perfectly align with that, right? And I think some of the most intense of you, well, you'll leave lab and you'll go home and you'll watch lectures on YouTube or talks on YouTube, and then when you're like on the way from lab to watching YouTube, you're listening to a podcast about something technical, right? And there's just this incredible pressure to be plugged into everything and track the fire hose. And that is awesome. The accessibility of information is awesome. But I think there's also a role for turning all that off, right? And thinking deeply about some problems. And I just want to take a second to like advocate for the deeper work stuff, right? I don't know how many people have read Deep Work by Cal Newport. It's pretty good, right? But there's a story at the beginning about Eric Demain, who's a faculty in computer science. And he tells the story about Eric, who Cal walked into work one day and he saw Eric sitting there at the whiteboard kind of looking like this. And then Cal worked all day, went to lunch, came back, worked all day, and then he left at the end of the day, and Eric was still staring at the board, looking at the same equations. And that was sort of emblematic of deep work. And I've had collaborations with some with a really good Russian mathematician, with Pablo Perillo is one of my best collaborators. I think a few of the folks that work with me, Bernard and Alex and Tobia, might even be here, although I can't see anything. For me, those sessions, I tell you, we tend to meet on Thursdays, and we start like at the end of the day, and we go until we're done. And when we were talking about the graphs of convex set stuff, we would go routinely 3 hours, where we're just kind of sitting there thinking. And it took 3 years till we published the first papers about that. And it was interesting. The last time I was at USC, I actually was giving talks about both diffusion policy and graphs of convex sets. And the difference between those were actually striking to me. I could say, I think there was a very little chance that someone could have asked a question about GCS that I wouldn't have thought. Not to say I had every answer, but I had such a robust understanding of that relatively, that it would be hard for someone in a few minutes to have caught up with the amount of thinking we had done on that, right? With diffusion policy, most of the questions people asked, we were saying, yeah, well, I don't really know, or we haven't tried that yet. And it's a much weaker position. So I think both of these will be important in the long run, but I guess I really hope that we incentivize people, again, sort of to also take the time to think deeply. And your role as a student is not to publish papers every quarter. It doesn't even matter if you do something relevant, actually. I mean, maybe that's spicy, I don't know. You shouldn't have to get citations, really. You should take the time when you're being protected by your advisor from all the noise of the world to just focus on one thing and have the experience of going super, super deep in that one thing, because you'll never get that chance again, right? And it doesn't really matter what you pick, but having experienced that depth one time, I think will help you see things differently more quickly in other fields when you're ready.
Just before I pass to Chelsea, I'll note that Russ did a fantastic job of empathizing with the pressures that students feel, but not all of us have VC funding yet. If you don't have VC funding, you're doing okay. Chelsea.
I'm tempted to reply to Russ because there's a lot of things that I agree with, but some other things that I maybe disagree with. But I'll stick to what I was planning to cover, which is that I think that now is a really exciting time in robotics. I think we've seen how foundation models have truly so much potential for enabling robots to go out into the real world and have actually work in the real world, which I think was unimaginable 10 years ago. And I think that one of the things that's a bit different is that typically in machine learning research and robotics research, we think about designing new algorithms or designing new methods, and things are a little bit different in the world of foundation models. One of the things when we were working on Pi 0 and Pi 05 that I wanted to highlight is that, first, unlike other domains in foundation models, we don't just have the data laying around for us. And so we need to both be figuring out how to collect the data, what data we want in the first place, and also actually how to, at the same time, in parallel to figuring out what data to collect, also figure out how to actually train models on 10,000 hours of data, which we've never even conceived of having before, at least within the realm of diverse, dexterous manipulation. And so I think that it kind of changes what, a little bit of what becomes the most important problems in robotics at the present compared to in the past, where I think that, and maybe to maybe reply a little bit to what Russ was thinking, I think that at least for me, I think the things that are the most impactful is actually spending time with the data, spending time figuring out what data we should be collecting, spending time with the robots and the policies. I actually really love sitting with robots and seeing how the robot's behaving and understanding that. And so I guess to reply, I think that for me, actually, the most impact hasn't been spending time thinking, looking at a whiteboard. I enjoy that. I like thinking a lot, but I think that actually, so much of this is we can't really just think about how neural networks work. We don't get an understanding just by writing down equations and thinking about it. A lot of it just comes down to running experiments, looking at data, looking at the robot, doing the tasks in response to that, and building intuition from running all sorts of experiments. And sometimes that sort of work is quite sometimes tedious, I guess, if you don't looking at data can be quite tedious, but I think that a lot of the impact will come from and to actually develop robots that can go into open world environments, that impact will come from figuring out what data to collect, how to collect it, and developing methods that will scale to those large data sets.
All right, now we move to the future, and I'm going to answer possibly a burning question a few of you have about the composition of the panel. And it is a relatively youthful panel. We could have got one of the distinguished veterans of robotics from the last 50 years, but the youthful composition of the panel is about accountability. And so I wanted people around who you can go up to at RSS2025 and say, I remember what you said on that panel in 2025, and you were spot on, you were completely right. But that is really what this section is about. What will we be doing in 2045? What research areas will still exist? Will humanoids by that stage be like elevators, a platform that has absolutely, or as far as I know, absolutely no further innovation attached to it? Will we have merged with the computer vision and AI and ML communities, or will we have further specialized? Will RSS have 10,000 attendees? These are all questions we can merely speculate at. And to start us off, I'll throw it over to Chelsea.
Great. So I think that, let's say the year is 2035. I think that as we've seen with autonomous vehicles, I think robots will start to be widely deployed. And I think that the research problems will look really different in that future. In particular, as robots are starting to be deployed a lot more broadly, we'll have way more data. And you might notice a theme in kind of my responses here. In particular, if we take an analogy of like Tesla or Waymo right now, they have probably more data than they could hope for, and they're not thinking about how to, for example, leverage data of humans walking on sidewalks, for example. They're really trying to figure out, given all of the vast amount of data that they have, how do they figure out which parts of that data to keep versus throw away, how to leverage that data. A lot of that data might be lower quality and so forth, and basically figuring out when you're instead of right now where we're thinking about how to collect data, how to use that data, we'll actually be thinking about how to throw away data and how to use very large amounts of low quality data. At the same time, it'll be really important to figure out when you have large amounts of low quality data, how do you get really high success rate? Because the reliability of these systems is really, really important as they're being deployed. And this is actually even a problem that hasn't been fully solved by language models even, that we don't have 99% reliability for these models. And I think that there's a really tremendous opportunity for these systems that are deployed to see, because we can get a large number of mistakes of online data from these systems, they should be able to learn from all of those mistakes and actually achieve really high reliability, more so than hand-engineered approaches that might be looking at safety and so forth. So yeah, I guess the kind of takeaways, I think that we'll look at things quite differently once there is large amounts of data from robots being deployed. We won't need to be thinking about the same sorts of data sources that we think about today. And using that data to achieve really high reliability will probably be top of mind.
Okay, so you asked about hardware. I'll start there. I think hardware is going to. People underestimate how much work there is left to do in hardware, right? I think by 2045, gosh, we're going to have certainly soft robots. They should be self-healing. Maybe they need to grow. Is that useful? I don't know. Maybe you don't need to grow if you have a hive mind in the cloud. But it seems pretty important for our infants, right, to sort of start small and get big. Robots are going to look totally different. I do think that building generalists right now is the right thing to do to launch the curriculum. But I expect that by 2045, we'll start getting specialists too. How many people saw Electric State? Kind of a goofy movie, but I actually loved the robots in the movie because there was just all these boutique specialist robots running around, and that's awesome. That's how it should be. It'll happen after we sort of learn how to build as general purpose as we can right now. Maybe it's humanoids. I actually completely agree about. So let's say just take the imitation learning large language model or large VLA, LBM kind of model. I don't see a ceiling to that from data yet. I don't think any of us do. And we should absolutely scale that. And I do think that, I think it's hard to ask the right whiteboard questions until we see what happens in that exploration. For me, I'm struggling with that, right? But I do think that's kind of phase one. I think some of you heard me say this once before. I think right now we're kind of like Voltaire sticking electrodes in frogs, right? And we kind of see something that's really interesting there, but it's just purely, we don't really know what's going on. And I think if we collect the right data and we scrutinize it with long walks and deep thinking, then we'll find like the governing equations. And in the electricity and magnetism space, that was Faraday, sort of came up with the right key experiments that sort of elucidated the fundamental principles of the data. And then it took another 30 years or so for Maxwell to give us the governing equations. And it's not going to be that, a theorem that when you're applying a toaster, touching a toaster, you need to, it's not going to be at the level of that. It might be lessons, theorems about the data. What is the right curriculum? I think we must have a much more rich, rigorous understanding of what that means. And the way we'll get there is by just spending lots of compute, subsetting the data, and learning the lessons in order to guide those questions. Now, what I'm thinking about and worried about is how do we get there, right? So right now, industry is doing this work very well, right? And I think academia is feeling a little stuck. A lot of people are taking dual positions, like me, right? And I really want to make sure that we somehow incentivize, again, that's my theme, I guess, we incentivize the world to somehow do that large scaling. We must see what happens, but also extract the core lessons in ways that really leverage the people that are best at the deep thinking, and don't ask them to switch tracks for 30 years until we're ready, in order to sort of direct the whole force of the field towards our ultimate understanding.
Okay, so 2045, we're going to have the millions of robots that Michael predicted in the homes and the offices, and self-driving cars are all going to be solved. Russ and Chelsea and their VCs are going to be incredibly rich. And those problems are all going to be elevator problems. So we're not going to be worried about those problems anymore because we had the data. We used the data to solve them. But the problems that we're going to be worrying about are the problems where we don't have the data. We're going to be thinking about how do we drill through the ice on Europa and find life under that ice in an environment that is completely unknown and completely inaccessible without any data. We're going to be thinking about how do we meet 60% of the West Coast's energy needs using marine energy with marine robots providing the maintenance, inspection, and monitoring around those offshore arrays. How are we able to do that in those extremely complex and very difficult to gather data environments? We'll be building aquaculture farms in order to get kelp burgers, which taste a lot like Impossible burgers and are very tasty, and being able to do that with almost zero freshwater requirements. But we're going to need robots in order to do those things. Building hydroponic farms on Mars so that we can explore the solar system. We're going to need to do those things as well. But we can't solve those problems by getting terabytes and terabytes of data because it's going to be too difficult to get that data. So we're going to need to solve these data-sparse problems, and we're going to be developing methods that can solve those problems. That's where I think we're going to be in 20 years. And I won't be rich yet because I'll still be working on those problems.
All right, so in one sentence, I would like to go from 80% RL bench kind of results to a robot that will take care of our grandmothers and help them live unassisted for as long as they can, right? So I think there is a major problem for us in terms of demographics, right? Population is getting older, and robotics has a major role to play in helping humans live independently, right? I could stop here, but I think there is more to that goal, right? I think the way we do robotics, or at least it seems like a big trend today, is, well, we get this bunch of data, we have this super highly parameterized model, and then we train it, kind of torturing the data until it confesses, right? To get an estimate, right? And I think that has value for now, but I think we need to distinguish between data, information, and knowledge. And knowledge can come from data, from observational data, but it can come from other ways into your model, right? You can bake that in, you can use other forms instead of data. And maybe we'll figure out that there are more efficient ways to transfer knowledge from what we know to the models we are building. I think that is a pretty rich direction, and I think connects to what Jeff says. There are many problems where the data is very scarce, and we need to address that in a perhaps different way.
I have a very similar, I thought about when I was thinking about this, I had very similar conclusion as Jeff. Like after 20 years, it's 2045, I'm not still, I haven't retired yet, so I should be writing a paper still. And we have maybe solved everything. Self-driving car is working, and we have battery issue released and energy density increased, so battery drone is working 10 hours from a single charge if that's happening. And a simulator with the robot foundation model or whatever, and then we can do everyday daily task with robots easily. Then if that's the case, what should I be working on? And then what should I work on to write a paper? And then I thought about the underwater robot, because like in the past, 20 years ago, when I was working on underwater, it was super hard. Like as there's a camera images, it's really turbid, and I can't really see what I'm seeing right now, but I have to do SLAM somehow. So what I want to say is, I think even if we solve most of the problem, I'm worried that still we might not be able to solve most critical problem, and those critical problem might be related to most dangerous or most tedious, most painful job for human, and robots are doing easy jobs and humans are doing hard jobs. So that was my concern and worry. So I think toward that future direction, I'll probably work on those corner problems where like civil engineering or construction site or underwater, like deep sea navigation. I want to still work on that part a little bit. That was my kind of conclusion.
Okay, so I'm not brave enough to make predictions for 2045, unlike my fellow panelists. I don't want to be held up accountable for that. But I will say that I would like to see certain things change about our research community when we get to that point, all right? So I'm a computer scientist, so I'm in the CS department. How many other CS people here? Yeah, just curious. Okay, CS, a whole bunch of you. How many ME people, mechanical engineers? Okay. How many others? Physicists, biologists, a few others? Ah, okay. So how many roboticists? So I think robotics has matured as a field. Why are we still stuck in these silos? And this goes back to what Fabio was saying about how our students sometimes, it's harmful for students when we all put in these silos. I think there's a lot of shared knowledge, shared vocabulary, shared understanding that sometimes our students have to piece together because they are in particular departments and they gather this from various sources. I hope that by that time we're all in robotics departments. I know that it's hard and stuff like that, but it would be nice if we all had robotics departments that we call home. All right, that's one more structural change I would like to see by 2045. The other is a little bit, again, related to what Fabio was saying about robots that help grandma. So if you look at the way we are structuring our models now, we're very object-centric to a degree, or task-centric to a degree. I think we should be more human-centric if we want robots that help people. And I think that we can't tag on the human aspect as an afterthought, right? Every time we try to treat people like objects, that's when things go wrong. And that's what we're doing now. So I hope that you start thinking more about the human part of the system. And that's really, really important. I hope that we get that figured out by 2045.
So the panel really warmed up, and as a result, we've actually hit our time. So I just want to wrap it up a little bit. So the panel, every person on the panel could speak about this topic for hours by themselves. And so they were lured onto the panel with the promise of this starting conversations, but not finishing them. The conversations will be continued throughout the week. You can talk to the panelists, but you can also talk to your colleagues as well about some of the topics that have arisen. And before I thank the panel one final time and let you go, I will remind you that the coffee break is now. You need to be back here at 4:30 for the humanoid session. Thank you to the organizers, and thank you to our amazing panel.
All right, we're going to get started with the next session, so please have a seat. So the next session is humanoids, and I'm going to be a session co-chair. My name is Bomjun Kim, and I'm from KAIST.
And I'm Tucker Hermans from the University of Utah, and we're going to go ahead and get started with our first paper, AMO, Adaptive Motion Optimization for Hyperdexterous Humanoid Whole Body Control. And presenting, we'll have Zhujin Sheng.
Hi everyone, I'm Shuxing, and today I'm presenting AMO, Adaptive Motion Optimization for Hyperdexterous Humanoid Whole Body Control. Humans naturally utilize all degrees of freedoms with whole body movements to expand their workspaces. Now we have high degree of freedom humanoid, we should be able to do the same. However, the kinematic potential is not fully utilized. For example, prior works show limited upper and lower body coordination with less movements for the torso and waist. How to enable full kinematic range of humanoid robots like this, like picking up something from the ground. Well, current motion imitation frameworks face two challenges. The first one is the dataset distribution bias. For example, we visualize the marginal distribution of CMU mocap dataset for the torso orientation. The pitch angle barely surpasses like 30 degrees, and the base height is barely below 0.8 meters. The second challenge is the requirement of motion trajectory during deployment. You can see the different control modes from a previous work covered. The key points are more or less needed during the deployment process. We propose AMO, a framework that enables the full kinematic range control for humanoid robots. First, we curated hybrid datasets from both human motion capture and uniformly sampled torso commands to overcome the data distribution challenge. Next, we use trajectory optimization to get whole body reference motions. Then we train an AMO network to predict the lower body reference motions from upper body commands. This provides us with an out-of-distribution capability and fast online inference speed. The AMO network is subsequently using RL training phase to provide reference motions. The trained WBC policy can then be readily used for downstream tasks such as whole body teleoperation. After we collect data with the teleoperation interface, we can use them for imitation learning and autonomous execution. AMO substantially expands the humanoid workspace, especially when there's a need for like collaboration for multiple motors. For example, the range of waist pitch motor is like very small, like 30 degrees, but AMO can utilize the hip movement to achieve a larger range, like 90 degrees. AMO also outperforms other baselines significantly in terms of the maximum kinematic range. For example, the pure waist tracking does not utilize all motors, and mocap imitation focuses on faces dataset distribution bias. We also want to highlight AMO's ability to track out-of-distribution targets. The gray area is basically out of training distribution, and AMO is still able to track it. For example, the height tracking can go all the way down to like 0.4 meters, and the pitch tracking can go over 90 degrees. And here's a brief demo video showing like all the teleoperated like AMO controller in the real world. So basically, without AMO, you can't pick up something from the ground. Here, I also want to highlight that the robot will be like using the right hand to pick up something and place it in the bottom left. So this is also not possible without like the full kinematic range whole body controller. And apart from like standing in place and do all these kind of whole body motions, the robot can also pick up something and do locomotion, such as walking. the robot is also capable of walking, here all with a single policy. And our models are all open sourced on GitHub. If you want to give it a try, you're welcome to do that. Thank you. Any questions? Okay.
On the ground floor over here.
Hey, thanks a lot for the presentation. I had a question on how do you think about this posture optimization when you have very heavy payloads that you're trying to pick off the ground?
Sorry, I didn't quite get it.
When the robot is trying to pick or interact with some very heavy dynamic objects, how do you think this posture optimization will work?
You mean very heavy objects?
Like
So
a dumbbell of like 5 kilos.
Okay, so currently I think the trajectory optimization only serves as like a reference motion, and if you want heavy things, you can just add that with the RL process.
Okay.
Have time for one other short question.
Okay.
I'll just maybe ask if you could briefly talk about limitations of your approach.
Of course. So as the gentleman mentioned, there's a lack of like force related manipulation. So currently it's more like you have to reach somewhere, but you don't really want the robots to be engaged with like any like force constrained environment, like opening a door or opening a cabinet or a drawer or something like that. So yeah.
All right, let's give a round of applause for the speaker.
Thank you.
Next, we have a demonstrating Berkeley humanoid light by Yufeng Qi.
Hello, everyone. I'm Yufeng Qi, and I'm here to present our work on demonstrating Berkeley humanoid light. So we think that humanoid robots, they should not be budget black boxes and budget busters. However, currently, they're still very costly and poses a very high barrier of entry. Current solutions are either commercially available platforms, but those are expensive and closed source. The high price tags are simply out of reach for most research labs and hobbyists. To make things worse, when things breaks down, the users just cannot repair on their own. There are also many awesome open source research projects out there, but they require specialized fabrication tools to build, including getting access to those advanced CNC machines and making customized PCBs. So to address this issue, we present Berkeley Humanoid Light. It is a 3D printed humanoid robot that is designed to be accessible, customizable, and fully open source. Firstly, for accessibility, we choose broadly available parts from major online vendors available in multiple countries. Also, we made careful selections to use the lowest price parts while still achieving the desired performance of the robot. All the structural components can be 3D printed on a normal desktop 3D printer. We also use cyclodal gearbox designs with additional reinforcements, including through screws and embedded hex stints to support higher load capability. Apart from accessibility, the robot is also designed to be highly customizable. The modular actuators can be modified to form different robot morphologies to suit different kind of research needs. And the daisy chaining of the actuators also allow flexibilities on reconfiguring the link length and joint ordering of the robot. All the software code base and CAD design files are fully open source, along with documentations and detailed guides to help users get started. By sharing all the resources we have, we hope to help democratize access to humanoid robots, as well as help innovations in this field. Everything can be accessed on our project website. So for actuator evaluation, we perform a series of experiments. We have measured around 90% mechanical efficiency across most operation conditions of the actuator and a transmission stiffness of around 320 newton-meters per rad. The performance is pretty stable over our 60-hour-long durability test, and also we measured around 0.5 newton-meters of variation in torque output across actuators printed on different printers. We also evaluate the position tracking capability by assembling the actuators into a 5 degrees of freedom robot arm. The arm is commanded to reach to 4 different spatial locations, repeated 100 times, and we are able to measure around 3.5 millimeters in standard deviation on the positional consistency. For the demonstration experiments, the robot is able to perform teleoperated manipulation tasks, including playing with a Rubik's Cube, writing its own names, picking blocks into a container, as well as some basic locomotion tasks following a user's commanded velocity. So one of the major limitations in our work is the insufficient study on thermal effects during those prolonged operations. Specifically, we observed that during the high torque and high speed conditions in our actuator evaluations, the PLA plastic on these cycloidal gear teeth tends to melt, breaking the actuator. Yeah, and thanks. With all that, I'm now glad to take any questions.
One on the bottom floor, right here.
Why all 3D printed, given that like there's like really cheap sheet metal manufacturing places? Like if you get like 10 people together, maybe you can get a CNC machine. Like why so insistent on 3D printing everything?
Yeah, so we think that 3D printing is still like one of the most accessible way that to make the robot. Basically, you just need to buy a small normal 3D printer and put it in your workshop or even in your home, and then you'll be able to create all these different morphologies of the robot. And for the sheet metal and stuff, you still need to reach out to manufacturers to so it's a bit more complicated process.
And we have time for one more question. If not, I have one. What's the maximum torque, peak torque, and the velocity of the actuator?
Yeah, so the robot has 2 different sized actuators. The larger one is maximum 20 newton meters, and the smaller one is 15 newton meters. And the maximum velocity, I kind of forgot, but it's on our poster during the poster and demonstration session, so feel free to drop by and see what's the velocity. Yeah.
Wonderful. Let's thank the speaker.
Thank you.
And our next talk will be on learning getting up policies, presented by Xiaolin Hin and Runpei Dong.
Okay. Hello, everyone. I'm Xiaolin He, and this is Runpei Dong. We are glad to be here to present our work, Learning Getting Up Policies for Real-World Humanoid Robots. This work tackles the problem of fall recovery of humanoid robots, which is a very important task because humanoid can easily fall. Our humanoid can enable a humanoid to get up from various poses, like supine poses as shown on the left video, and prone poses as shown on the right. Our humanoid can also generalize across diverse terrains, including concrete paths, muddy grass, brick surface, grass slope, and also stone tile. Why is getting up different? First, unlike locomotion tasks, that is periodic, getting up do not have a periodic pattern. Second, getting up involves complex contact pattern which involves the whole body. Third, unlike locomotion tasks, motion reference aren't readily available and are hard to handcraft. In order to solve this problem, the most straightforward method is end-to-end reinforcement learning. but that is too time-consuming on the reward tuning. Our human up is a two-stage design, where the first stage is a motion discovery stage, and the second stage is a sim-to-real tracking stage. In stage 1, we train a policy with minimum regularization to discover a get-up motion without being hindered by torque and velocity limits. And in stage 2, we track the motion discovered in stage 1 while adhering real-world constraints of smoothness, torque, velocity limits, and generalized across poses and terrains. In our two-stage reinforcement learning design, we have 3 key curriculums. First, we switch to full collision meshes. Second, we randomize initial postures of the robot. And third, we use stronger control regularization. Together, they form a dual curriculum where the task gets easier from getting up to tracking, and the control regularization gets harder, which we can ensure robust humanoid control. Let's go.
Okay, now let's talk about some experimental results. We start by looking at stage 1 and stage 2's motions. Stage 1's motion is fast and unsafe. And in comparison, stage 2's motion is both slower and safer. Furthermore, this two-stage IL breakdown is necessary. Single-stage reinforcement learning with full regularization fails. The policy only learns to raise the torso because of the strong sim-to-real constraints that limit the robot. Moving on to real-world results, here are rollouts of our policies in the real world. We compare HumanUp to Unitrace built-in controller. Unitrace built-in controller follows a three-phase design. It first resets to a canonical pose, then transitions into a squat, and finally stands up, taking about 11 seconds. In contrast, our HumanUp learns a continuous motion that is faster, taking only 6 seconds. Furthermore, our motion is also safer as it relies more on the stronger lower body. It minimally hits more fragile arm motors. Here is a video comparison. You can see that the Unitrace built-in controller fails to transition from lying down to squat on a sloping rough terrain. In quantitative real-world experiments across 6 different terrains, we find that HumanUp consistently outperforms the Unitrace built-in controller and ambulation without post-randomization. To summarize, we present HumanUp, a two-stage RL framework with corrective learning for solving challenging whole-body control problems. HumanUp enables human robots to get out from various initial poses and generalize to various terrains. Please check out our project page for code, videos, and additional results. We are happy to take any questions, and thanks a lot for your attention. Any questions?
Right here in the middle, on the ground floor.
Thank you for the presentation. Can you elaborate more on how you defined the safety and whether the controller was safer than the other one?
Yeah, so the safety actually can be considered across various aspects. The first one is about the motion smoothness. The motion should be smooth without any jiggling or something like that. Also, the motion shouldn't be too fast. It will cause the torques to be too large, and also the dove velocity and dove acceleration will be also too large. So basically, you have to measure from several aspects to ensure the robot is safe to deploy. Yeah.
Okay, right here. Let's try to make it brief.
Thanks. How much did you have to tune the regularizer that you used in your method? What kind, did it work out of the box, or did you have to spend some effort tuning the regularizers?
Are you talking about reward tuning things?
Yeah.
Okay, so because we decouple the problem into 2 stages, the first stage is solving the task. The reward tuning is not that difficult because we have not that hard sim-to-real constraints. And the second stage is about tracking. And tracking with reinforcement learning is relatively easy, so we don't actually need a lot of reward tuning in this work. It's typically very easy and trained very fast. Yeah.
Thanks.
All right, let's thank the speakers. Next, we have yet another humanoid stand-up policy learning paper, but unfortunately, speakers couldn't make it here, so we're gonna play a pre-recorded video, and there's gonna be no Q&A.
Hi everyone, this is Tao Huang. I represent our paper, Learning Humanoid Stand-Up Control Across Diverse Postures. Stand-up control is a basic but important task for humanoid robots. In locomotion, it enables recovery from falls to long-term stability. In local manipulation, it's essential for resuming interaction after posture changes. Existing model-based optimization can plan feasible stand-up motions, but it's often computationally expensive and sensitive to model inaccuracies, limiting real-time use. Reinforcement learning offers a more flexible alternative with minor modeling assumptions. However, existing methods face key limitations such as ignoring hardware constraints, relying on prior motion data, handling ground-only postures, unclear transferability to other robots. To address these issues, we propose HOST, a general IO framework for generalized, robust, and stable humanoid stand-up control. Let's get started from a standard RL framework. The first challenge is the burden of reward engineering and the difficulty of policy optimization, especially when multiple rewards conflict with each other. To address this, we adopt a multi-critic RL framework. We group the rewards into 4 categories: task, style, regularization, and post-task reward. Each group is assigned an independent critic to estimate its expected return. The final value function is then aggregated from these individual critics, enabling more effective balance over diverse reward functions. The second challenge is that the learned policies often produce violent and oscillatory motions, which are undesirable for hardware. To reduce violent motions, we apply action rescaling to bound PT targets at each control step, effectively limiting motion speed. To smooth out motion oscillations, we adopt L2C2 regularization, which encourages smooth outputs from both the critic and policy networks. This significantly improves hardware stability. The third challenge is the trade-off between exploration and motion constraints. Tighter constraints improve safety but limit exploration, while looser ones allow risky motions. To address this, we apply a curriculum on action rescaling, starting with the loose PD bonds to encourage exploration and gradually tightening them. Besides, we apply a vertical pulling force on the robot during early training stage to ease the standing up difficulty. The idea is inspired by developmental studies where parents' support help infants learn to stand up more quickly and stably. The fourth challenge is twofold: handling diverse real-world postures and bridging the sim-to-real gap. To cover posture diversity, we designed some simulation terrains for training. To overcome sim-to-real gap, we apply domain randomization techniques. After training and simulation, our policy can transfer directly to the real robot with no fine-tuning. Next, we showcase results on Unity G1, highlighting its generalization, robustness, and stability. In outdoor environments, the robot reliably stands up from wooden floors, platforms, or even uneven stone roads. At one point, it lay under a tree like Newton, stood up to check for falling apples. Not sure if any apple fell, but at least the robot did not. We also test indoors, lying, slopes, and sofas, reclining and sitting in various chairs. In all cases, the robot stood up smoothly and reliably. We test various ground postures, supine, prone, and side lying. In all cases, the robot stood up stably and smoothly as well. We further tested robustness and stability. The robot can balance on 15-degree slippery slope, recover from sudden falls, stand up with a 10-kilogram payload, and resist against friendly external pushes by me. We have open-sourced the full code base, making it accessible to the broader research. Beyond the code, we also actively share tuning practice and development insights with robotics companies and the research lab working to adapt HOST to their own robots. With minor modifications, HOST has been successfully applied to humanoid robots of varying size and designs, helping lower the barrier to real-world stand-up control. However, we still observe a noticeable sim-to-real gap when deploying on large-sized humanoid robots. We believe this highlights the need for further improvements in both hardware and algorithmic design. Bridging this gap remains an important direction for future work. As a summary and takeaway, we present HOST, a general IO framework for generalized, robust, and stable humanoid stand-up control. And finally, after so many days and nights of hard work, we took our robot to watch the sunrise together. In that quiet moment, I was really moved. I couldn't help but give a robot a warm hug. I believe that humans and humanoid robots can share more than just data and control. We can share efforts, tears, and flowers. That's all. This is Tao Huang for the presentation. Welcome to our post for more discussions. Thank you for your attention.
All right, our next talk will be on language-guided whole-body control, and presenting will be Jiayou Huang.
So, hi everyone, I'm Xiaoyu Huang, and I'm a PhD student from UC Berkeley. I'm honored to present language-directed humanoid whole body control via end-to-end learning. So, what's the motivation of LangWBC? In previous works, universal motion tracking controllers mostly solves an inverse dynamics problem of reaching to some desired poses given some next frame prediction. However, due to artifacts in those desired poses, it often results in jitters, limiting agile motions. On the other hand, we can directly leverage generative models to model a diverse, dynamically feasible agile motion distribution directly. However, they are limited to simulation in prior works. Can we model the distribution of real-world humanoid whole body control with a generative model as well? On top of this, could we model not only motions, but also the joint distribution of whole body motions and natural languages all within one same model? The answer is yes. In LangWBC, we show agile whole body control for real-world humanoid robot with diverse language commands, smooth transitions, and novel motion generation via language interpolation. Our method consists of 3 stages. First, we utilize mocap datasets and retarget them into robot-specific motions, along with text captions. Second, we learn language-agnostic teacher policies with deep mimic-style rewards that's able to track these motions accurately to form the dynamically feasible motion distribution that the student policy will learn from. Third, the most important part is student learning, where we use a clip encoder and a conditional variational autoencoder to model the joint distribution of language commands and state action pairs from the teacher policies. By pairing text commands with the teachers, this step learns a unified structured latent space, leading to natural language understanding of the associated whole body motions. Notice that because we simultaneously swap out the input from privileged states in the teacher policies to the real-world observations that is used in the student policies, we highlight that LangWBC requires no extra training stages from teacher-student framework in order to do sim-to-real transfer. After training, the student policy can perform a diverse set of language commands in the real world. We also show smooth transitions between challenging agile motions, such as walking to running, and then finally to standing. And also turning around continuously, which requires a strong skill to balance its body. LangWBC is also robust to variations in languages for semantically similar unseen commands. For example, walking forwards versus moving forwards. Importantly, we highlight the capacity of novel motion generation as a direct benefit of the structured latent space. By directly interpolating 2 text commands, walking forward and walking sideways, the policy generates a novel motion of walking diagonally that is unseen in training distribution. Finally, LangWBC is robust to external perturbations, and also, thanks to the intuitive language interface, it can be directly integrated with LLMs to incorporate reasoning for downstream tasks. So that's the end of my presentation. Welcome to visit our poster at 24, and thank you very much.
Please raise your hand if you have a question.
I'll ask a question. Okay. Why did you use a clip model to make the embedding? Because clip model is typically used to align the images and the text? It seems like an odd choice in this example.
We use the clip model as a general encoder for the text input, but it can be replaced by any other model as well. Yes.
How big is the vocabulary?
The vocabulary, it's a continuous latent space, and the hidden dimension is 256 hidden. Oh, how many different motions? It covers up to 100 motions, around 100 motions. Yes. I also have a latent space analysis on the poster, and that's pretty nice to watch at.
All right, let's thank the speaker.
Thank you guys very much.
Next, we have ASAP, Aligning Simulation and Real-World Physics for Learning Humanoid Whole Body Skills by Tyron Hay.
All right, let's get started. Hello, everyone. I'm Tyron, a robotics PhD student from Carnegie Mellon. Today, I'm happy to present you our paper, ASAP, Aligning Simulation and Real-World Physics for Learning Agile Humanoid Whole Body Skills. So sim-to-real reinforcement learning is making amazing progress for humanoid control. We are now seeing these impressive demos from Unitree, from Boston Dynamics. And for today's humanoid session, we have 10 papers in total, and 9 out of 10 papers are doing sim-to-real RL for humanoid control. So how does sim-to-real RL work? It usually starts with a largely parallelable simulated environments. We have the robot imported, we define the real-world function, and we let the RL cook. And then we have this sweet and smooth sim-to-real transfer. Unfortunately, that's not the case. Oftentimes, what we end up is something like this. Policy that performs greatly in the simulation performs very badly in the real world. Sim-to-real RL does not work out of box. So how do people usually solve this sim-to-real transfer? One option is domain randomization. The idea behind domain randomization is basically saying that, okay, we know all models are wrong, but let's train our policy on as many wrong models as possible to robustify the policy. It works empirically very well for our test. And the other option is called system identification. The idea is, okay, we know our current model is wrong. Let's find the better simulated parameters to match the physics of the real world. If you take a closer look at both methods, you'll find the underlying key is models. So in this paper, the core research question we aim to answer is it possible, or can we learn a correct model, better model, with reinforcement learning from real-world robotic experience? Introducing ASAP, Aligning Simulation and Real-World Physics. We start with pre-training motion tracking policy, and then we deploy them in the real world to do data collection. Here's pre-training. This is me doing Cristiano Ronaldo's jump, and then we do post-estimation on the video that I recorded. This is the post-estimation. Then we train our RL controller to clean the motion from post-estimation. Then we do kinematic-based motion retargeting to get humanoid motion. Then we train another RL controller to track that humanoid motion. Finally, we deploy it in the real world. From me doing that to the humanoid doing the exact same thing. The story does not end here. We have the policy. We deploy it in the real world. We don't want to waste it. We collect every state and action transition in the real world data collection, and we play back the action we took in the real world back to simulation. So the resulted simulated states and real world states are going to be different. Therefore, we define a reward measuring the gap between simulated states and real-world states. And we train our RL-based delta action model to match the simulator with the real-world states. Here, we visualize the magnitude of the RL-based delta action model. The bigger the red dots are, the bigger the magnitude of the delta action is. You can see, to better align the sim-to-real gap, the delta action model learns the largest magnitude for the knee and ankle joints. But that's not our goal, right? Our goal is not to get a delta action model. Our goal is to get a policy that works better in the real world. So what we did instead is we freeze the delta action model, we zip it with the simulator to form a new hybrid simulator, and we fine-tune out the policy with that hybrid aligned simulator. The good thing about this fine-tuning is that the whole point of us training this delta action model is to make the hybrid simulator better match the real-world physics. And finally, We deploy the policy in the real world without any delta action model because the real world physics does not need to be aligned for. Now you're seeing that the policy before and after fine-tuning. On the left, that's the policy for pre-training, and on the right, you are seeing the policy doing the exact same motion. After fine-tuning, you'll find more elegance and smoothness. In summary, we present a new sim-to-real method beyond domain randomization and system identification by training an RL-based delta action model to better match the physics between simulation and the real world. We have open sourced the training code, so you should be able to train your humanoid doing the Cristiano Ronaldo's move within 2 hours. And I think there are a lot of interesting questions to be answered in the future. That's my presentation, and I'm happy to take your questions.
Hi, thanks for the really great talk. My question is, how much data do you have to collect in the real world?
In the real world, we collect around 200 episodes. That's around, I don't remember the exact numbers, but it's around 200 episodes. For each episode, it's around 5 to 10 seconds.
Hi, thanks for the great work. Actually, I'm wondering, when would you release the full training code for ASAP?
The training code is fully open sourced. The delta action model is not yet, but I think it'll be very quick. I'm cleaning the code base right now.
Oh, thank you.
Yeah, thank you so much.
At the back.
This is working? Oh, perfect. Why did you choose to collect data with the policy and not in traditional manner that you just randomly shake the robot and try to fit a model on it to do a system identification?
Okay, so yeah, I think to do that, we have very good work, things like actuator.net, doing very great. So I think for here, we're basically trying to challenge the, so we're saying that I don't think.
Let's take this offline for the sake of time.
Okay, cool.
Let's thank the speaker. Our next speaker is going to be Wentao Dong, who will also be presenting on whole body control, this time on fine-grained locomotion.
Hello, everyone. I'm Wentao from Shanghai Jiao Tong University. It's my pleasure to present our paper, HugWBC, a unified and general humanoid whole body controller for versatile locomotion. It's a co-work with Yufei, Minghuan, Weinan, and Jiang Miao. Recent advances in humanoid robotics have shown remarkable progress in motion tracking and terrain adaptabilities. However, these methods are designed primarily for the tracking some omni-goals or trying to complete some Parker tasks with only velocity commands. Based on this performance, we raise these 3 questions. How to command versatile locomotion behaviors, how to make the movements more nature, and can we support local manipulations? Here, we introduce HugWBC, a whole body controller designed to support a wide range of humanoid behaviors. It enables the robots to change between gaits, it can adjust its body postures, and it can even complete hopping gait. Besides that, we use the combination of our locomotion commands with the upper body intervention to show some whole body behaviors of the robots. You can see for the left, the robot can box in with whole body, and for the right, it is complete a local manipulation tasks. Here is the key designs in HugWBC. It's extended command spaces, which including 3 parts: task command, behavior commands, and intervention. For the task command, it adjusts the velocity commands. For the behavior, it includes foot posture and gaze. As for the intervention, we use an indicator to facilitate for the upper body interventions. When default, the controller operates as a whole body controller for nature movements. When the indicator is activated, we will decouple the upper bodies for the external control signals, while the lower body is still working on the keeping balance with the locomotion tasks. And here's a key component for training nature gaits. We use the phi, the phase variable, and we define the contact probability function C phi to to replace the rigid step functions. With such a smooth transition between step and on the ground, we define the context swing rewards and foot trajectory rewards. This guides the robots when to move the foot and how to swing the foot. During the training, we incorporate asymmetry laws. We use the mirror function F that maps the observation and actions. As you can see, if the observation is mirrored, the output actions should be mirrored. So with that, and we use the asymmetric actor-critic framework as well. Here is the intervention curriculum training paths. We use the curriculum training for the noise with a mixing of the original policy outputs actions. And the noise samples is the noise with 2/3 parts of moving and 1/3 parts of stationary. We've tested the effect of this intervention training through the commands tracking evaluation on the various types of external disturbances. Tracking error is measured as average deviation across command sweeps, with all the terms remaining held as constant. The results demonstrate that intervention training accurates the command following performance. And finally, by measuring the foot displacement under the posture commands while standing gait, we show that the policy achieves better stability. In push recovery tests, it demonstrates it has improved robustness as well. In conclusion, it is a general low-level controller with extended command space, and it supports upper body intervention. And the code is available now at the website. Thank you. That's all. Thank you for your attention.
Okay. Any questions? So maybe I'll ask one. You had a lot of loss terms and reward terms.
Yes.
And you talked a little bit about that, but can you say which one you think was like the most important in the end?
I think the reward terms, right? I think the reward terms we showed before is the context swing rewards. It shows when you should raise your foot and when you can put your feet on the ground. With such rewards, it defines the gait patterns for the robots. And this makes the robot move nature and as you expected. I think that's the crucial reward in our project.
Okay. Let's thank Wentao.
Okay, next up we have Beam Dojo, learning agile humanoid locomotion on sparse footholds, and this is going to be a pre-recorded talk.
Hello everyone, this is Huai Wang from Shanghai AI Laboratory. This presentation is pre-recorded using a synthesized voice, as I'm currently unable to attend in person. I'm excited to present our work Beam Dojo, learning agile humanoid locomotion on sparse footholds. Recent advances in learning-based humanoid locomotion have shown impressive robustness across tasks like walking, stair climbing, and parkour. However, these methods still struggle with complex terrains and agile locomotion on fine-grained footholds. While similar challenges have been tackled successfully in quadrupedal locomotion, transferring these methods to humanoids is non-trivial, primarily due to different foot geometry and unstable morphology of humanoid robots. So, what makes humanoid locomotion on sparse footholds hard? First, sparse rewards for correct foot placement, making credit assignment difficult across the full stepping sequence. Second, inefficient learning process, largely due to frequent missteps that cause early termination. What's more, the perception is also a challenge to accurately sense sparse terrains. To address these, we propose Beam Dojo, the first learning-based approach that enables humanoids to precisely control foot placement on sparse footholds. The core idea of Beam Dojo is Don't let a misstep mean failure. We do this by mapping the complex task terrain to a flat training terrain. During training, the humanoid walks on this flat terrain, but it receives perceptual inputs as if it were on the real task terrain. You can think of it as imagining walking on the real terrain. This decouples the observation space, where the task terrain provides elevation map and the sampling-based foothold reward, which is computed from the contact area between the foot and the stone. We introduce the double critic module to separately learn dense locomotion rewards and this sparse foothold reward, and then their predicted values are combined to update the policy. In stage 2, we transfer the learned policy to the real task terrain and fine-tune it. The actor and double critics are directly copied from stage 1. For real-world deployment, we use the Unitree G1 humanoid, equipped with a Livox MID 360 LiDAR on the head. To generate reliable elevation maps, we leverage FastLIO for odometry and robot-centric elevation mapping to sample terrain points. We use a 15 by 15 grid at 0.1 m resolution, updated at 10 Hz. Then zero-shot sim-to-real transfer is achieved. The humanoid can walk on the real terrain without retraining. In simulation, we run some ablations. Compared to baselines without stage 1 training or without the double critic module, our method shows more accurate foot placement and faster learning. Here is the real-world demonstration. Our humanoid robot walks both forward and backward across a challenging terrain that includes randomly placed stepping stones, narrow balance beams, and gaps, executing each step with precise foot placement. The stepping stones are 20 centimeters wide with a maximum spacing of 45 centimeters. The balance beam is 20 centimeters in width, and the gap spans 50 centimeters. We even test under external disturbances and 6 kilograms payloads, and the robot still completes the task robustly. You can find more details in our paper and website, and we welcome you to visit our poster session. Thank you.
Our next presentation will be on GateNet, and it will be presented by Junhang Lee with the help of some colleagues.
Hey guys. All right, good morning, good afternoon, everyone. My name is Junhang. I'm from University of Southern California. Today, I will present our work on GateNet MPC for variable frequencies humanoid locomotion. All right. So one of the main locomotion capability of human is the ability to adapt to different stepping strategies in different kind of scenarios, such as with constrained foothold or with any external disturbances. Right. The current model-based optimization-based control techniques has two extremes. For reduced order dynamics model, is intentionally ignore the highly nonlinear terms, and therefore, with full order models, it retains the highly dynamic, high fidelity kinematics and dynamics coupling, but with a compromise of solution accuracy with online execution, right? So even this very nice stepping behaviors on the MIT robot is a fixed gate frequency. And then the problem really becomes how to maintain the two, right? High fidelity kinematic dynamics coupling in gate adaptation and while using a reduced order model for speed for online execution, right? So here is what we propose, a hierarchical model-based control framework. At the mid-level, we propose a GateNet augmented MPC that can optimize the step duration, location, and contact forces all at once, right? So the overall idea is here. With a whole body dynamics, we can have a very high fidelity model, but on the opposite side, we have the centroidal dynamics. Although a very good abstraction of the whole body dynamics, it does not really enforce any kinematics or dynamics coupling of the step durations or the step location. On the other hand, the whole body dynamics addresses very well, so that's why you see a lot of these contact implicit method that use whole body dynamics, right? So with this, we construct a model whole body MPC with variable step durations and throw in my simulation and collect a bunch of different data and to relay the state information to the step durations, right? So this way, we don't need to really solve this very heavy whole body MPC in real time. Instead, we learn a gate network to capture this abstract decision-making process of the gate decisions, right? We then use a neural network to condense it with PCA loading, and then the inference time is almost instant online. Right? So with this, the net prediction in terms of MPC DT would then be used into the discretized centroidal dynamics formulation to vary the step duration. And hence, that leaves only the bilinear constraint of full location and the force now, which can be thrown into a SQP solver that we use. Okay? So at the core of this work lies the gate net augmented MPC. There are three main parts of it. So first, the nonlinear MPC problem is linearized at each time step by the search direction QP problem. And then based on the local solutions, the gate net will predict a MPC DT, which will be used to re-update the spatial momentum and the pulse reference trajectories to ensure the kinematic capability, or feasibility in this case. So this synergy will keep going until we find a solution or the convergence of the solution, right? So with this formulation, we can allow a very direct, explicit constraints on the full locations, right? So which works amazingly in these stepping stone terrains, right? So this simulation shows 3D stepping stones, right? And on the hardware side, we use our in-house humanoid, Hector V2. We validated the gate net. The informed gate net decisions is versatile to different disturbances, including these external forces, uneven terrains, and even external load, right? And another great example here is it allows the robot to traverse these virtual gaps or discontinuities of the terrain with synchronized step locations and step durations. We use one-step preview data of the terrain here to demonstrate the effectiveness of this short-term planning and also online real-time control. And another example here is the terrain with small obstacles and also gaps. And the gate net can also be accommodated such obstacles avoidance cases when extending to 3D. So I guess with that said, that's pretty much for the talk. I'm happy to answer any questions. Thank you. Oh, and I have a little surprise here. Yeah, this is our Hector. Wearing a short hat. So a little small
The back here. On the ground floor, right here. Go ahead and shout it.
Hi. How easy is it to extend this technique when these robots start to carry loads? Do you need to model like a disturbance, or you have to change the inertial properties of your robot? Because CG will change, and you have to. Do you need to change your formulation or something like?
We can actually just let different or randomize a different loads for the robot to carry, and then that should be able to inform the gate net to be more robust to these different kind of loads. Yep. Any other questions?
Okay. Well, let's thank the speaker again, and
thank you
for an awesome live demo.
All right, next up is Homie, humanoid local manipulation with isomorphic exoskeleton cockpit. And this is going to be a pre-recorded talk as well.
Hi, everyone. I am here to introduce Homie, humanoid local manipulation with isomorphic exoskeleton cockpit. Homie is a novel humanoid teleoperation cockpit integrates a humanoid local manipulation policy and a low-cost exoskeleton-based hardware system. Compared to related works, Homie is very cheap, more precise in arm and hand tracking, and it's the first to support robust humanoid whole-body local manipulation without relying on mocap data, all making teleoperation and data collection much easier. Here is the overview of Homie. As shown in the left, Homie's hardware system includes a model-based isomorphic exoskeleton arm, a pair of Hall sensor-based motion sensing gloves, and a command pedal. Also, Homie has a novel reinforcement learning algorithm enabling robots to stably walk and squat under any upper body poses. Each iteration, operators will see first point of view of robot on the screen, and teleoperate the exoskeleton to give required joint positions for both humanoid arms and hands. Meanwhile, by tapping the pedal, locomotion commands will be given to the L-train policy, which then control the robot to perform local manipulation tasks. In this process, data will be collected and used by imitation learning algorithms to train autonomous policies later. The isomorphic design of exoskeleton arms makes simple joint matching possible. We just need to set gut angles of motors directly to the robot. Our motion sensing gloves are based on Hall sensors. These sensors are very small, thus we are able to equip each glove with 15 DAF, more than most existing dexterous hands. By mapping glove joints to hand joints, operators can teleoperate different dexterous hands with only one pair of gloves. Here is a simple description of our pedal design. Our experiments show that our low-cost hardware system has high joint acquisition frequency and accuracy. Thanks to the isomorphic design, we can directly set the gut values of motors and sensors to robots' joints. Thus, our teleoperation system doesn't need any chips for computation and can give required upper body poses at a high frequency over 200 Hz. This is the framework of our reinforcement learning-based algorithm. We design a curriculum to help robots better balance under changing upper body poses. Initially, the joints are set to the default position with a high probability, and the difficulty gradually increases until the workspace is visited with equal probability. Before, policies can't afford stable capability to squat to any required heights. We design a heuristic height tracking reward, which significantly helps humanoids learn to squat. We also utilize the symmetry of humanoid robots to both ensure symmetry outputs of the train policy and accelerate the training process. Ablation experiments show that all these three introduces techniques help to better train the humanoid robots to robustly walk and squat under any upper body poses, with a much faster training process, less tracking errors, and more symmetry actions. On the 4 tested tasks, our system uses only about half time to complete compared to VR-based methods like Open Television. Here is a demo to show teleoperation tasks achieved by Homie. Combining the train policy and the cockpit, our system enables a single operator to achieve full control of humanoids and perform diverse local manipulation tasks faster than other systems, with upper body controlling the exoskeleton while lower body pedaling. The policy enables the robot to keep balance even under strong external disturbances, such as heavy hitting, which helps the robot to perform tasks in complex situations.
We further transfer our policies to ISOCSIM and use the cockpit to control robots within a variety of simulated environments.
Here are QR codes of Homie, and it's fully open source. Thanks for your attention.
All right, that was the last talk of our session, but stay tuned because we're going to immediately switch to the next section.
Start now? Okay. Hello, everyone. Welcome to the next session, session 8. Imitation Learning 1. My name is Dan Fei, I'm Assistant Professor at Georgia Tech, joined by...
My name is Han, Assistant Professor at Harvard University.
All right, we're going to be the co-chairs for this session. And we'll have our first paper, curating demonstrations using online experience, presented by Annie Shen and Alec Lesson. Let's welcome the speaker. Let's start.
Hi, everyone. I'm Annie, and this is Alec. We're from Stanford University, and today we're excited to talk about our work on curating demonstrations using online experience. So robot policies that have been trained or post-trained with imitation learning often struggle to achieve high reliability, even given lots of demonstrations. Why is this the case? Well, one contributing reason is that as our data sets scale, they naturally contain a wide range of different strategies, and not all of these are easily replicable by the robot. And so curating this data might be really helpful. And in this work, we look at the question of how do we automatically identify high-quality data, specifically data that contains reliable strategies. And so a strategy might be unreliable for multiple reasons. It might be brittle. It might not be well represented in the data. And it might lead to more partial observability from the robot's perspective or require memory. And so if we take a look at some examples, with this task of the spoon picking up on the left strategy A versus strategy B, in the middle versus on the edge, which strategy is more reliable for the robot to use? It's hard to tell. And same thing with this task of the strawberry picking up from the top or picking up from the side. It's difficult to tell at first glance which strategy might be more reliable. But it does matter. And so it's challenging to identify good strategies with manually or with really any offline metric, we argue, because what makes for a reliable strategy might depend on the robot itself. So the key idea that we build off of is that successes and failures in policy rollouts are indicative of how good a strategy is. So we can take our data set with all strategies and train an initial policy on all this data. And this policy will capture all the different strategies in the original data set. And then when we collect rollouts from this policy, that will lead to successes and failures from different strategies. And then we train a classifier to predict rollout success and failure. And if trained well, then this classifier will be able to discern which strategies are more and less reliable. And so we call this process demo score. This classifier can then be used to, in many ways, to filter the original data set and to train a final policy. Now, a problem with this is that we might overfit to rollouts from a particular policy checkpoint, and we want the classifier to be able to generalize to the original demo distribution. And so the way that we go about this is we can use different policy checkpoints for cross-validation. So we train and cross-val the classifier to make it a lot more robust.
So we tested this method on 5 different tasks on an Aloha robot. And despite actually having fewer demonstrations used to train the policy, we find that this curation process improves success rates by around 30%. Additionally, on simulated experiments, we find that demo score outperforms prior methods, such as return condition policies and self-imitation, both of which also use online rollouts as well. More qualitatively, policies trained with all demonstrations, such as the one on the left, will often use unreliable strategies, such as trying to pick up the strawberry from the top, whereas demo score curation leads the policy to use more robust strategies, such as picking up the strawberry from the side. On this jelly bean cup filling task, we use a crowdsourced data set with lots of different strategies from different individuals. The policy trained on all data is unable to complete the task, whereas when we apply demo score curation, the policy is now able to finish the task successfully. So what are the key takeaways? It's often hard to judge what strategies are most reliable in an offline manner, but curating strategy quality can be key to improve policy performance. Demo score does this curation using a small amount of online policy data. This can be viewed as akin to online RL if you think of the classifier as a kind of value function used for demonstration filtering. By training and cross-validating the classifier to predict rollout successes and failures, we can achieve much higher policy performance on real-world and simulated tasks. So please check us out at poster 40 if you want to chat more about this.
Thank you. Any questions? Oh, ground floor.
Hi. Yeah, thanks for the awesome talk. How do you ensure, how does your method ensure it does not throw away trajectories that perhaps didn't perform as well, but still contain like important recovery behaviors to teach your like policy, recover from failure or something?
Yeah, that's a great question. And so first we want to emphasize that like the classifier can be used in a lot of different ways and not just to filter out data. So you can be used to like reweight data, for example, if you don't want to throw away data. And then if we find that if the behavior does lead to successes, like recovery behaviors, then that is something that the classifier will retain. And so those sort of trajectories, even if they might not be totally optimal, if they lead to successes, will actually be retained in the data.
All right. Thank you.
One more quick one. Middle, ground floor.
So I guess one thing that's interesting about this work is that there's like a concept of strategies, like strategies that correspond to successes and failures. Can you share a little bit about what types of strategies that you refer to as this high-level strategy tends to lead to failures, and why do you need to like throw them out?
Yeah, so we find that like especially with large data sets these days collected by a ton of different humans, humans will have just different ways of collecting the data, and it's just difficult for humans who are collecting this data to know what will be reliable or not. And so we found this in our experiments just with different modes of collecting these demonstrations. And some of our experiments also use crowdsourced data where we have like a variety of different people collecting data. And we do find that like filtering out data in this way improves reliability a lot. So there's some trajectories that are more and less reliable depending on how the robot's interacting with the objects.
Okay, let's thank our speaker again. Second paper, Attention-Enhanced Diffusion Policy via VLM-Generated Code for Instruction Ambiguity, presented by Yixuan Wang.
Hi everyone, I'm glad to present our work, Code Diffuser. In this work, we built a system that can steer low-level visual motor policy and align with potentially vague instructions. So language can be ambiguous when specifying the task. For example, for these packing battery tasks, there are 3 batteries to pick from and 6 slots to place. If the instruction is putting 1 battery into a slot, there will be 18 choices. If we are more specific, saying the right battery, there will be 6 choices. For the most specific one, there will be only 1 choice. And similarly, for the hand mark task, the number of choices will be different according to different level of language ambiguities. So how is the current VLA model's steerability under the ambiguous instructions? So if we look at the Octo paper, most of the tasks is obvious enough so that the visual observation only is sufficient. And for the most advanced VLA model, Pile 5, most of the tasks consist of picking up almost everything and put into a slot. So I would say currently there's no systematic evaluation under instructions with ambiguities. So how to steer the visual motor policy? For example, for the hang the blue mark on the left branch task, we are wondering what is a good representation that can bridge the instruction and low-level policy. And in this work, we use code. The code is interpretable and executable, so we use it to bridge the gap. More specifically, we input the instruction into vision language model and generate the code. And the code will interface with the visual foundation model and compute 3D attention map. And then the 3D attention map can highlight the target object and communicate with low-level visual motor policy. And here is a more specific example of our pipeline. So the VLM will take in instruction and generate the code, And first, it will detect 2 marks in the workspace. Because we do not specify the target mark, it will just randomly choose one. And similarly, we can do the same thing for the branch, detect 4 branches and randomly select one. And the final 3D attention map will highlight the target mark and branch and input to the visual motor policy. And the policy, such as diffusion policy, can predict actions and accomplish the task. And here is a more interesting example of a more specific instruction. Hang the blue mark on the left branch. And similarly, we can detect all the marks. But here, we select the blue mark by its semantic meaning. And similarly, for the branch, we can detect all the branches and select the left branch according to its geometric position. And the 3D attention map will highlight the left branch and the blue mark. And the robot policy will accomplish the task according to the instruction. And this highlights that our framework could handle the instructions with different ambiguities. For the results, we first want to highlight that we can handle complicated natural language, even with a lot of contextual description and self-correction structure. Additionally, we can also understand the very fine-grained semantics, such as names on the books. And the left example highlights the Dubai book, and the right example highlights the vintage farmhouse. And because we are using the codes as an intermediate representation, our framework can understand such detailed semantic information to accomplish the task. Geometric information is also important. On the right example, we want to pick up the frontmost battery and put to the right column. And as you can see in this video grid, our robot can accomplish the task aligning with the instruction very well. At last, we want to highlight a lot of our tasks involve context-rich manipulation, such as squeezing the books aside to create the space. And because we are using the learned policy, it's possible now. At last, our framework can work on diverse things and instructions as shown in this grid. And thank you for your attention. Welcome to our poster session for more information, and also welcome to the web demo we have. Thank you.
Any question? Middle, ground floor.
Hi, thank you for giving a great talk. I had a question about if you guys have any thoughts on how to actually use this VLM for inferring the underlying intent for an ambiguous instruction, right? Yeah, do you have any thoughts on that?
Yeah, thanks. That's definitely a great question. I think code generation is still possible because the VLM or LLM has a lot of common sense embedded in it. So, for example, if your description has a lot of contextual description, as we showed before, it can still understand your intention and generate the code that can really interface with the perception APIs and the policy APIs.
Got it. Thank you.
No problem.
One more question. To my left, on the ground floor.
So I saw that you have the instructions, for example, find branch, right? So are you relying on a model that you've trained on to do that reliably, or what does that part look like?
Currently, we are using the visual foundation model. So with this powerful like SAM and Dino V2, we can build the perception tools that can understand the scene very well.
Thank you.
Okay, let's thank our speaker again.
Thank you.
Okay, our next presentation will be, can we detect failures without failure data? Uncertainty-aware runtime failure detection for imitation learning policies. And this will be presented by Chen Xu. Let's welcome our speaker.
It is my pleasure to, It is my pleasure to present our work, Can We Detect Failures Without Failure Data? A certainty-aware runtime failure detection for imitation learning policies. We're motivated to detect when generative imitation learning policies, such as diffusion or flow policies, fail within rollouts. Previous approaches often require failure data collection or sampling multiple actions. However, this method could suffer from overfitting to particular modes or slowing policy inference. In contrast, we want to detect failures using successful demonstrations only. We hereby present fail detect, a two-stage approach. In the first stage, we learn scalar score network DM, which distills each action observation pair from successful data into a real number. In the second stage, we compute scores on successful rollout and calibrate a time-varying decision threshold eta t. During rollout, we sequentially compute the scalar score and detect failures once the score exceeds the threshold at time t. The framework is flexible to incorporating new detectors in the first stage and new threshold designs in the second stage. Specifically, stage 1 learns scores representative of success data. We train the score network on policy inputs and outputs. Inputs OT are image embeddings and robot states, and outputs AT are robot actions. We consider both post hoc and learned score designs, most of which are adapted from original applications. We further propose log-PZO, which models the likelihood of observation embeddings in the latent space. To calibrate decision threshold, we first compute stroke trajectories on a set of successful rollouts using the trained score model. We then construct time-varying threshold by building a one-sided conformal prediction band. During execution, scores on successful rollout, the blue curve, remain below the threshold band for the whole trajectory, whereas we detect a failure when the score in red exceeds the threshold at any moment. We show learned log-PZO score trajectories in red and blue and threshold in shaded blue. There is a clear separation between the two trajectory classes, and most successes lie below threshold, whereas failures lead to spikes. On RoboMimic simulation, fail detect under our log-PZO does not falsely mark successful rollouts and as failures. This ability to control false positive comes from the robustness of log-PZO and the theoretical guarantee of conformal prediction. Meanwhile, we mark detection moments in red borders. Fail detect raises failure alarms during or slightly later than the moments of actual failures in each task, making these detections reasonable and well aligned with human intuition. We show similar behaviors on hardware, where the task is to fold the red towel twice and push it to the table corner. Fail detect does not make false detections when the rollout is successful under both in distribution and out of distribution initial conditions. On the other hand, when failures occur, fail detect can accurately capture these failures by raising an alarm. Additionally, note that fail detect capture different types of failure, such as a failed second fold on the left and a failed first fold on the right. We further consider a clean up spill experiment, where one arm sets the fallen cup upright and the other cleans up the spill. We similarly observe the ability of fail detect to avoid false positives when the policy is successful under different initial conditions. Meanwhile, different failures are also captured. On the left, fail detect captures the handing behavior of the robot after towel pickup, and on the right, detection is made as the robot performs a ghost grip yet still approaches the spill. Overall, fail detect performs runtime failure detection for generative imitation learning policies without access to failure data. It is performant across simulation and hardware experiments with detections that align with human intuition. Fail detect with our proposed log-PZO score is also fast, enabling runtime detections during or slightly after failure occurs. It is robust by reaching approximately 75% average accuracy. Please visit our poster for more information. Thank you.
We have time for questions. Ground floor in the middle.
Thanks for the great talk. This might just be because I'm unfamiliar with the one-sided conformal prediction you were referring to. But if you have no a priori knowledge about the distribution of that signal on your success metrics or on your successful rollouts, how can you know where to place that threshold such that you are going to capture a certain false positive, false negative rates?
Yeah, that's a great question. So conformal is a distribution-free framework. So as long as your data are exchangeable, or like RID in a special sense, we can guarantee that. It's not really requiring that your trajectory of scores have a specific or follow a specific distribution.
Maybe question, ground floor in the middle.
I have a question. So when I'm looking at the video, I can see that some of these failure detections are not exactly aligned with when these failures are actually occurring, between when the detections are happening as to where these failures are occurring. And I feel like temporal alignment is pretty important when you're trying to leverage these types of failure information. So do you have any thoughts on how to actually get that working with your system?
I think there are two parts. The first is design of the threshold. We probably can calibrate it on more success rollout. And the second is train the detector to better reflect the training distribution or the data demo data better. Both could help to have a more timely detection.
Right,
okay, in the interest of time, let's move to the next presentation. Let's thank the speaker again.
Okay. Next, we have Unified Video Action Model, presented by Shuang Li.
Okay, hello everyone. I'm Shuang Li. Today I will present Unified Video Action Model. So video generation is very powerful, but why is it not widely used in robotics? So in previous methods, we first generate videos and then extract actions from the videos. However, there are two main limitations. First, video generation is slow. So for tasks that requires faster robot reaction, video generation is not suitable. And second, error accumulation. There are often artifacts in the generated videos. For example, the saucer disappears in the video, and the noisy video can cause wrong actions. So in this work, we aim to make video generation more practical for robotics. And we propose unified video action model. It enables precise policy and real-time inference. It also supports versatile functionality, so a single model can be used for different purposes. For example, serving as a policy model, video generation model, forward and inverse dynamics models. So how does our model achieve this? There are three key designs. First, joint video action embedding. We want to learn a joint latent that incorporates both the video and action information. So the video can provide scene information for action prediction, and action can provide dynamics information for video generation. And second, decoupled video action decoding. We have two decoders, one for action generation, one for video generation. And during policy inference, we can skip the video generation, and this enables fast policy inference. So the joint embedding and decoupled decoding further unlock the potential of our model for versatile functionality. And we will achieve this through mask training. So during training, we can mask out some input and output of the model. For example, if we use observation as input and action as output, this becomes a standard policy model. If we mask out all the actions, and we only use the observation as input and predict the future observations, this is the standard video generation model. Through this mask training, we can train a single model for versatile functionality. This can also reduce the overfitting problem for each specific task, but previous policy models without this video generation can't do the mask training. So next, we show the policy result. We compare our model and baselines from 4 different aspects. The policy performance. We test these models on both a single task setting and multitask setting. And then we compare with baselines, including OpenVLA, UniPy, diffusion policy. We see that our model performed the best on most of the tasks, especially on the multitask setting. And for the Liberal 10, we also compare with the Pi0, which is a state-of-the-art policy model, and also fine-tuned on Liberal 10. Our model has better performance. So how much do videos help actions? We compare our model with a version that only do the action prediction. And we found this unified video action prediction can significantly improve the performance. It is also more robust to visual changes. We test on the settings with significant visual changes from the training data, including the background color, background object, and gold color. And we compare with the baseline diffusion policy, we found that our model is more robust to these visual changes. So we also evaluate different methods of their inference speed on generating a single action trajectory. Our model achieves a similar performance as diffusion policy, and both of them are much faster than OpenVLA and UniPy. So is this speed sufficient for real-world tasks? And to evaluate this, we test our model on 3 real-world tasks, including the cup arrangement, mouse arrangement, and toe folding. We can see our model can do this real-time policy inference. It also achieves a higher success rate than the diffusion policy baseline. So to summarize, we propose a unified video action model. It can benefit from video generation, enables scalable training and multitask learning without sacrificing the robot policy performance in terms of action accuracy and inference speed. It also supports versatile functionality when operating on the video action pairs, and a single model can be used as a policy, video, forward, and inverse dynamics models. Please check our poster for more details. Thank you.
Questions? To the right, to my right.
Thanks for the talk. So, have you ever tried, if you increase the number of demonstrations, how the auxiliary video diffusion loss will help to improve in that case? Yeah.
Yeah, actually we do have a small experiment. We add 3,000 additional human videos, and we found there's a 4% success rate improvement on the labor 10 task. But it's also like a small scale. We believe if we add additional video data or video action data, it can further improve the performance.
Okay, thank you.
Yeah, thanks.
One more question. Ground floor, middle.
Should I do this way? Okay. Yeah, I was wondering if you try to see if the model can generalize to normal scene object or trajectory. Like how well is the model's generalization? And thanks for the talk.
Thanks for the question. So actually, we have a visual robustness testing. It's already the null scene setting. We changed the background color, background objects, but we didn't test on the new trajectory. We believe that if we use additional video data, we can learn more robust behaviors from those data. But yeah, thank you for the question.
Thank the speaker again. All right. Next, we have Dex Wild, Dexterous Human Interactions for In-the-Wild Robot Policies, presented by Tony Tao and Mohan Kumar Srimar.
My name is Tony Tao. My name is Mohan. And we're here to present Dex Wild, Dexterous Human Interactions for In-the-Wild Robot Policies. I want to start with a question. Where should we get the data to train robots? One way is to teleop the robot. This gives high-quality data, but it's difficult to get diversity. On the other hand, human videos are rich in diversity, but they're hard to use directly in training. So how do we get both quality and diversity? Well, we could just take robots out of the lab, but robots teleop in the wild is hard. That's why we're introducing Dex Wild, a human hand data collection system for collecting high-quality, diverse demonstrations in the wild. Dex Wild has two parts, a human data collection system that's almost 5 times faster than teleop, and a co-training pipeline that combines human and robot data to improve generalization. We believe that good data has 3 traits. It should be diverse, including many objects, tasks, and environments, high quality, so it's easy to use for training, and reusable, so it's general enough for use on any robot. These traits guide our design goals. To gather diverse data, our system is portable. To get high quality, we make no sacrifices in fidelity. And to make sure our data is reusable, Dex Wild data is robot agnostic. It's extremely easy to bring Dex Wild to new places and collect demonstrations. There are only 3 components: a tracking camera for wrist tracking, a hand sensor pod, and a mini PC for storing the data. In total, we collect almost 10,000 demos in 93 unique environments. We collect data at home, at the office, in the kitchen, or in the game room, indoors, outdoors, in the day, and in the night. We really brought Dex Wild everywhere. Even though Dex Wild is extremely portable, we make no sacrifices on data quality. We start with mocap gloves for precise hand pose estimation. Then we use palm-mounted cameras to capture high-quality task-centric observations. Lastly, we use Aruco markers to track wrist pose, which avoids fragile SLAM-based wrist tracking. We carefully designed the observation and action spaces so that Dex Wild is robot agnostic. We first mirror the camera setup on the robots. This aligns the observation space and avoids embodiment-specific information from being captured. Our human hand actions can be retargeted to any robot hand, even ones that don't exist today. This means as hardware improves, DexWall data can continue to be used.
Once we collect the data, how do we use it? We use a co-training approach. Human data gives us diversity and affordances, while robot data provides grounding and low-level control. We combine these two to produce robust, generalizable policies. We collect lots of human demonstrations and a small amount of robot data and combine them together. We sample from the dataset using a fixed co-training ratio for human to robot, and then we train these policies using ACT and diffusion policy.
So once we have these models, let's bring our robot into the wild. We achieve zero-shot generalization for 5 tasks in 53 environments. Our policies work on average 3.8 times better than training with robot data only in completely unseen scenes. DexWall also works for complex bimanual tasks, and we show that our method enables robots to complete tasks that require coordination between both arms. We also show that low-level robot skills can transfer between similar tasks. For example, combining human pouring data and robot spraying data enables pouring with no additional robot demos. Using the same hand, we can zero-shot deploy to an entirely new robot arm. And for new hands, just collect a few demos in the lab and co-train it with the human data you already have. And it's able to zero-shot just like before. Please check out our website
and come say hi at our poster.
Questions? Okay. Middle, ground floor. Yeah. Nice.
Hey, thanks for the great talk. I had a quick question. So the rollout videos you showed, are they real time?
So those videos were sped up, but we have real-time videos on our website.
Yeah. Thank you.
One more question? Okay, I have one question. So I'm curious about when you say you generalize to new robot in hands, how do you deal with proprioception, like actual joint encoding of that specific hand?
Yeah, so that's a great question. So what we do is we basically take our human hand data and retarget it to the new robot hand. And then for the existing robot data that we have, we can also retarget that to the new robot hand. And then we co-train them all together. Yeah.
I see. Okay, thank you.
Thank you.
Okay, let's thank our speaker again.
So our next presentation will be From Foresight to Forethought, VLM in the Loop, Policy Steering via Latent Alignment by Yilin Wu.
Hello, I'm Yilin. Today I'm very excited to share our work, From Foresight to Forethought, VLM in the Loop Policy Steering via Latent Alignment, a way to make open-world manipulation more reliable. Recently, stochastic behavioral cloning policies are powerful ways to learn diverse and complex robot behaviors from human demonstrations. Now, imagine that we pre-trained a diffusion-based imitation learning policies in our lab on diverse ways of picking up the cup, from the handle or from the lip. At test time, the user gives the specific language instructions to ask the robot to serve a cup of water to the guest. Sometimes the sampled behavior from this pre-trained policy is really great. It picks up the cup with a handle. However, sometimes it completely fails at the task. Or it produces a more nuanced failures, like violating the sanitation rules with the fingers in the cup. How can the robot select actions at test time that lead to good outcomes? First, we need the robot to predict the future consequences of the actions. And second, it must be able to verify the outcomes aligned with a given task. Therefore, our key idea is to use a word model to predict the future consequences of the sampled actions, and then use VLM's strong reasoning capabilities to verify that outcomes are aligned with a given task goal. However, word model and the VLM operate in fundamentally different representations. On the left, the word model imagines the future latent state trajectories given the current observation and sampled actions. On the right, ideally, the VLM should reason and verify the outcomes are aligned with the given task in language description, but that relies on textual representations of the future. To enable the communicate between the word model and the VLM, we need to align the word model's latent state with VLM's text token space. Specifically, we need to fine-tune the VLM to describe the latent trajectory in natural language in order for us to choose which trajectory description is most aligned with the task. After alignment, we now take a closer look at our system with this steering process for this cup task. We begin by forward simulating the future observations for T steps with the word model in the latent space. And then we can ask the VLM to translate those latent states into text descriptions with enough motion details for evaluation. Finally, we need to query the same VLM again to choose which action plan is most aligned with the task to finalize the steering process. On the left, our system can satisfy the user request by only keeping the mode of grasping by handle. On the right, under novel such task descriptions, our system can also flexibly choose another mode, grasping by rim, to satisfy the user request. Now, beyond this task, we move towards a longer horizon task that transfers the fork from the table to the bowl. Given this specific user request, the VLM evaluates various strategies of picking up the fork and translates those plans into text. It then determines that grasping by the handle is the only way to maintain sanitation for eating. So it executes the specific plan in the real world. In the subsequent phase, similarly, the VLM filters out the other plans that place the fork outside the bowl, selecting the optimal approach that is consistent with the task goal to execute, which is to place the fork inside the bowl. Beyond this long horizon task, we further demonstrate that by using flexible reasoning capabilities from a VLM, our system can adapt to novel task descriptions, reliably steer our policy towards good outcomes across different task contexts. Quantitatively, we also showcase that under such novel task descriptions, our system can achieve a 30% performance gain over the base policy by using our proposed steering method across 3 tasks. At the same time, our system is also be able to generalize to small environmental perturbations, handling objects of different sizes and colors, as well as the diverse table covers. If you're interested in our method about more details and more ablation results, please stop by our poster at poster 54 at Imitation Learning Session 1.
Questions? If there is no, maybe I can start one. So can you specify what is your word model? Do you train it, or is it a pre-trained word model?
Yeah, we are using a Dreamer V3 style word model, and we pre-train that with the rollouts from the policy and then freeze the parameters when we fine-tune the VLM.
Okay. One question in the ground floor middle.
Thank you for the excellent talk. I was wondering, have you compared the results with your approach with something that would instead produce predictions directly in image space? And now you have a very rich description that does not have potential lossiness that arises from translating it into language, etc. I wondered if that was a problem, and I wondered if there's some comparison to this.
Yeah, we have a baseline that uses the image, predicted image observations with GPT, and our method has higher performance over that. And also, we think that image contains kind of some redundant information when you're trying to evaluate your action plans against task goal. For example, you don't actually care about the texture of the table when you're trying to evaluate the grasping of the cup.
Thank you.
Okay, let's move to the next presentation. Thank the speaker. So the next presentation will be, is your imitation learning policy better than mine? Policy comparison with near optimal stopping. This will be presented by David Snyder.
Hi, everyone. My name is David, and I'm very excited to be presenting work done in collaboration with TRI and the Princeton IROM Lab on near-optimal stopping for sequential policy comparison. Policy comparison is a fundamental problem in robotics. It is a gold standard in evaluation and codifying empirical progress within the field. And in addition, it's very important for understanding design selection. The analytical opacity of many design choices often requires that downstream evaluation is the best way to reason counterfactually about design choices. Finally, it's important for establishing a practice of reproducible science in robotics. So the policy comparison problem can be understood as a task specification, instances of which are drawn IID. For now, we will assume binary success-failure metrics. Under these assumptions, each policy induces a true success rate on the distribution of task instances, which are traditionally estimated by drawing new examples and then observing their successes and failures in order to estimate the success rates. In so doing, this constructs a composite versus composite statistical testing problem where the blue region indicates that the test policy is better, and the red region indicates that the test policy is not better than the baseline. Now, the standard approach for tackling this problem is a batch setting in which n trials are run, the associated successes and failures are observed, and a decision is made. This decision will control the false positive rate, deciding blue when red is true, but it comes with an important catch, which is choosing the batch size n. Importantly, if the empirical performance gap is large, then not many trials will be needed to distinguish the policies, but if it's small, many trials may be required. This is important because once n is chosen, we are committed to running all and only those trials, lest early stopping or adding additional trials creates p-hacking, which invalidates statistical assurances. In so doing, we have a kind of tug of war, where reliable improvements require many trials to control the false positive rate, but evaluation is, of course, very costly, so we want to minimize the number of trials needed. To do this, we introduce STEP, an efficient sequential testing framework for policy comparison with tunable probabilistic guarantees. STEP incorporates new trials in a sequential fashion to make these comparison decisions. In so doing, it can stop early while maintaining the statistical properties of batch procedures while minimizing the expected number of evaluation samples. To do this, it synthesizes sequential decision boundaries which uniformly control the false positive rate while weighing the aggregate evidence for each hypothesis at every time step and stopping when a threshold is reached. To use STEP, the user sets the false positive limit alpha, as well as nmax, which is interpreted as the greatest number of trials willing to be run to seek a significant decision. STEP then adapts to the comparison difficulty and is robust to the choice of nmax. To illustrate this, we show a case starting with an easy setting of a clean spill task with an empirical gap of 50 percentage points, where STEP returns a decision in 8 trials, even though nmax was set to 50. Moving to a slightly harder task of fold red towel, with a gap of 36 points, STEP returns a decision in 19 trials, again despite an nmax of 50. On a harder setting of an eggplant in basket with a 16-point gap in simulation, the time to decision is now 130 trials with an nmax of 500. We now switch back to the fold red towel task to illustrate the robustness to nmax. So if we adjust the nmax from 50 to 200, the number of additional trials required to a decision is only 2 additional ones. If we again increase nmax to 500, which is a 10-fold increase over the initial setting, we observe that the total number of trials required is only increased by a total of 4 to 23. In summary, STEP reduces evaluation inefficiency while maintaining rigorous comparisons by adapting to the difficulty of the particular policy comparison instance. In addition, it is fast and efficient to run and works for multitask and multi-policy comparisons as well. For more information about using STEP to evaluate your policies, please see the project website and our poster. Thank you.
Questions? Ground floor in the middle.
Oh, thanks for the talk. From your presentation, it seems that STEP is a pretty generic framework. So I'm wondering whether or not in your title, is there a reason that you're restricting your framework to an imitation learning policy comparison setup?
Yeah, that's a great question. I would say that really, ideally, STEP is designed for cases where the evaluation is costly. which I think applies perhaps to robotics broadly, perhaps even beyond imitation learning. We were interested in imitation learning applications, hence the title as selected. But yeah, that's a great question. You could use it for other policy comparison as well.
Any other questions?
Thanks for the talk. My question is, how do you evaluate when the policy isn't like success or failure, when it has like progressive rewards?
Yes. So for right now, we need to assume that you have a kind of aggregate over, say, an entire trajectory. We're in the process of generalizing this to partial credit, say, if that sort of gets at the general idea. But yeah, for correlated rewards, then it would not hold. You need more sophisticated tools.
Thank you.
Okay, let's thank the speaker again.
Okay. Next, we have DDAT, Diffusion Policies Enforcing Dynamically Admissible Robot Trajectories.
Hi, everyone. I'm JB. I'm postdoc at Berkeley. And today, the project I'll present was a collaboration between Google and Bayer. And this project aims at generating diffusion trajectories for robots that are feasible. So the way we do that with diffusion is that you typically generate trajectories. All right, I can keep going. So yeah, I'm a postdoc with Professor Nigar Meir, looking for a job in industry. So yeah. So here's the way we do it. You diffusion, you start with a random bunch of points, that's your states, and then you denoise it, so the noise level goes down, and so the video should play, and the points will coalesce into a nice trajectory. Here we go, maybe. All right. So then you get your clean trajectory after some time. You can see it's very costly and slow to denoise. That's a, yeah. But on the good side for diffusion, when it works, is that you get a whole trajectory at once. It's better than sequential. It's very good for long horizon planning. Okay, very good for long horizon planning, even in sparse reward environment. But the downside, yes, it's costly to do this denoising. And what I want to talk about today is that the problem, because it is stochastic, you cannot enforce this trajectory to actually satisfy your equation of motion if you use it for robot planning. So on the next slide, I will, yeah, next slide.
Can we advance to the next slide?
Thanks. So here's the problem formulation. We have a black box simulator for robot dynamics. So that can be your gym simulator, for instance. Then a bit forward, we have our data set of trajectories, which exhibit the behavior of the robot you want to imitate. And then a bit forward, we want to train a diffusion model that condition on your initial state, generate your sequence of next states. But there's a catch. We want this trajectory to be feasible. So that means in it to respect your dynamics. So the next state must be reachable. So there must exist an action that go from your current to your next state. How we do that? So on the next slide, the training of our approach, get a clean trajectory, add noise epsilon, send it through a diffusion model, and then you get a denoised but maybe not feasible trajectory, so you do projection. You get tau p, and then a bit after that, you can get use that for your loss to update your diffusion model. So the projection algorithm, that's a crucial part here, and it's hard because you have black box dynamics. So when you have only a sequence of states, there is a way of doing it with naive projection, but it doesn't scale very well. It takes a lot of computation. So we kind of improved it using a reference trajectory for long horizon planning. But yeah, this sampling-based technique is kind of costly. So yeah, you can use a reference for better long horizon planning. But because it doesn't scale well, instead we generate action at the same time as you generate state. And then using those actions, it's much easier to generate a feasible trajectory. But you don't need to discard all your state prediction. Instead, you can use your state prediction to create a feedback term with your action prediction and get a better next state that is feasible. And that's very fast. That allows you for good tracking. So then on the next slide, we use those projector to, of course, do feasibility, but it also improves the quality of trajectories. So we tested on a bunch of different systems. We did long horizon planning, so that means several hundred time steps. And we trained several diffusion models as baseline, one that generates states in action, one that only plan in the action space. Was our model with projection is actually better in terms of reward. We also deployed it open loop, zero shot on the hardware on our Go2. Our baseline fails most of the time, whereas adding those projection helps a lot to generate a feasible trajectory. And to summarize, so projection can help you generate high quality trajectory so you can wait longer before replanning, which is important because diffusion is costly to replan. So that's all. Here's the QR code, and come see me at the poster. Thank you.
Thank you. 2 questions. So ground floor to my right.
Thanks a lot for the presentation. So when you do this projection, how much of this embodiment mismatch can happen? So for example, you take like a go-to robot and you have like, you train a diffusion policy with data set for that, from that. And now you try to deploy it like on another embodiment completely. Does this projection still hold in that case, or is there certain assumptions that you have to make about the system?
You need to do it on the same system. Like the dynamics, especially if you want it to be feasible, it is very embodiment specific. So you need your simulator to match your embodiments in your physics.
So both the data used for training diffusion policy as well as the deployment that you're doing should be in the same embodiment?
I guess we didn't try training on data generated with different simulator because we just did it all on the same. But it might work, yes.
Right. Thank you.
Okay. In the interest of time, we'll move on to the next speaker, and let's thank the speaker again.
Okay, last presentation of this session will be Factor, Force Attending Curriculum Training for Contact-Rich Policy Learning, presented by Jason Liu.
Hi, I'm Jason, and I'll be presenting Factor, Force Attending Curriculum Training for Contact-Rich Policy Learning. For contact-rich tasks, humans rely heavily on force feedback for task completion and generalization. When lifting a box, we sense its weight and resistance, and we adapt our motion based on this force feedback, just as we do when cutting fruit or rolling dough. But in robotics, we often underutilize force information in both data collection and policy learning, relying primarily on visual feedback. Because of this, robots often struggle to perform contact-rich tasks reliably. One main reason force is underused is that most low-cost teleop systems simply don't capture it during data collection. For example, these leader-follower arms have become popular, but they typically lack force feedback for the user. Yet humans naturally rely on both vision and force sensations, making vision-only teleop unintuitive, especially for contact-rich tasks. To this end, we present a low-cost force feedback teleop system, which allows the user to feel the environment that the robot experiences. We use standard off-the-shelf servo motors for the leader arm. It's easy to build and only costs around $1,000 USD. Assembly instructions are on the website. To achieve force feedback, we do not use any additional sensors. Instead, we leverage joint torque information that is readily available on many existing manipulators, such as the Franka Panda. Specifically, we relay and scale external joint torque of the follower arm back to the leader arm. We additionally add a velocity damping term to reduce oscillations caused by the force feedback in the leader arm. To further facilitate teleop, we implement gravity compensation and kinematic redundancy resolution to prevent the leader arm from swinging uncontrollably during teleoperation. All terms are summed together to yield the final leader arm control law. We compare our force feedback teleop system to a baseline without force feedback, and we observe a significant improvement in task completion rate, completion time, and ease of use. So now that we can collect force-augmented robot data, the question becomes, how can we effectively leverage this additional modality in robot learning? We find that naively adding force to policy learning does not guarantee performance improvement. For example, this action chunking transformer, trained with both vision and force observations, fails to generalize to novel objects unseen during training. This happens because BC policies often overfit to vision input and ignore force when it is added naively. To address this issue, we introduce FACTOR, Force Attending Curriculum Training. The idea is to blur the vision input towards the beginning of training such that the network is encouraged to attend more to the force input. As training progresses, we gradually unblur the vision input to recover its full resolution. We can also apply blurring in the vision encoder's latent space to achieve a similar effect. FACTOR allows the network to properly attend to force input. We find that this greatly helps the policies generalize to unseen objects, where FACTOR policies outperform the vision plus force baseline by 43% in success rate for objects outside of the training distribution. We analyze our findings further by visualizing the cross-attention between the vision and force observation tokens with the action tokens. We can see that in the baseline policy without FACTOR, the force input represented in blue is very much ignored. However, with FACTOR, we can see that the attention to force outweighs that of the vision as the arms begin lifting the box, which signals a learned mode switch. We also observed that FACTOR policies exhibit robust recovery behavior. This behavior was never recorded in the training data. This happens because when the arms lose contact with the object, the robot's joint torque readings revert back to values before lifting up the object. And since our policy properly attends to force inputs, the policy can naturally recover to a pre-lift state. And finally, building instructions and code for the FACTOR teleop system and training setup are both available on the website. Thank you.
Questions? Ground floor middle, yeah.
Do you think you can extend this to tactile data on the hand itself?
Yeah, I think so. It's very similar. We actually try a similar thing with the gripper, where we're recording the gripper current, and the similar effect, the similar method applies as well.
Okay. Okay, in the back, ground floor.
Thanks for the talk. So the current-based joint torque, are you using current-based joint torque, or do they actually have joint torque sensor or torque sensors on the joints?
I'm using the external joint torque sensor, so they're actual sensors.
Oh, okay, good. Because I was going to ask about if you were wondering if the noise was maybe part of why the force did not guarantee policy performance, policy improvement. But I suppose if you're using force torque sensors, it's probably relatively low noise.
Yeah, it's pretty low noise, I find, at least on the Franka system.
Thanks.
Okay, this concludes the session, and let's thank the speaker again. Before we go for dinner, I think the program chair will show up.
All right, everyone, as you walk outside the auditorium, just a quick reminder, you know the drill by now. We're going to have food outside. Hopefully food will be until 8 p.m. tonight. So that's in Founders Park, which is on the left-hand side. After getting food and drinks, please make your way to the poster session. As yesterday, we're going to have posters, demo, sponsors booth is going to be fun. Definitely grab food and get there. And just a small reminder for the virtual presentations, there will be a QR code on the posters to be inclusive, like, please connect to these Zoom presentations and ask questions. Enjoy Robo Night.